Chemistry is a pure science that deals with the composition, properties, and uses of matter. In our everyday life, we encounter chemistry, and that is why chemistry is very, very important for us to study. Chemistry is one of the pure sciences that we are supposed to study if we are to be writing WAEC, NAEC, or JAMB. The others are biology and physics. So why do we study chemistry? You have a palm wine. When the palm wine is freshly gotten from the palm tree, it tastes very sweet, but after some time, it sours. So what makes the palm wine to sour? Chemistry. You have a nail. A newly bought nail or a newly made nail is normally very shiny, but after some time, the nail gets rusted and looks exactly like this. What causes the rusting? Chemistry. When you're sick, you buy drugs, you take drugs. So, what are the elements or compounds that make up the drugs? So that when you take them into your body, they function effectively in order to make you to get well. The process of making these drugs is also chemistry. So there are plenty things in life, in our everyday life, that has to do with chemistry, and that's why we study chemistry. So as a way of introduction, we are going to be looking at the definition of chemistry. Chemistry is a pure science that deals with the composition. What are the makeup components of the drugs that we take? The chemicals that we use, the detergents. What is the composition? What are those elements that come together to make it up? Properties. How does these chemicals, how do the chemicals, how do they react? What are their properties? And uses. What and what can they be used for? So chemistry is a pure science that deals with the composition, properties, and the uses of matter. Matter is anything that has mass and occupies space, just like the chemicals that we're talking about. So now, in our everyday life, we encounter chemistry. So what are those things that happen in life that are actually chemistry? We'll talk about making palm wine sour, just like I showed you earlier. Rusting of nails, just like I showed you earlier. And drugs production, how you go about producing your drug. Also, the process of cooking our food, lighting matches, and burning of firewood. All these are chemistry happening in nature. So in time, we are going to be studying all these in details. And that is chemistry. So when they ask you in class, why are you studying chemistry? You study chemistry because you want to understand all these that happen in your everyday life. And chemistry is a pure science because it goes through the normal process that every science, every pure science goes through in its study, such as observation, carrying out of experiment, formulation of hypotheses, formulation of laws, and taking down records. So all the processes that every pure science goes through. Chemistry is a very, very important subject, and that is why we study it in secondary schools. What are the uses of chemistry? Why do we study chemistry? What are those things that we can use chemistry to do? If you want to grow food in the farm, we need fertilizers to help our crops to grow very well and in a very healthy form. We also need insecticides to kill the weeds so that they don't disturb our crops. So in order for us to grow food, we need chemicals, because it is with these chemicals that we make the fertilizer as well as the insecticides. If we want to build a house, we need concrete, we need cement, we need tiles. All these things are made from some chemicals. So we need to study them in chemistry. In military and space travel, we need to manufacture ammunitions, the gunpowder and the ammunitions that we need for our military. We also need chemistry to know the way to produce them. In medicine and in pharmaceuticals, where we produce drugs, we need to know the right chemicals to mix together in order to get the right effect. So all these things are the uses of chemistry. And as a way of getting down your notes, I have them outlined on the board. Uses of chemistry. Food. In order to have food, you need fertilizers in your farm so that our crops can grow very well. And we also need insecticide to kill the weeds. For clothing, in order for us to manufacture have good textile and fiber production, we need to know how to make the chemicals that are used for this. In our military and space science, we need to manufacture ammunition. So how do we go about it? The knowledge of chemistry helps us in the manufacture or production of ammunition. And in space science, we need to know chemistry in order for us to explore very well the outer space and the planets. For housing, we need cement. So what are those chemicals that we use in producing cement? We also need concrete, steel, tiles, and other things. Then in medicine, for us to produce drugs so that we can live healthily, we need to know the components of these drugs, and that is chemistry. For transportation, we need to know the right fuels to use and how to make this fuel, how to do fractional distillation. In Nigeria here, the major income that we get is from our crude oil. So how do we turn this our crude oil to final products like PMS and diesel? We need the knowledge of fractional distillation, separation, and that is chemistry. So we also need chemistry to produce alloys. An alloy is a combination of metal that can make it very, very effective for use in producing automobiles because it brings out the best quality in those metals whenever they are combined. So chemistry can be used in all these areas in life: food production, clothing production, military and space science, housing, medicine, and transportation. And that is why we learn chemistry. So chemistry is a very, very important aspect, or is a very, very important pure science. Chemistry is very, very important for us to survive as human beings in life. But at the same time, chemical processes also affects human being and the environment adversely. There are some chemical processes that harm the environment. Example, pollution. When chemical waste from oil industries, like we have in the Niger Delta, when these wastes are discharged inappropriately, maybe through gas flaring or discharged due to pipeline being damaged, this can cause very, very harmful effect to the environment. When there is oil spillage, the chemicals in the oil are not very friendly to the animals or animals that are in the water. The aquatic life are adversely affected. Also, when you do oil flaring or gas flaring, these gases that are discharged into the atmosphere are not very good to the environment. If you go to some states, you find out that people are taking cocaine, morphine, and heroin. Youths are addicted to this and they continue to take it, and it's not good to their health. That is abuse of chemistry, and it's also called drug abuse specifically. Also, corrosion of iron makes the iron not to be glittery and to look good the way we would have wanted it to, or the way we would have wanted to be looking. All these are adverse effects of chemistry, and they need to be checked. In order to check drug abuse, government has to bring out strict laws in the manufacture and transportation of these drugs that are not good, drugs like cocaine, morphine, or heroin. There has to also be strict laws on gas flaring. Chemical waste from oil industries has to be discharged in the proper way. There has to be good education to the youths so that they will know how to use drugs. And corrosion can also be prevented by using alloy and cathodic protection. So, as a way of the adverse effects of chemistry are corrosion of iron, rusting in the presence of water and oxygen. For rusting to take place, there has to be water and oxygen. And this corrosion of iron can be prevented by alloying, coating, cathodic protection, and use of sacrificial metal. Pollution, which is caused by chemical waste from factories and oil refineries. They actually pollute the environment and harm living things. How do we check this? By having or doing safe discharge of this waste and treating them actually before you discharge. If you treat the waste before you discharge into the water bodies, they will be less harmful or even non-harmful. Drug abuse, when people are addicted to drugs like heroin, cocaine, morphine, it can damage their health. And this drug abuse is very, very dangerous to human life. And for us to check this, we need strict laws, and we need to educate the people that are taking it that it is not good for them. So you see these three adverse effects of chemistry, and you see how to prevent them or check them attached to them. So WAEC may ask you such questions. How do we take care of corrosion? By alloying, coating, cathodic protection, and use of sacrificial metal. How do we take care of pollution? By making sure that the waste are safely discharged and treated before discharging. How do we take care of drug abuse? By enacting strict laws and also educating the populace. So that is the adverse effects of chemistry and how they can be controlled or checked. When you study chemistry, you want to get a job after studying chemistry, maybe in the university, you come out, you want to get a job. What are those job opportunities that are available for people with the knowledge of chemistry? Where can somebody that studied chemistry work? Where can he or she get employment? There are many places that somebody that studied chemistry can work. You can work in the oil industry. Nigeria has plenty oil industry companies in Lagos and in Port Harcourt. You can work in any of those places if you have the knowledge of chemistry. You can also work in food processing industries. Those industries that make milk, canned food, you can work with them. You can also work in the industry that give health services, the pharmaceuticals. Those pharmacists, they will have knowledge of chemistry, so they can work in pharmaceuticals. They can also work as chemists. Also, people with the knowledge of chemistry can also work as teachers or lecturers in universities. So when you have the knowledge of chemistry and you get to the university and study courses like biochemistry, pharmacy, chemical engineering, there are lots of opportunities for you to work. So you can also work as a chemical engineer in oil industries. So as a way of getting notes, I've outlined this on the board. So somebody with the knowledge of chemistry can work in the industry that gives teaching services. He can become a chemistry teacher or lecturer for secondary schools, universities, polytechnics, and all the rest of them. Can also work in food processing industry. People like food technologists, research chemists can work in food processing industries. They can also work in petroleum and petrochemical industries, like the chemical engineers, laboratory assistants. Also, they can work in health services, like the pharmacists, those that produce drugs, the biochemists, the nutritionists, those that advise us, counsel us on the best food to eat. They can also work in extractive industries, like the chemical engineers and the research chemists. Extractive industries, how you get the metals and other things out from the earth crust. They can also work in the agricultural sector as agriculture scientists and chemists, and also in forestry as scientists who do research on the best possible way to conserve our forest. So all these are career opportunities for those that have the knowledge of chemistry. So when you're studying chemistry, don't feel bad because matter is anything that has mass and occupies space. This nail I'm holding is a matter. It has mass, I can feel the weight, and it occupies this space. The jug that I showed you the other time is also matter because it has mass. Mass can be likened to weight, and it also occupies this very space. So anything that has mass and occupies space is matter. The palm wine, everything, even we human beings, we are all matter because we have mass and we actually occupy space. How do you differentiate one matter from the other? How do you identify matter when you see them? You can do that using their properties. Properties are those characteristics of matter that help you to differentiate one from the other. These properties of matter can be physical or chemical. The physical properties are those that are associated with physical change, such as boiling point, melting point, density, etc. Whereas chemical properties are those properties that are involved with the formation of new substances or new chemicals, as the case may be. Chemical properties are things like fermentation and rusting. Now, we are supposed to know the difference between physical change and chemical change. A physical change is one in which no new substance is formed and which is also reversible. Whereas a chemical change is one in which a new substance is formed and it is not reversible. So those are the basics of the nature of matter. In subsequent classes, we are going to be looking at the forms in which matter can exist, either as an element, a mixture, or a compound. So as a way of getting down notes, we can say that matter is anything that has mass and occupies space. Example is the nail, palm wine, drugs. The examples that I've already shown you. In fact, almost everything that you can see around you can be called matter because they actually possess mass and occupy space. Now we look at properties of matter. These are characteristics that substances possess which helps in identifying them. Now you can actually differentiate between water and ethanol using their boiling points because they don't boil at the same temperature. Now, physical properties are those properties that are associated with the physical changes. Example is boiling point, melting point, density, hardness, color, odor, taste, etc. Chemical properties are those involved when matter undergoes a change to form a new substance. Example is rusting, fermentation, dissolution of metals and limestone in acid. Now, we have physical change and chemical change. All these are chemical changes: rusting, fermentation, and dissolution of metal and limestone in acid, because in each case, new substances are formed. So we say that chemical change is one which is not easily reversed and in which new substances are formed, whereas physical change is one which is easily reversed and in which no new substances are formed. So that is how we wrap it up on the nature of matter. In subsequent classes, we are going to be looking at elements, mixtures, and compound. And thereafter, we look at separating techniques. Please hit the subscribe button. Thank you. Matter may be classified as elements, compounds, or mixture. Elements and compounds are pure forms because they cannot be broken down into simpler substances, whereas mixtures are impure because they can still be separated. An element is a substance that cannot be broken down into simpler forms by ordinary chemical process. Example of an element is oxygen, the one we breathe in, hydrogen, sodium, sulfur, potassium, all the elements that you know, and there are about 109 elements. Compound constitutes of two or more elements chemically bound together. Example of a compound is water, consisting of two elements, hydrogen and oxygen. Another example of a compound is hydrogen chloride, HCl, consisting of hydrogen and chlorine. Mixture constitutes of many substances that can be separated using physical processes or chemical processes as well. Example of mixtures are blood, urine, the milk you take, the air that you breathe in, consisting of oxygen, nitrogen, and the rest of them, the blood. As a way of taking notes, we are going to be looking at these elements, compounds, and mixtures. Matter may be classified as elements, compounds, and mixtures. An element is a substance which cannot be split into simpler units by an ordinary chemical process. Example is oxygen, hydrogen, etc. And there are about 109 known elements. Elements are actually in pure form because they cannot be broken down into other elements. A compound is a substance which contains two or more elements chemically combined together. Example is H2O, which is water, and HCl, which is hydrogen chloride. Note that the properties of the constituent elements, let's say for hydrogen, for water, the property of water, H2O, is very different from the property of hydrogen separately or oxygen separately. Just like HCl, this is an acid, it's corrosive. the property of this acid is very, very different from the property of the hydrogen differently, or the chlorine differently. Now, a mixture contains two or more constituents which can easily be separated by physical methods. In subsequent classes, we are going to be looking at separation techniques. We are going to find out that we actually use separation techniques to separate mixtures. Examples of mixtures are air, soil, urine, palm wine, Coca-Cola, milk, blood, crude oil, brass, seawater, etc. Separation techniques. Separation techniques are those methods that we use in separating the constituents of mixtures. The individual constituents of mixtures behave differently. They have different properties. They retain their respective properties. So if you have a mixture like crude oil, in Nigeria we have lots of deposits of crude oil. The constituent part of the crude oil can be separated so that we can have the PMS, we can have the diesel, we can have the fuel that the aeroplane use. So how do you separate this mixture of crude oil in order for you to get the fuel, that the petrol that we use for cars, the one that airplane use, and the diesel for diesel engine? We use what we call separation technique. And the separation technique used here is fractional distillation, considering the boiling point, because the boiling point of PMS is different from that of diesel and is different from that of the AGO. So due to this difference in boiling point, which is a physical property, we can easily separate. Now you buy your rice from the market. You have stone inside the rice. Some of our locally made rice, you have stone, then you have your rice. You can easily use sieving because of the difference in size of the stone and the rice. If you have beans, also difference in size between the seeds of the beans and the stone. So there has to be physical property that can easily differentiate one constituent of a mixture from the other for you to be able to separate them into two. We have different separation techniques, and these separation techniques are actually used for specific kind of mixtures. So what are these kind of mixtures that need these various separation techniques? The separation techniques that we have are sieving, filtration, decantation, crystallization, fractional crystallization, distillation, fractional distillation, magnetic separation, chromatography, and the rest of them. Now we are going to be looking at a particular mixture and the suitable separation technique used. Sieving. When you have solids of different sizes, like in the sand of different sizes, you have to sieve. If you want to collect specific sand side of a specific mm from the other one, you have to sieve it out to get the size that you need. If you have your rice and it's contaminated with stone, and the stone and the rice have different size, and you want to sieve out, you want to separate, you use sieving. Magnetic separation is used whenever you have magnetic solids and you want to separate them from non-magnetic ones, as in steel. So whenever you have metals that are magnetic and you want to separate them from non-magnetic ones, you use magnetic separation. We have decantation, filtration, and centrifugation. And these techniques can be used to separate insoluble solid from a liquid. So whenever you have insoluble solid, a solid that cannot dissolve in a liquid, you can separate it from the liquid using either of decantation, filtration, or centrifugation. You also have evaporation, crystallization, precipitation, and fractional distillation. And these techniques are used to separate soluble solid from a solution. When you have a soluble solid, that means solid that can actually dissolve in a solvent. If you want to separate them, then you use these, either evaporation, crystallization, precipitation, or fractional crystallization. Now you have another technique known as distillation, which is used to separate solvent from its solution. You also have fractional distillation, which is used to separate miscible liquids, just like we have in crude oil. We also have separating funnel, used to separate immiscible liquids. And we have chromatography, that is used to separate solids from a solution. So how do these questions come out in WAEC or JAMB or NACO? You're going to be asked which of the following methods can be used to separate solids of different sizes. And you have options: sieving, magnetic separation, decantation, and filtration. You are supposed to pick sieving. They're also going to ask you which of the following separation techniques can be used to separate solvent from its solution. You should know that it is distillation. Now, if you have substances that are impure, to get them to be pure, you used to use separation techniques to separate them, to separate the impurities from the main substance. So how do you test for purity? How do you know that a substance is pure? What can you use in checking to know that this substance is pure, that the proper separation has been done? Test for purity. There are two major ways of testing for purity: either by using the melting point or boiling point, or by using the chromatographic characteristics of the substance. Now, impurities make substances not to boil or melt at the specific temperature that they should, as it's written in the book. Actually, impurities decreases the melting point and also increases the boiling point for liquids. Impurities decreases the melting point for solid and increases the boiling point for liquids. So, for you to know whether a solid is pure, when it melts below the temperature that it should have melted, then you know it is impure. Whereas that of a liquid, it will now boil at a temperature that is higher than the normal boiling point. Also, in a chromogram, a pure substance produces a single spot, unlike an impure substance. So that is how you test for purity. So to make impure substances to be pure, they need to undergo purification using any of these separation techniques. Matter is made up of discrete or small particles, which can either be atoms, molecules, or ions. So matter, like me, you, the drugs we take, the food, anything around us that has mass and weight, is actually made up of discrete or small particles. And these particles, we can have what we call atoms, we can have molecules, we can have ions. Atoms, or an atom, is the smallest part or particle of an element that can take part in a chemical reaction. You can have an atom of elements like phosphorus, an atom of sodium, an atom of calcium. Now, a molecule is the smallest particle of a substance that can actually exist alone and still retain the properties of that substance. You can have a molecule of hydrogen. An atom of hydrogen is written as H, whereas a molecule of hydrogen is written as H2. H subscript 2. Now, what is an ion? An ion is an atom or group of atoms that possess an electrical charge. Now we're going to look at these concepts one by one. So we are looking at the particulate nature of matter. How matter is actually made up of small particles. These discrete small particles can either be atom, molecule, or ion. Now, an atom is the smallest particle of an element which can take part in a chemical reaction. You can see this is phosphorus atom P, this is sulfur atom S. But now, if you have phosphorus that can stay alone, this might not be alone, it will be in the presence of other atoms. But now you have this P4. This is 4 atoms. It has an atomicity of 4. 4 atoms of phosphorus that are together, they can exist alone. We call it molecule. So a molecule is the smallest particle of a substance that can normally exist alone. Very, very important. Atom might not be able to stay alone, but molecules are able to exist alone and still retain the chemical properties of that very substance, be it element or a compound. Example is neon. Neon can stay alone with the atomicity of 1, just having 1 atom. Argon, hydrogen, nitrogen, phosphorus, sulfur, the sulfur molecule, oxygen molecule, and ozone molecule. So all these are molecules. They can have more than 1 atom, but the atoms just have only 1 atom. Very, very importantly. Now we look at ions. An ion is an atom or group of atoms which possess an electric charge. If this charge is positive, then we'll call them cation, or we'll call it cation. But if it is negative, we'll call it what? Anion. So these 3 are the basics. Please make sure you get down the notes. Get down the notes so that you can easily understand in future when you go through it. Now, these 3 are the major discrete forms that matter can exist in. Very, very important. Atomicity is simply the number of atoms in one molecule. Like here now, the atomicity here is 4. Atomicity here is 8 because there are 8 atoms in one molecule. All these are molecules. But atom, the difference is that atom is just 1 single atom. But for molecule, it could be more than 1 atom. And these molecules can exist alone. You can see them in nature alone, unlike what we can have here. Whereas ions are actually charged. They are charged. So you can have something like this, Ca plus. So you can have something like Na plus. This is single positive charge, double positive charge. So all these are ions. Because they are positive, they are called cations. So example of anion is chlorine with negative charge. Non-metals are mostly anions. Non-metals are mostly anions. Non-metals are mostly negatively charged, whereas metals are mostly positively charged. So these are the three discrete particles that matter is made up of. Subsequent classes, we are going to be going into details of how to use these and understand them much better. John Dalton in 1808 helped us understand more about atoms, and he put forward the Dalton's atomic theory. This Dalton atomic theory over the years have undergone several changes and modifications because some of the statements through experiments have been proven to be wrong or cannot hold completely. So now we're going to look at the statements of the Dalton atomic theory, and at the same time I'll be mentioning or pointing out the modification or the modifications that have been done on these statements. So let's look at the first statement of Dalton's atomic theory. All elements are made up of small, indivisible particles called atoms. Is this true? Yes, because all elements are actually made up of atoms, small atoms, but that these atoms are indivisible. Now, through the experiments of people like Rutherford, we're able to know that atoms are actually divisible. Atoms are actually made up of protons, neutrons, and electrons. So whereas the first part is true, the second part is not true. So this used to be very correct, but because of several experiments that have gone through in recent times, we are able to find out that atoms are actually divisible. Number two, atoms can neither be created nor destroyed. This still holds true for ordinary chemical reactions. But we know that in nuclear reactions, things like uranium can still be broken down into other atoms of other elements. Now, so this one, nuclear reactions, makes this very statement to be not completely true. Here, the discovery of electrons, protons, and neutrons made this not to be completely correct. So these are the modifications to this, whereas nuclear reactions should be taken into consideration for you to have this to be true. Now, thirdly, we have that atoms of the same element are alike in every aspect and differ from atoms of all other elements. This is not completely true because of the discovery of isotopes. Now, in isotopes, we find out that one element, say chlorine, can have different isotopes. They can have the same chemical property, but the mass number will not be the same. So this is the modification to this. Now, when atoms combine with other atoms, they do so in simple ratio. This is actually correct for inorganic reactions. The combination between the combining atoms, different atoms, for inorganic reaction can occur in simple ratios. But when you have complex organic reactions, like that involving proteins or other things in organic chemistry, there is no simple ratio combination. You can have them in multiple ratios. Now we have the fifth statement of the Dalton atomic theory. All chemical changes result from the combination or separation of atoms. I think this still holds true. So these are the statements of the Dalton's atomic theory, and these are their modifications. So these modifications We are born out of experiment that has been conducted since after Dalton in 1808. Since after John Dalton in 1808 put forward the following statements. Much of this statement has already been supported by things like the law of multiple proportion, the law of conservation of mass, and other laws. So in subsequent classes, we are going to be using those laws to do a lot of calculation and other inferences. Thank you. Let's look at symbols of elements. Now, if you want to represent an element, maybe in a chemical equation, or if you want to write it in abbreviated form and you want people to understand, you use what we call symbols of elements. Symbols of elements are simply the first letters. If the first letter is already taken, you can have the first letter plus the second letter as the symbol of an element. Now you can also have the first letter of the Latin version of that element, or the Latin name of the element, or the first letter of the Latin element and the second letter. So that is how we come about symbols of elements. So we're going to be looking at the first 20 elements and their symbols. Now let's look at element number 1, hydrogen. The first letter is H, so the symbol we are using H. Element number 2 is helium. Because H is already taken and it's also the first letter, now we use the first letter plus the second letter. So we have He as the symbol of helium. Lithium, we have Li. Beryllium, we have Be, because we already have boron as B. Carbon is C. Nitrogen is N. Oxygen is O. Fluorine is F. Neon is N. Sodium is N. Why is sodium N? Because the Latin name for sodium is natrium. So we are using this first two, Na. Sodium is Na. Sodium is Na because the Latin name is natrium. So we are using it as a symbol. Magnesium is Mg. Aluminium is Al. Silicon is Si. So the symbol can either be the first letter or the first letter plus the second letter. Hello, welcome. Let's continue with the first 20 elements and how we can memorize them and be able to use them. So we have the atomic numbers, which is increasing downwards, and we have the elements. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, with atomic number 14. Then we have phosphorus, sulfur, chlorine, argon, potassium, and calcium. So from 1 down to 20, I continued from here because of the space. So these are their symbols, and like I taught us in the last class, symbols are just the first letter of the name. Could be the Latin form of the name, like sodium. The Latin name is natrium, so the symbol is Na, the first letter with the next letter. So it could be for the English name or the Latin name, the first letter. And if the first letter is already chosen, the first letter and the second letter, the first one written in capital letter. So that's how you represent the symbol. Now, we are going to look at atomicity and atomic number. Like these are the atomic numbers of these very elements. So starting from 1 down. Now, atomicity simply means the number of atoms in the molecule of a given element. So let's say we have H2. This is how the molecule of hydrogen is. So what is the atomicity of this? The atomicity is actually 2, because there are 2 atoms of hydrogen in this very molecule. If you have ozone, O3, the atomicity is actually 3, because there are 3 atoms of oxygen in ozone. So that is what atomicity is. Now, let's look at how we can memorize the atomic numbers of these first 20 elements. Now, when I was in school, there is this method that I used, and I will encourage us to devise a way, because you knowing the first 20 elements and the atomic number will help you in a lot of calculations in basic chemistry, because you're supposed to know the atomic number. And you can easily infer the mass number with the atomic number, because most times the mass number is actually the atomic number times 2, with some little difference or fractions of difference. So how do we memorize the first 20 elements? So this is how I got around it when I was in the secondary school. So this is the elements themselves with their atomic numbers. So the way I do is that once I get into the hall, or when I want to work extensively with calculations involving atomic number, mass number, valency, oxidation number, and the rest of them. So I go with this song, Hello Helene. Hello representing hydrogen, Helene representing Helen. But I'll go through it. Hello Helene, listen Berlin, boron cannot overflow neon. So may all silly people sulfur, chlorine, argon, potassium, calcium. So that's the way I used to memorize the first 20 elements, which I would like you to look at. So let's go through it again. Hello Helene, listen Berlin, boron cannot overflow neon. Hello Helene, listen Berlin, boron cannot overflow neon. So may all silly people for phosphorus, sulfur, chlorine, argon, potassium, calcium. So this was what I was taught when I was much younger, and it really helped me a lot in trying to memorize the first 20 elements so that I can easily deduce their atomic numbers and also infer their mass numbers and use those in calculations. So I would like you to look at this very critically. Now we also looked at the symbols of elements and also atomicity. Atomic number, like I told you, are these numbers. So for hydrogen, the atomic number is 1. For helium, the atomic number is 2. For lithium, the atomic number is 3. Just like that. So up to silicon, that is 14. Phosphorus is 15. Sulfur is 16. Chlorine is 17. Argon is 18. Potassium is 19. Calcium is 20. So these are the first 20 elements, and these are their symbols. So atomicity is simply the number of atoms in one molecule. Very, very important. If you have this molecule S8, the atomicity is 8, because there are 8 atoms of sulfur in this very molecule. If you have this molecule P4, the atomicity is 4. So you can easily infer the atomicity by looking at the subscript, the number subscript, to the symbol of the very element. So that's where we're going to be stopping today. In subsequent classes, we're going to be moving further. Please hit the subscribe button to subscribe. Support our channel in any way that you can. Please. Thank you, and God bless you. Hello, welcome. Today we are going to be looking at particle size, mass, and quantity. Over the years, scientists have been trying to find out the size of molecules or atoms, though it is not yet still possible to, with the help of the eye, to see the size of the molecule. We know that the size of molecules or atoms are in the range of n times 10 to the power minus 7 cm, where n is actually between 0 and 10. So that is the size of molecule. between n times 10 to the power minus 7 cm in the range of, where n is in the range of 0 and 10. Now we are going to be looking at relative atomic mass and relative molecular mass. Relative atomic mass, also known as mass number, is a quantity that we are going to be using in doing several calculations in chemistry. Also, relative molecular mass, very, very important. We're also going to be using it to do lots of calculations in chemistry. Now, relative atomic mass is for elements or single elements or elements that we can easily look at on their own, whereas that of relative molecular mass is for compounds. So let's say relative atomic mass for element hydrogen, the mass number or the relative atomic mass is 1.008, whereas that of oxygen is 15.99, approximately 16. Now, what do we understand in this relative atomic mass? When we check the mass number or when we check the atomic number of hydrogen, it is 1. When we check the atomic number of oxygen, it is 8. So 8 times 2 will give us the mass number or the relative atomic mass. So mostly we are going to find out that the relative atomic masses of the elements are actually 2 times their atomic number. Take note, because the atomic mass is actually consisting of both the neutron and proton inside the nucleus. And you know that the proton has the same mass as the electron, and the electron number is actually, the mass there is actually giving us a perspective of what the relative atomic mass is. So when you add up both the mass of the proton and the neutron, you have the atomic mass. So it's actually like 2 times the atomic number. So that is what the atomic mass is, 2 times the atomic number. Roughly, not accurately, but approximately 2 times the atomic number. So if you check the last lecture where I gave the atomic numbers of the elements, so each of them, when you get to the atomic number, just do times 2 of it. It's likely that you get the mass number or the relative atomic mass. Another word for the relative atomic mass is actually mass number. So you can be seeing them interchangeably used. Now, instead of doing 2 times the atomic number to get the rough estimate of what the mass number or the relative atomic mass is, the equipment that is used to find the relative atomic mass or the relative atomic number is what we call mass spectrometer. Very, very important, mass spectrometer. So with this mass spectrometer, you can actually measure the relative atomic mass and get the actual number. And that's why you're able to get this. So these are actually got from mass spectrometer. And why we have them in fractions is that most atoms actually have isotopes. So they have isotopic forms, 2 different forms existing with the same atomic number but different molecular mass or different atomic masses. So because of that existence, we have this. And previously, the reference point for checking the relative molecular mass, it was actually hydrogen, because hydrogen has that of 1. So the ones that have, because hydrogen is the lightest element, so every other element has mass that is heavier than hydrogen. So they were all calibrated with hydrogen as the reference point. But in modern time, that we are now using mass spectrometer and observing the fact that there are isotopes, we are now using carbon as the reference point. So with those 2 into consideration, you can say that the relative atomic mass, AR, relative, R stands for relative, A is atomic mass, of an element is the number of times the average mass of one atom of that element is heavier than 1/12 the mass of one atom of carbon-12. So the relative atomic mass for hydrogen is 1.008, that of oxygen is 15.99. So you can easily say that the mass number of oxygen is actually 16. Now, the relative molecular mass, when you're talking about molecular mass, it's talking about compounds. The relative molecular mass of an element or a compound is the number of times the average mass of one molecule of it is heavier than 1/12 of mass of one atom of carbon-12. So this carbon-12 is actually the isotope of carbon that is used as the reference in these calculations and using mass spectrometer to measure. So for relative molecular mass for, say, compound calcium triazocarbonate, so if you want to calculate this now, you have Ca, the relative atomic mass for calcium is 40. So there is only one calcium, only one molecule, so you have 1 times 40. Carbon, the relative atomic mass for carbon is 12. You know the mass, the atomic number of carbon is 6. So the relative atomic mass is times 2, which is 12. But since there is only one carbon atom, we have 1 times 12. Then the relative atomic mass of oxygen is 16. As we have here, 15.99, approximately 16. But there are 3 atoms of oxygen, we have times 3. So when you multiply out and add up together, we have the relative molecular mass of calcium triazocarbonate to be 100. So that is how you do this calculation. Very, very simple. So you use this 100 in your calculation. So calcium carbonate, the relative atomic molecular mass is actually 100. So that's how you calculate relative molecular mass. You add up the individual elements that are involved for a compound. Whereas relative atomic mass, just write straight down the reading from the mass spectrometer. So these two very quantities, we are going to be using it a lot in calculating. Note, you can also hear this, some people call this relative atomic mass number. This also mass number, but in specific terms is actually the relative atomic mass, and this one relative molecular mass. Thank you. Please, if you enjoyed this video, hit the subscribe button. Support us in any way that you can. Thank you. God bless you. Welcome. Let's look at some terms that we'll be using a whole lot in chemistry. Some quantities that we're going to be using in doing some calculations. Today we're going to be looking at mole and molar mass. When you hear the term mole, what does it mean? 1 mole of a substance is the amount containing as many elementary entities as the number of atoms in exactly 12 grams of carbon-12. In the previous classes, I told us that the reference point in using the mass spectrometer to measure the masses of elements and compounds is actually carbon-12, the carbon-12 isotope. Now, 1 mole of a substance is simply the amount of that very substance containing as many elementary entities. These elementary entities could be atoms, it could be ions, it could be molecules. So 1 mole of a substance, whether it is element or compound, is the amount containing as many elementary entities as the number of atoms in exactly 12 grams of carbon-12. So what is the number of atoms in exactly 12 grams of carbon-12? The number of atoms is actually what we call Avogadro's number. So the number of atoms in 12 grams of carbon-12 is actually 6.02 times 10 to the power 23. So this is the number of atoms that is contained in 12 grams of carbon-12. So the amount containing as many entities, whether it's ions or atoms, as the number of atoms in exactly this, which is this, is actually what we call 1 mole of a substance. Now, the number of moles of a substance is actually equal to number of particles all over 6.02 times 10 to the power 23. So you come across in WAEC and JAMB, what is the quantity for the Avogadro's number? You have to have it inside your head that it is 6.02 times 10 to the power 23. So if you are told to calculate the number of moles of a substance and you're given the number of particles, just know that it is actually the number of particles all over 6.02 times 10 to the power 23. Now let's look at the molar mass of any substance. What is molar mass? Molar mass is simply the mass of 1 mole. Mass of 1 mole of that substance expressed in gram. The unit is gram per mole. So for say oxygen is 32. That's oxygen molecule is 32 gram per mole. Sodium is 23. No, sodium is a single atomic. It has one atomicity of 1. Hydrogen ion is 1 gram per mole. Calcium oxide, which is CaO, is actually 56 gram per mole. 56 because this is 40 and this is 16. So the molar mass of calcium is 40 and that of oxygen, single oxygen, is 16. So you have 40 plus 16, 56. So very, very importantly, this one is for oxygen molecule, O2, which is 16 times 2 to give us 32 gram per mole. So very, very importantly, you need to know what molar mass is so that you can, when doing calculations, you can easily use it and what 1 mole is, and you need to take note of the Avogadro's number. Thank you. Hello, welcome. Today we're going to be looking at laws of chemical combination. When elements combine, how do they combine? What are the laws that govern their combination? And today we're going to be starting with the law of conservation of mass, which states that matter is neither created nor destroyed during chemical reactions, but can change from one form to the other. So the laws of chemical combination includes laws of conservation of mass, laws of definite proportion, and law of multiple proportions, as well as the law of reciprocal proportion. So we're going to go through these 4 laws. So number 1, the law of conservation of mass states that matter is neither created nor destroyed during chemical reaction, but changes from one form to another. So in WAEC, in your JAMB or NICO, you're going to see this law stated and you're going to be asked which law is stated. Is it the law of conservation of mass or law of definite proportion or multiple or reciprocal? So whenever it is stated like this, that matter is neither created nor destroyed during chemical reaction but changes from one form to the other, know that it is the law of conservation of mass. Now, the law of definite proportion states that all pure samples of a particular chemical compound contain similar elements combined in the same proportion by mass. That is the law of definite proportion. All pure samples of a particular chemical compound contain similar elements combined in the same proportion by mass. Now we look at the law of multiple proportion. And the law of multiple proportion states that if 2 elements, A and B, combine to form more than one chemical compound, then the various masses of one element A, which combine separately with the fixed mass of the other element B, are in simple multiple ratio. This is fixed mass, please. There is mass here, I missed out on it. So please take note of these law of multiple proportion. It states that if 2 elements, A and B, combine to form more than one chemical compound, then the various masses of one element A, which combine separately with a fixed mass of the other element B, are in simple multiple ratio. So these are the 3 law of chemical combination. The last one is what we call the law of reciprocal proportion. So that is the 4th law of chemical composition, of chemical combination. And what does this law state? This law, the law of reciprocal proportion, states that the masses of several elements, A, B, and C, the law of reciprocal proportion states that the masses of several elements A, B, and C, which combines separately with a fixed mass of another element, D, are the same as or in simple ratio as in the masses in which A, B, and C combine with one another. That is the law of reciprocal proportion. So if I'm going to clean this board, I'll be able to state this. The law of reciprocal proportion states that the masses of several elements A, B, and C, which combine separately with a fixed mass of another element D are the same as or in simple ratio as the masses A, B, and C combine with one another. And that is the law of reciprocal proportion. So those 4 laws are the laws of chemical combinations. And as a student that is going to write WAEC or JAMB or NICO, you're supposed to know these laws. You're supposed to know how to state them. And you're supposed to know how to pick them out whenever they are stated. And you are told to pick out the option that rightly describes the statement that is made. Thank you. Yes, welcome back. We are going to be learning states of matter. States of what? Matter. States of matter. What do you understand by the term states of matter? The physical state in which the matter exists in. You understand? There are 3 major states of matter. We have the word solid state, the liquid state, and the word gaseous state. So those are the states of matter we have. We have the word solid, we have the word liquid, and we have the word gaseous state. So these are the 3 states of matter. How do we understand it? When we have something like ice, the ice that we get from our fridge, isn't it? The ice block. When the temperature goes up, what do we have? The ice will turn to what? Liquid water, isn't it? Then when the temperature continues to go up, then we have what? Gaseous, which is what? Which is what? Vapor. Which is what? Vapor. Which is what? Vapor. So those are the 3 states that a given matter can find in. What matter is changing from ice to liquid to vapor? What matter? Water, isn't it? Yes. Is it not water? Yes. Which is what? H2O, is it not? Yes, sir. So when it was ice, it is still H2O, isn't it? Yes. When it is liquid, it is still H2O. When it is vapor, it is still what? H2O. It's just that it is changing from different states to the what? Order. It is changing from different what? States to the what? Order. And that's what we call it states of what? Matter, the physical state. So this physical state has to be, it has something to do with the arrangement of the particles of the water. You understand? At one point, there is very less kinetic energy. Which point has very less kinetic energy? In the solid state, it has very less what? Kinetic what? Energy. So the particles are not moving. And what kind of arrangement does it have? It has a closely packed what? Particles. Is that clear? Yeah. The particles are closely packed. And this one happens at what? Low what? Temperature. So in the physical state of solid, in the solid state, The particles have what? Low temperature. There is what? Less kinetic what? Energy. And there is what? Closely packed particles. Is that clear? Then here in liquid state we have there is what we call high what? High temperature. Is it? And there is more what? More kinetic energy. Is it? And the particles are loose. They are loosely what? Packed. They are a little bit loosely packed than the solid state. But in liquid state we have very high temperature. Is it?
Yes, sir.
Very high what? Temperature. Then there is what? Even more kinetic energy than here. Is it? More kinetic energy. And the particles here do what? They are scattered. Is that clear? So that's why here we have ice, and where we have what? Liquid, and here we have what? Vapor. Is that clear? Is that clear? So these are the different states of matter, and this is what differentiates them. You understand? What differentiates the different states of matter is the what? The temperature. If the temperature is low, you expect that the particles of the solid will have what? Less kinetic energy. And because it has less kinetic energy, it will be more closely packed together. That's why we are having it in solid form. But when you increase the temperature, the particles of the matter acquire more kinetic energy and they will start moving. You understand? And they become loose. So we have what we call liquid state. When you continue to apply more temperature, the particles gain more kinetic energy and they tend to scatter. Then we have what we call the gaseous state. So what are the physical processes? What are the physical conditions or processes that cause change of state? Processes that do what? Cause change of state. Who can tell me the processes that cause change of state? Number one is what we call what? Number one is what? Melting. Melting causes change of state. Melting will cause the change of state from one state to the other state.
Solid.
From solid to what? Liquid. It is called what? Melting. That's the process. Then which other one?
From liquid to vapor.
Called what? Evaporation, or vaporization, isn't it? Vaporization. That is from what? Liquid to what? Gaseous. Vaporization. So JAMB is going to draw something like this and write A here, and they will ask you what process causes the change from liquid to gas. What's the answer? Vaporization. What other process?
Condensation.
Condensation. Condensation. What happens in condensation? From gaseous to what? Liquid. We have what? Condensation. What other process happens? This condensation can also be called what? Liquefaction. Liquid what?
Faction.
That's turning of gas into liquid. Liquefaction. That's another word for condensation. Then we have freezing. Freezing or solidification. That's when it changes from liquid to what? Solid. We have what we call what? Freezing or what? Solidification. So the opposite of melting is what? Freezing. And the opposite of vaporization is what? Condensation. Is that clear? Now what other process of that is a state change of state? Sublimation. Sublimation. We also have what? Sublimation. What is sublimation? When it changes from gaseous state, from what to what? From solid straight to what? Gas. Without changing to liquid. When it changes straight from solid to gas, we call it what? Sublimation. So those processes are what? Melting, vaporization, sublimation. We also have what? Freezing. But freezing, or you call it solidification. Then we also have what we call condensation. But condensation, which I have already explained. So we have melting, vaporization, condensation, freezing, and what? Sublimation. So those processes are processes that bring about what? Change of state. They bring about what? Change of state. Change of state. And you're supposed to know this diagram that shows from solid to what? Liquid, and liquid to what? Gaseous state. And you're supposed to know what happens in solid state. There is what? Low temperature, less kinetic energy, and closely packed particles. Here there is better or bigger temperature, higher than this, but not as high as in gaseous state. There is more kinetic energy, and there is what? It's loosely packed. The particles are loosely packed. Whereas in gaseous state, we have very high temperature or high temperature, not actually very high. But when the temperature is high enough to give it more kinetic energy in order for the particle to scatter, we have what we call gaseous state. Understand? And this can easily be explained by what? Ice, water. Water can be in form of ice at a very low temperature and less kinetic energy and closely packed state. But when you apply heat, you know that heat increases the temperature. So when you apply heat, the particles will get more kinetic energy and tend to and turn towards liquid. Then when you continue to apply heat, like you're boiling your water in the kitchen, what happens? It starts going into what? Vapor. The gaseous state. Is that clear? Yes. So that is the process of change of state. Yes, welcome. We are going to be studying the properties of matter. Properties of matter. Properties of matter. Properties of matter. Matter or substances are identified by their characteristics. Is that clear? You can identify a matter by its characteristics. And these characteristics that you identify matter by are known as the word properties. Is that clear? Any characteristic that you can identify a matter by is known as its what? Its properties. So we can say that matter can be identified by its what? Character, its characteristics. And these characteristics are called what? Properties. Is that clear? So how can you say that something is different from something? You can always identify that by the character of that thing. You understand? If this is different from this, you understand it. So these properties could be so there are two types of these properties that you can use in identifying matter. You understand? Number one, it could be what? Physical property. And number two, it could be what? Chemical property. So these are the two properties that every matter has. It could be physical or what? Chemical. What are examples of physical properties? Number one, you can talk about the what? You can talk about the what? Melting point. Melting point. You understand? The melting point of water is not the same thing as the melting point of iron. But the melting point of water is very small. But that of iron is very large. So with that you can say that this is water and this is what? Iron. If you apply heat and this one does not melt after some time, but this one melts immediately, maybe at 100 degrees Celsius, water melts or water starts boiling. But when you heat iron, even at 100, it will not even move, it will just stay like that. So you say no, this is water, this is iron, because two of them have different characteristics. So melting point is a very important aspect. Melting point. At 0 degrees Celsius, water is still trying to turn to is still ice, isn't it? Yes. But at 100 degrees, it melts towards gaseous state. So you can use melting point. You say since water melts at 100 degrees, but iron does not melt at 100. So when you test the two of them, you You can say this is iron and this is what? Water. Number 2 is what? Boiling point. Number 2 is what? Number 2 is boiling point. Number 3 is what? Density. Density, that's the weight, the mass. You understand? With respect to its volume, density. Then what other quantity? Solubility is another one. Solubility. You understand? Solubility. That's his ability to dissolve in water. You understand?
Yes, sir.
His ability to dissolve in water or any other solvent. That's solubility. You know, so sometimes they dissolve in water, but they don't dissolve in other solvents. Another, this physical property is what? Color. Color. There are some things that once you see the color, you know that this is the substance, isn't it?
Yes, sir.
Like water is colorless, isn't it?
Yes.
What other characteristics or
Odor.
Odor, the smell. There are some substances that have repugnant smell. Once you hear the smell, you just go out. But some don't have smell. Like water does not have smell. You understand?
Okay.
So whenever you see water, you can say this is water. If you get across sulfur, it has bad odor. Or ammonia, say this is ammonia. This is the smell. Then we'll talk about chemical properties. What are things that we can call chemical properties? Chemical properties. These are changes to form new what? Substances. So when matter change to form new substances, we talk about chemical properties, is it not?
Yes, sir.
And it could be in so many forms. It could be in form of reaction with one other substance, is it not?
Yes.
Good example is rusting, is it not?
Yes.
Iron, they rust in the presence of water and oxygen, isn't it?
Yes.
So other substances undergo different chemical processes, like when they react with water or the oxygen in the air, when they react with any other gas across the environment, they change. Exactly.
Yes, sir.
So will be in various forms. But very importantly, you need to identify these physical properties. You use them in testing. When you go further in chemistry, you see that you use things like boiling point, melting point to identify that this is this and this is that. But when you go into advanced chemistry, you also see that you use chemical properties to also identify. When something can react with oxygen, the degree with which it reacts with oxygen can tell you that this is this kind of compound. Is that clear? Thank you. Hello, welcome. Today we are going to be learning physical and chemical changes. Physical and chemical what?
Changes.
Physical and chemical what? Changes. Matter undergoes two types of changes. Matter undergoes how many types of changes? Two types of changes. Matter undergoes two types of changes. Number one is what we call the what? Physical change. And number two is what we call the what? Chemical change. These are the two types of change that matter can undergo. And I told you that example of matter is an ice block because it has mass and it occupies what? Space. Matter is anything that has mass and occupies what? Space. Common salt. Do you know what they call common salt? The salt you use in your house to cook, isn't it? Yes. That is matter because it has weight and occupies what? Space. So matter like ice block or common salt undergoes two types of what? Change. Iron. You know what iron is, isn't it? Yes. It's a matter, isn't it? It undergoes changes too. You understand? So any matter can either undergo a physical change or what? Chemical change. A physical change is a change from one state to the other that is reversible. Example, when ice changes from ice block to water, can it be reversed?
No.
When ice changes from ice block to water, can it be reversed?
Yes.
How can you reverse it? Putting it in the freezer, isn't it?
Yes.
It will get back to ice, isn't it?
Yes.
So it is reversible. So therefore, what kind of change is that? Physical. Whenever there is a change from one state, in ice block, what state is it in? Solid state. It changes to water. Water is in what state? Liquid state. Whenever there is a change in state, we call it a what? Physical change. Because it is what? Reversible. Is that clear?
Yes.
So physical change, this is a reversible what? Change from one state back to another, isn't it? Isn't it?
Yes.
You can also say that it is a temporary change. Is that clear? Example is the solution of what? Of common salt in water. You understand?
Yes.
If you carry common salt and put in water, it will dissolve. But when you carry it and leave it under the sun, the water will evaporate and you still see your common salt back, isn't it?
Yes.
Number 2 example is ice block changing to what? Water, isn't it?
Yes.
So this is another type of a physical change. Is that clear?
Yes.
Is that clear?
Yes.
Another example is heating of what?
Sulfur.
Heating of sulfur
In the absence.
in the what?
Absence of air.
Absence of
Air.
air. Heating of sulfur in the absence of air is another example of what? Physical change. So physical change is the reversible change from one state to another that is temporary. Example, dissolution of common salt in water, heating of sulfur in the absence of air, ice block melting to what? Water. Is that clear? Now, what is chemical change? This is an irreversible change. Chemical change is what? Irreversible. In which new substance is what? Formed. In which a new substance is formed, or in which new substances are formed. You understand?
Yes.
In physical change, no new substance is formed, but in chemical change, new substances are formed. Is that clear?
Yes.
Is that clear? Example is what? Dissolution of what? Dissolution of metal sodium in what? Water. What is the chemical reaction? Na plus what? H2O. To give us what? Sodium what? Hydroxide plus what? Hydrogen that is given up. Is that clear?
Yes, sir.
Is that clear?
Yes.
To balance the equation. So dissolution of sodium in water is an example of what? Chemical reaction. Because when sodium reacts with water, it forms sodium hydroxide. Is that clear? This is a totally new substance, different from what we have here. So this is a what? Chemical reaction. And then is going to ask you, which of the following reactions or which of the following changes is a chemical change? It would write dissolution of common salt in water, melting of ice block to water, heating of sulfur in the absence of air, dissolution of sodium in water. Which one is a chemical change? Dissolution of sodium in water. What other example of chemical change do we have? What? Burning of what? Magnesium. Bonding of magnesium is a what? Chemical change. Bonding of magnesium is a what? Chemical change. Because when magnesium bonds in air, it gives what we call magnesium oxide. It gives what we call what? Magnesium what? Oxide. Is that clear?
Yes, sir.
Is that clear? So this is what we have. Magnesium metal burning in oxygen gas to give us magnesium what? Oxide. Is that clear? So this is another example of a what? Chemical change. So then we will ask you, which of the following is a physical change? They will write burning of magnesium in air, dissolution of sodium in water, melting of ice block. Which one is a physical change? Melting of ice block. You're supposed to know it. Very important. The two types of changes that matter undergo are what? Physical change or what? Chemical change. In physical change, it is reversible and it simply changes state from one state to another. But in chemical change, new substances are formed. Is that clear? Now we are going to tabulate the differences between physical and what? Between physical and what? We are going to tabulate it so that it's easier to understand. So we say difference between physical and what? Chemical change. So what are the differences between physical and chemical changes? Here we have what? Physical what? Change. And here we have what? Chemical what? Change. So who can tell me one difference between a physical change and chemical change? Physical change, it is easily reversible. Physical changes are easily reversible, isn't it?
Yes.
What of chemical change?
It's not
It is not easily what? Reversible. Who can give me another?
new substance are not formed.
In physical change, no new substance is formed. But in chemical change is what? New substance is formed. Or new substances are formed. Is that clear?
Yes.
Then what other change the difference? In physical change, very what? Little amount of heat is what? Is absorbed or evolved or emitted, isn't it?
Yes.
Whereas here, what happens? Remarkable what?
Heat change.
Remarkable heat change. So whenever a physical change is taking place, there is little or more, very little amount of heat given off or taken in. Is that clear?
Yes.
But in chemical reaction or in chemical changes, there is large amount of heat either given out or absorbed. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
What other change?
Change in mass.
No what?
Change in mass.
Change in mass. No change in mass. There is no change in mass in physical change. But in chemical change, what happens?
A new substance has different masses.
Here, new substance always has different what? Masses. So new substances always have different masses. Is that clear?
Yes, sir.
When you dissolve when a block of ice dissolves, the mass of that block of ice will still be the same thing as the mass of water that is formed, isn't it?
Yes.
There is no difference in their masses. But once there is a chemical reaction, or chemical change, there is difference in mass between the reactant and the what? Product. Difference in mass between the reactant and the what? Product. So that's why there is always change in mass for chemical change, but there is no change in mass for physical change. Little amount of energy is either given out or absorbed, but here remarkable amount of it, that's large amount of it. Here there is no new substances formed in physical change. In chemical change there are new substances formed. In physical change it is easily what? Reversible. But chemical changes are not easily reversible. Is that clear? Is that clear? Yes, today we are going to be learning about the modifications of Dalton's atomic theory. Modifications of what? Dalton's atomic theory. Like I told us before, Dalton's atomic theory, due to recent developments in science, most of those statements of Dalton's atomic theory are no longer true. Is that clear? The number one statement of Dalton's atomic theory is that what? Matter is made up of small indivisible particles known as atoms. Small indivisible. You understand? He's saying that atoms cannot be divided. But in recent discovery, due to nuclear reactions, due to what? Nuclear reactions, we find out that atoms are divisible. Is that not true? Atoms are what? Divisible, because uranium can split into thorium and helium. Because what? Uranium can split into thorium and what? Helium. Is that clear? So atom of uranium can split into thorium and what? Helium. So that makes that first statement to be false. That makes that first statement to be what? False. To be what? False. 283. That's the mass number of uranium. And the atomic number is what? 92. The atomic number is what? 92. The mass number is 283. So the mass number of thorium is what? 234. Is what? 234. And the atomic number is what? 2. And the atomic number is what? 2. This is 4. And this is what? 0. This one is 238, not 283. 238. You see that? The mass number here is 238, which is the division of this. If you add this together, you get this. If you add this together, you do what? You get this. So you see, an atom of uranium can split into thorium and what? Helium. So atoms are actually divisible. You understand? So that modifies the first statement of Dalton's atomic theory that says that matter are made up of small indivisible particles called what? Atoms. So in essence, atoms are actually divisible when nuclear reactions do what? Occur. The second statement says that matter can neither be created nor destroyed. Is it not what it said? Yes. But we'll find out that there are some energy changes that could happen. Is that clear? There are some energy changes that could happen where matter or atom can be what? Destroyed. Can be what? Destroyed. Is that clear? Yes. So in some instances there could be some energy changes that could consume matter. Is that clear? That you could consume matter and liberate energy. And liberate what? Energy. And you call it exothermic processes. Processes that can give out energy and consume matter. So that makes that second statement to be also what? False or modified. Then the third statement says that atoms of the same elements are what? Exactly alike and different from atoms of other elements. And now, with the advent of the technology or the knowledge of isotopy, what is isotopy? When we have atoms of an element having different numbers, different mass numbers, you understand? So that means they are not actually the same. Example is chlorine. There are various forms of chlorine that have different mass numbers, you understand? The same atomic number but different mass number. So the Phenomenon of isotopy makes the third statement to not be exactly true. Is that clear? Now, fourthly, we have chemical compounds. We are assumed to come out from simple proportion reactions. Is that clear? But in recent understanding, we find out that in organic reaction, in what? Organic reactions or organic compounds, in organic compounds, we find out that atoms don't actually combine in simple proportions. Is that clear? They don't actually combine in simple proportions as proposed by Dalton's atomic theory. Is that clear? So with these modifications, it's good that you know that matter is made up of small particles known as atoms. But it's not actually true that these atoms, that all these atoms cannot split. Some of them can actually split. Like in the case of uranium, they are split into thorium and what? Helium. You understand? We say that atoms can neither be created nor destroyed, but not in all cases. You understand? In extra cases, you see that some energy can be liberated and matter consumed. Is that clear? In further lessons, we also learn about the law of relativity and other laws that prove this. Then the third statement that says that atoms of every similar element is exactly the same. The phenomenon of isotopy proves that one wrong, isn't it? Now we also have organic reaction taking place in non-simple proportion manner. Is that clear? Proving the fourth statement to also not be exactly true. Is that clear? Good. Yes, welcome. Today we are going to be learning about atomic structure. Today we are going to be learning what? Atomic structure. How is the atom arranged? How are the electrons, the protons and the neutrons, how are they arranged in an atom? If you say that this is an atom, how many electrons do you have?
One.
Surrounding the what? Nucleus. Surrounding the what? Nucleus. The nucleus is made up of protons and what? Neutrons. Made up of what? Protons and what? Neutrons. With electron doing what? Revolving around it. With electron doing what? Revolving around it. That is the structure of what? An atom. That is the structure of an what? Atom. Every atom, whether it is atom of sodium, oxygen, fluorine, you understand? Chlorine, all of them have a nucleus at the center. Then electrons doing what? Revolving around it. Is that clear? That is the structure of what? An atom. And that is what we call what? Atomic structure. What is atomic structure? It consists of a centrally placed what? Nucleus. Centrally placed what? Nucleus. This is the what? Nucleus is centrally placed, is on the center. You understand? And this nucleus contains what? Protons and what? Neutrons. It contains what? Protons and what? Neutrons. Which is what? Surrounded by a cloud of what? Electron. By a cloud of what? Electron. Is that clear? So every single atom of any element must have these three things. Must have this what? Three things. Number one is what? Proton. Number one is what? And this proton has a mass of what? 1. And an electrical charge of what? +1. Electrical charge of what? +1. So where is the proton found in this atom? Where?
Inside the
nucleus. Inside the nucleus at the center. Is that clear? Yes. Then secondly, it must have a what? Neutron. And this neutron has a mass of what? 1. And has a charge of what? No charge. Neutron is also inside the what? Nucleus. Then you now have electron having a charge, a mass of 1/1840. Is that clear? And a charge of what? -1. So if you say that every atom has equal number of electron and what? Proton. Let's say this one has how many electrons now? 1. This one must have a proton of what number? 1. Is that clear? Yes. So because this is to ensure the electrical neutrality of an atom, because this one is minus, but yes. Electrons are what? Minus. Protons are what? Plus. So when there is -1 here and +1, it will be what? Neutral. It will be what? Neutral. If this atom has the atomic number of 5 and there is 5 proton here and also 5 electron here, what will be the charge? It will also be what? Neutral, because 5 cancels what? 5. 5 positive and 5 what? Negative. Is that clear? Yes. So the phenomenon that ensures that there is the same number of electron and what? Proton ensures the what? Neutrality of the what? Atom. That's why every atom is what? Neutral. You understand? Because it has equal numbers of what? Electron and what? Proton. So the proton is having plus. If the atomic number is 20, the proton will be having what? Plus what? 20. If and the electron will be having minus what? 20. Minus 20 cancel plus 20 makes the atom to be what? Neutral. Is that clear? Yes. Is that clear? Yes. Now, the first shell is known as the what? K shell. The first shell is known as the what? K shell. Always have it in mind as we go forward. Is that clear? Yes. Can we go forward? Yes. I hope it's very clear. Yes. So whenever you talk about atomic structure, you are talking about the what? You are talking about a neutral atom that has a nucleus of a positive nucleus. You understand? And an electron crown that has negative charge. Is that clear? Yes. Now let's talk about the electron distribution. Let's talk about the what? Electron distribution. How the electrons are distributed. How the electrons are what? Distributed. Yes, welcome. So we learned that atomic structure is all about the way the atom is arranged, isn't it? The way the atom is arranged in the form that the electrons form cloud round the what? Nucleus. Round the what? Nucleus. And we know that the nucleus is made up of the proton and the what? Neutron. Proton and the what? Neutron make up the what? Nucleus. Whereas the outside, you have what revolving around the nucleus? What? Electrons. So how are these electrons arranged? These electrons that revolve around. That's what we'll learn when we talk about what? Electron what? Distribution. How are these electrons distributed around the what? Nucleus. Is that clear? You know it's not only one electron that is always moving about. One is for when you are considering hydrogen, because hydrogen has an atomic number of what? 1. What if we are talking about things like oxygen that has up to 8? We're talking about chlorine, sodium. You understand? How will you arrange the electrons? You understand? The number of electrons is similar to the number of the what? Atomic number of the very what? Element. Is that clear? So now we have electronic configuration is the way electrons are what? Arranged outside and around the what? Nucleus. You know that the electrons are always around the nucleus. They are revolving around. So the way they are arranged is known as what? Electronic what? Configuration. Is that clear? So how they are arranged outside and around the nucleus of our what? Atom. They are arranged in orbits called shells. They are arranged in orbits called what? Shells. I drew it for you. Isn't it? So when you have something like this, when you have an atom with a what? This is what? Nucleus. And this nucleus is made up of what? Proton and what? Neutron. Isn't it? Then revolving around is what? Electrons. You understand? So these electrons revolve in what we call what? Shells. In what we call what? Shells. This circular thing is known as what? Shells or orbits. Is that clear? And there are what? 7 shells. Is that clear? Yeah. 7 shells. Number 1 shell is known as the what? K shell. After the K, when the K, the first one fills up, then we'll see the what? Second what? Shell. And the second shell is known as what? L. When L fills up, you have also another one known as what? N. N, O, P to what? Q. Is that clear? Now, the first shell is the K shell. It has the lowest what? Energy. It has the lowest what? Energy. When you're talking about the energy configuration, you find out that the K shell has the lowest what? Energy. The K shell has the lowest what? Energy. And it also has the least number of maximum electrons. The maximum electron in the K shell is how many? 2. Is how many? 2. But the maximum in the other cell is up to what? 8. Is that clear? Yeah. So the K shell can only have only 2 electrons. Only what? 1 and 2. But here you can have 1, 2, 3, 4, 5, 6, 7, what? 8. That's the maximum for the K shell. Is that clear? Yes. But the maximum for the L shell is what? For the K shell is what? 2. Whereas the maximum for the L shell is what? 8. Is that clear? Is that clear? Yes, sir. Are we together on that? Yes. Now we're going to look at some critical aspects of this electronic configuration. Critical aspects of what? The electronic configuration. To calculate the maximum number of electron in an orbit or shell. To calculate the maximum number of electron in a shell, we use the formula. It might come out in JAMB. It might ask you to calculate the maximum number of electrons. You understand? Yes. You use the formula 2n to power what? 2. The formula what? 2n to power 2. Where n is the number of energy level of the shell. Where n is what? The number of the energy level of the shell. So we have that where n is equal to 2, comma, which is for what? L shell. Then the maximum number of electrons will be what? What will be the maximum number of electrons? It will be what? 2 bracket 2 to power what? 2. 2 to power 2 is what? 4. 2 times 4 is what? 8. So the maximum number of electrons for L shell is what? 8. So how do you know the n for each of them? How do you know the n for each of them? You know the n by saying this is shell. Is that clear? The n is what? The energy. If we have here K and we have here L, we have here what? M, we have N, we have O, P, and we have what? Q. What is the energy level for K is what? 1. For L is what? For M is what? For N is what? For O is what? For P is what? For Q is what? 7. We have 7 shells, you understand? The energy levels are 1, 2, 3 down. Is that clear? Yes. And the energy level represent their what? N. Represent their what? N. So, how do you know the what? Maximum number of what? Electrons. What's the maximum number of electrons? For this one, the formula is what? 2 bracket what? 2 bracket, no, this one is what? 1, 2. 1 squared is 1, 1 times 2, 2. This one will be what? 2 bracket 2, 2. What will be the answer? 8. 2 squared is 4, 4 times 2, 8. This one will be what? 2 bracket what? 3 squared. 3 squared is 9, 9 times 2, 18. For this one, it will be what? 2 bracket 4 squared. 4 squared was what? 16, 16 times 2, 32. Just like that down. Is that clear? Yes. So I want you to do the rest by yourself. Do for shell OPQ. Tell me the maximum number of electrons that can be found on the shell. Is that clear?
Yes.
So that is how you solve. How do you get the maximum number of electrons? By using the formula 2n squared. That's what we use here. Is that not clear?
Yes, sir.
So anywhere we see n, we replace it with the what? The energy level, which is 1, 2 to 7, according to the number of shells. Is that clear?
Yes, sir.
Thank you. Yes, welcome. Today we are going to be learning about atomic number and what? Mass number. Atomic number and what? Mass number. What differentiates hydrogen from helium, oxygen, or sodium is the number of what? Electrons, the atomic number. You understand? Or their mass number. Every element, every atom of any element have different atomic and mass number from the other one. Is that clear?
Yes.
So when you have the periodic table, you know the periodic table is where we have the collection of all the elements, isn't it?
Yes.
Both metals, non-metals, and metalloids. Is that clear?
Yes,
What differentiates all the elements inside the periodic table is their atomic numbers. Is their what? Atomic number. So it serves as the identity of the atom. It serves as the identity of the elements. Is that clear?
Yes.
The atomic number serves as the what? Identity. That's how you know this is this. If they tell you that an element is having atomic number of 1, definitely you know that that element is what? Hydrogen. You know that that element is what? Hydrogen. If it has an atomic number of 8, you understand? You know that it is what? Oxygen. So we are going to learn how to identify elements by their atomic number. Is that clear? But what is this atomic number we are talking about? Atomic number represented by the letter what? Z. Is the number of what? Protons. Number of what? Protons in the nucleus of an what? Atom. Number of what? Protons in the nucleus of one what? Atom. And we told us that the number of protons is always equal to the number of what? Number of what? Electrons. Number of protons, which is inside the nucleus, is always equal to the number of what? Electrons. So if we say that a given element has 20 protons, it also means that it has how many electrons? 20. In order to make that atom to be what? Neutral. In order to make it to be what? Neutral. So atomic number is the number of what? Protons in the nucleus of an what? Atom. It increases by 1 in the what? Periodic what? Table. You need to know and understand the what? Periodic table. It's very, very important. Is that clear? Number 2 is what? Mass number. Represented by the letter what? A. And it is the what? The sum of the what? Proton and what? Neutron in the atom of a what? Element. You know that the protons and neutrons are contained in the what? Protons and neutrons are contained in the what? Nucleus of element. So the total sum of the number of proton and the neutron in that nucleus is known as what? Mass number. Is that clear?
Yes, sir.
Example, when we have sodium, sodium has a mass number of what? 23. That means that the total number of proton and neutron in the nucleus of sodium atom is what? 23. But sodium has the atomic number of what? 11, because that is the number of what? Proton. Is that clear?
Yes, sir.
So this is the what? Atomic number, whereas the one up is the what? Mass number. The one down is the what? Atomic number. The one up is what? Mass number. You find that the mass number is always mostly 2 times the what? Atomic number. Is that clear?
Yes.
Almost 2 times, approximately 2 times. Can you see magnesium?
Yes.
The atomic number is what? The atomic number of magnesium is what? 12. And the mass number is what?
24.
So if X is an element, is that clear? The atomic number is represented by Z, atomic number, whereas A is the what? Mass number. The one up is always the mass number, the one down is always the what? So the one up is the what? Mass number, which is the number of what? Proton and what? Neutron. And the one down is the number of what? Proton. So number of proton and neutron minus number of proton will give you number of what? Neutrons. Is that clear? So if you are given the mass number of an element and the atomic number, you are told to find the number of neutron. How do you do it? Mass number minus the what? Atomic number. If you are given an atomic number and you are told to find the number of electrons, how do you find the number of electrons? If you are given the atomic number.
Mass number plus.
Once you are given atomic number is also the number of electrons. Because the number of electrons is always equal to the number of protons. Is that clear?
Yes.
If you are given atomic number and you are told to find the number of protons, what will be the number of protons? It's the same thing, because atomic number is simply the number of what? Proton. It's also the number of what? Electron. Because every atom is electrically neutral. Is that clear?
Yes.
But the neutron number is the mass number minus what? Atomic number. Because the nucleus is made up of the neutron and the what? Proton. So if you are given the mass number, which is the number of both neutron and proton, and you are not told to find the number of neutron alone, you just do atomic mass number minus what? Atomic number. Is that clear?
Yes.
Yes, welcome. We are going to be learning how to fill the electrons in the shells. How to fill the what? Electrons in the shells. We say that the atom of an element is made up of the centrally placed nucleus surrounded by the what? Electrons revolving around the shells. So how do you fill in these shells? When you talk about an element that has atomic number of 1, that means it's at how many number of electrons? 1 revolving. But if it has atomic number of 20, it has up to what? 20 electrons. How are these electrons arranged around the cell? Now find out that in filling the electrons in the shells, we formally say that we use the formula 2n squared. You understand? The first shell is known as the K shell. And the K shell has how many? What is the maximum number of electrons for the K shell? Is 2 bracket 1 squared, which is what? 2. So the maximum number of electrons in the first K shell is what? 2. After K you have the what? L. And the L, the end for L is what? 2. The maximum here is what? 8. So the next one, which is L, the maximum number of electrons is what? 8. The next one is what? M. M will be what? Here we use what? 3. So it will give what? 18. But here we are saying that in filling the electron shell, the use of this formula is only applied to the what? First and what? Second shell. That's the K and the what? L shell. The K and what? L shell. Which will make the maximum for K to be 2, maximum for L to be what? 8. If you use this formula for M and N, it will give 18 and what? 32. But we now say that in using this formula, it applies to only the first and what? Second shell of the first 20 elements. For the first contains 2 electrons and the second contains how many? 8 electrons. Subsequent shells, that is the third and the fourth. You know the third and the fourth shell is the M and what? N shell. Subsequent shells, which is the third and fourth or other ones, can only hold a maximum of what? 8. And not 18 or what? That's 2. It still holds only what? 8. Why? This is due to the presence of subdivisions of shell called orbitals. Subdivisions of cells called what? Orbitals. Apart from the normal shell or the orbit, you also have other divisions of shells known as what? Orbitals. Known as what? Orbitals. And there are 4 of them. You have the what? SPD what? F. SPD what? F orbital. The K contains only 1 S orbital. Is that clear? The first one, which is K shell, contains only 1 S orbital. Whereas the L, which is the second one, contains S and what? P orbital. M contains what? S, P and what? D orbitals. Whereas N orbit or shell contains S, P, D, F what? Orbital. Each orbital has a maximum number of electrons it can what? Hold. Is that clear? Every orbital has a maximum number of electrons it can hold. S can only hold what? 2. P can only hold what? 6. D can only hold what? 10. F can only hold what? 14 electrons. Is that clear?
Yes.
Is that clear? Now we're going to learn about how these electrons are held in these orbitals. How are these electrons held in these orbitals? How do we do this? We'll talk about the shell. Who can tell me the shells that we have?
K.
Good. K what? L, M, N. Down to Q. Isn't it?
Yes.
Now, what are the shell numbers or the energies? For K is what? 1. L is what?
2.
M is what? 3. N is what? 4. Is that clear?
Yes.
What are the orbital types? What are the orbital types for K? What kind of orbital does it have? It has S, is it not? 1S. L has what? SP. S and P. Because it's 2 here, you put 2S and 2 what? P. M has what? SP what? D. Because it's 3, we will put what? 3. N has what? S, P, D, F. Because it's 4 here, you put what?
4.
Is that clear?
Yes.
Those are the what? Orbitals. Is that clear?
Yes.
Filling style. Filling style. How is it filled? You understand?
Yes.
First of all, you have to fill the what? K. After the K, you fill the what? L. After the L, you fill the what? M. After the M, you fill the what? N. Is that clear? You fill the K shell. After the K, you fill the what? L shell. After the L, M. After the M, what? N. Is that clear? So if you have here S and you have 2S, 2 what? P. And you have what? 3S, 3P and 3 what? D. And we have what? 4S, 4P and 4D and what? 4F. Is that clear?
Yes, sir.
How do you feel? First of all, you feel the 1S first in the K shell. Is that clear?
Yes.
After that, you feel the what? 2X. Is that clear?
Yes.
After filling the 2S, you now feel what? 2P and what? 3S. Is that clear?
Yes.
After filling 2P and 3S, you feel what?
3P and
3P and what? 4S. After filling 3P and 4S, you feel what?
3D, 4.
3D and what? 4P. After filling that one, you now feel what? 4D and you now feel what? 4F. Do you see the way you feel?
Yes, sir.
You feel according to, first of all, you must put S. You put 2S. You feel what? 2P. You feel what? 3S. 3P. 4S. 3D. 4P. 4D and 4 what? F. Is that clear?
Yes.
That is how you feel. And you know that when you're filling 1S, what is the maximum number of electrons for 1S? 2. 2S, what's the maximum number of electrons? 2. P, what's the maximum number of electrons? 6. P here is 6. D here is what? 10. F is what? 14. Is that clear?
Yes.
So we're going to try filling this electron by using the first 20 elements. By using the what? First 20 elements. We're going to experiment this by using the first 20 elements. By using the first 20 elements. Yes, welcome. Today we are going to be learning about valency radicals and oxidation number. Valency radicals and what? Oxidation number. Previously we learned about the first 20 elements. We learned about the what? First 20 elements. And we said that in learning the first 20 elements, there are 3 things that are important. Number 1 is mastering the first 20 elements that are in the periodic table. Number 2 is knowing the atomic numbers. And number 3 is knowing their mass numbers. Is that clear?
Yes.
So those are the 3 things you took notes in when you learned the first 20 elements. Now you can be able to easily tell me the atomic number of hydrogen or what? Oxygen. You understand? Now, your knowledge of atomic number of the first 20 elements gives you the ability to easily know the valency of each of the what element, of each of the what elements. You can also deduce the oxidation number of such elements, and that is what we are going to learn today. How to, from your knowledge of the atomic numbers of the first 20 elements, deduce their valencies and what? Oxidation number. Deduce their valencies and what?
Oxidation number.
Now, what is valency? Valency is the combining power of any what? Element. You understand?
Yeah.
The ability of the element to combine with another element. Is that clear? In reactions, chemical combinations for metals are done by giving out electrons. They are done by what? Giving out electrons. Whereas that of non-metals are done by accepting electrons. They are done by what? When an element gives us an electron, it makes it to have a positive valency. It makes it to have a what? Positive valency. But when an element receives, it makes it to have a what? Negative valency. Now, you find out that if there is only one electron on the outermost shell of an element, it's easier for that element to just give out that one, is it not? Yes. So it will combine faster than the one that a metal that has two, because it needs extra energy to release the two. But if it's having only one, it can easily release the one. Is that clear? So those people having one electron on the outermost shell are said to be having valency of what? One. If the metal has two to give out, it has valency of what? Two. So which one has more combining power? One. The one that has one, because it can easily give out one and combine. That's why we say valency is the combining power of what? Element. If it has two, it will take it more energy. It will have to give out one, then give out the other one. You understand? And that's why potassium and sodium, they have very high combining power. They can easily combine. Is that clear? The same thing happens to non-metals. If a non-metal needs just one electron to complete its octet, is that clear? It has more combining power, like chlorine and fluorine. They are very reactive. The ones that have higher combining power are always very what? Reactive. Sodium and potassium are very reactive, and also chlorine and fluorine. So we say that valency is the combining power of elements. It is the property of atomic structure. It is the property of what? And we say that the atomic structure is simply the way the electrons revolve around the what? Nucleus. Is it not? Yes. So this valency is the property of atomic structure. Metals have positive what? Valency. I said it. Why do they have positive valency? They give out electron. Why non-metals have what? Negative valency. Why? Because they accept electrons. Stable valency is 8. Stable valency is what? 8. Whenever the number of electrons on the outermost shell in the electronic configuration of any element is 8, then it is what? Stable. It will not react. Who can give me an example of metals that have 8 electrons on their outermost shell? Neon. Neon has what? 8. Another example is what? Argon. They are called noble gases. All the noble gases, they have 8 electrons on the outermost shell, so they don't react. They are stable. You see them in free state like that. Now, you can also say that valency is the number of electrons needed to give out, needed or given out to make atom to have a stable 8 outer electron. Is that clear? Yes. So that number of electrons that you can give out or accept to make you to be stable 8, to make you to be stable 8 is what? Is your valency. Is your what? Valency. That number of electrons that you need to give out. Like sodium, how many electrons does sodium need to give out to react to have 8 stable octet? 1. Calcium needs what? 2. Is that clear? Example is sodium. Sodium has valency of 1, and oxygen has valency of what? 2. So we are going to specify how is it that sodium has a valency of 1. How can you say that volume of sodium has valency of 1? How can you deduce the valency of elements? Is that clear?
Yes.
Now we are looking at what? Which element are we looking at? Sodium. What's the formula for what's the symbol for sodium? Na, isn't it?
Yes.
Now, how do we know the valency of sodium? I told you us that how we know the valencies is by our initial knowledge of the first 20 elements. In the first 20 elements, what is the atomic number of sodium? Check your what you just drew. What is the atomic number of sodium?
11.
11. Is there on your saying you have it in your notes? The atomic number of sodium is what?
11.
Atomic number of sodium is what? 11. So from this you can say the valency. How do you deduce the valency from the atomic number? You draw the shells, isn't it? So you draw. This is the nucleus, is it not?
Yes.
The first shell has only 2 electrons. Has only what?
2 electrons.
So you have 1 and what? 2. Isn't it?
Yes.
The second one has how many?
8.
8. So you are looking at how many here? 11. So you have 1, 2, 3, 4, 5, 6, 7, 8. But 9, 10. This one has completed 8, but so you draw another one. Then what? 11. Is that clear? The first shell must have only what? 2. The second can have what?
8.
The third can have what? 8. All of them can be having 8. You understand? So always make sure that you fill in the first shell to be only 2 electrons. But with the subsequent one, you can fill up to 8. You understand? Until you arrive at the number of the atomic number of the specified what? Elements. Is that clear?
Yes.
So the specified element has atomic number of what? 11. So we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You understand?
Yes.
And we say that the valency is the number of electrons on the outermost what? Shell. What is the number of electrons on the outermost shell? 1. So the valency of sodium is what? 1. Is that clear?
Yes.
Did we see how we made the valency of electron to be of sodium to be 1? Did we see it?
Yes.
Now we're going to take another element. What other metal element can we take? Let's take another metal element. Meanwhile, the oxidation number is also most likely that one. Is that clear?
Yes.
It's most likely the valency as well. So now let's talk about calcium. Let's talk about what? Calcium. What is the atomic number of calcium?
20.
Atomic number is what? 20. But?
Yes.
Good. Now let's draw the shells for what? The electronic configuration for calcium. This is the what? Nucleus, isn't it?
Yes.
The first shell has what? 1, 2. But?
Yes.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Is it complete?
Yes.
Because the atomic number is what?
20.
So what is the valency of calcium?
2.
What is the valency? 2. The valency is equal to 2. Why? Because there are 2 electrons on the outermost what? Shell. Is that clear?
Yes, sir.
Can you see how you can deduce the valency from the what? Atomic number by drawing the electronic configuration in the shell. Isn't it?
Yes, sir.
Is that clear?
Yes, sir.
Now we are going to take up this one is about the metals. Let's take an instance of a non-metal. An instance of a what? Non-metal. Let's talk about fluorine. Let's talk about what?
Fluorine.
Fluorine. What is the atomic number of fluorine?
9.
9. Isn't it?
Yes.
Now let's draw this electronic configuration. The first one is the what? Nucleus, ba? Then we have 1, 2, then what? 3, 4, 5, 6, 7, 8, 9. Can you see? The outer electron has how many? It has 7, isn't it?
Yes.
But we don't call the valency 7 because it's a non-metal. We say how many electrons do we need to make the outer electron 8? How many? 1. So the valency of fluorine is what? -1. Is that clear?
Yes.
Can we see that?
Yes.
Now let's talk about another non-metal known as chlorine. What is the atomic number of chlorine?
17.
17, isn't it? So we draw chlorine. We have 1, 2, back. Then we have what? 3, 4, 5, 6, 7, 8, 9, 10, isn't it? 11, 12, 13, 14, 15, 16, 17. So what is the atomic, what is the valency?
-1.
Still minus what?
1.
1. Can you see it?
Yes, sir.
So it's either the number that needed to make it update or the number he removes to get stable. Is that clear?
Yes.
Is that clear?
Yes, sir.
Good. So we say that, yeah, welcome. We say that valency is the what? Combining what? Power. So it's actually the power that elements use in combining, isn't it?
Yes.
Now we look at sodium oxide. Is that clear?
Yes.
Where we have sodium combining with what? Oxygen. So let's draw for sodium. Sodium, what's the atomic number for sodium?
Yes.
11 bar.
Yes.
So we'll draw for sodium. This is the nucleus. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bar.
Yes.
Then we have what again?
11.
11. So the combining power of sodium is what? 1. Isn't it?
Yes.
Now, if sodium wants to react with oxygen, what's the distance for oxygen? 8 bar.
Yes.
So let's say this is sodium. Isn't it? This is sodium. Now oxygen is how many? 8. How many? 8. So this is the nucleus of oxygen. Then we have what? 1, 2, 3, 4, 5, 6, 7, what? 8. So this is what? Oxygen, is it not?
Yes.
So if this oxygen wants to react with this sodium, will it be stable? If this one release 1, if you release this one now, it goes here, so it will make this one to be, let's say this is this one is here, 1 is here, so we will now have what? 2, back.
Yes.
So this one will now be how many? No, let's say this is 1 here, and this is 1 here. Then this one releases this only one that he has. Give it to this man, this one will now have how many? 7. It's not still 8.
Yes.
But this one is already stable because it's now 8. So it needs another sodium again. So this is the sodium nucleus. Then we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and what? 11. Isn't it? So this one will also need to release its own what? Electron. So this one will now become what? Stable. And that electron will now what? Come here. And this one will now be what? Stable. Because it's now 8, isn't it?
Yes.
So we're now having, how many sodium do we have? 2 sodium and what? 1 what? Oxygen. So if you want to write the formula, you have Na what? 2O. Can you see that? Can you see that? So for any element to be stable, the outer electron has to be what? 8. So you see that the extra one here that made this one 11 plus the extra one here that made this one 11 was released for this one to complete.
Yes.
Is it not?
Yes.
This is the normal diagram. Is it not the normal diagram?
Yes.
This is for 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is what? 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is what? 8. 1, 2, 3, 4, 5, 6, 7, 8. You understand? But this is not, none of them is stable. You understand?
Yes.
So this one has to release this valency to make this one what? Stable. Then this one releases valency to make this one stable. Therefore forming sodium what? Oxide. Is that clear?
Yes, sir.
So that's why we say valency is the what? Combining what? Power. Now let's look at another example. If we have water, how is water formed? Water is formed from what and what? Hydrogen and what? Oxygen. Water is H2O. So how do you get that H2O? Now, oxygen is how many? What's the atomic number? 8. So you have oxygen, you have the nucleus, then you have 1, 2, 3, 4, 5, 6, 7, 8. Back? Then hydrogen is what? 1 back? So the nucleus and what? 1. Now, if this hydrogen release this only one electron, it goes here, it will make it to be what? Stable, but but will it be enough to make this one stable?
No.
This one needs how many? 2. You understand?
Yes.
And because it needs 2, that's why the valency is -2, is it not?
Yes.
Valency of this one is what? 1. So it will need another what? Hydrogen of valency plus 1 to make it stable, is it not?
Yes.
So this one now will release this for this. This one will release this for what? This. So that's why this can be written as what? H what? 2O. Because there are 2 H and 1 O. Is that clear?
Yes.
Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
So as a way of example for assignment, okay, let's stop here for now. But did we understand it?
Yes.
Good. Yes, welcome. We are going to be learning about the radicals. Today we said we are going to be learning about the valence radicals and what? Oxidation number, isn't it?
Yes.
Now, like I said before, the knowledge of the first 20 elements and the atomic number, with that you can solve a lot of problems in chemistry calculations. Is that clear?
Yes, sir.
The radicals are group of atoms which behave as one unit. Radicals are what? Group of atoms which behave as what? One unit. Is that clear? And it could also be called a charged atom. It could also be called a what? Charged atom. Atom that has charge. We have cations which are positively charged what? Metals. I told us that metals normally give out electron when they want to react. Is that clear?
Yes.
So when they want to react and they give out electron, they become positively charged. They become what? Positively charged. And they are called what? Cations. They are called what? Cations. Is that clear?
But the spelling was something.
Which one?
Cation.
It's correct. C-A-T-I-O-N-S. Isn't it?
Cation.
Cations.
Okay.
Isn't it?
Yeah.
Now, when you have what? Non-metals, when they want to react, they do what? They receive electrons. And whenever an element receives an electron, it becomes what? Negatively charged. So non-metals that are negatively charged are known as what? Anions. Anions. Is that clear?
Yes.
Metals are cations because they are positively charged. Non-metals are what? Anions. The oxidation state of radicals is also their what? Valency. It's also their what? Valency. We've already learned about valency, isn't it?
Yes.
The number of electrons in the atmosphere. needed to be released for there to be combination, or needed to be what? Accepted for there to be combination. For non-metals. For metals is the give out, isn't it?
Yes.
Now, radicals, like I told us, is charged atom. Atom that has charge, positive or what? Negative charge. What is the valency of potassium? Is 1, but now the oxidation state of potassium is what? +1. Can you see? So you can easily deduce from the valency the oxidation state, is it not? What is the valency of calcium? 2. So the oxidation state of calcium ion, that is the calcium that wants to react with another element, is what? +2. Is that clear? So the oxidation state has charge. You understand? Because we are talking about radical, whereas the valency does not have what? Charge. Can you understand it? Then ion 3 ion, can you see that? Ion 3 ion, the oxidation state is what? 3, whereas the valency is what? 3. Is that clear? All this I told you that you can easily deduce them from the atomic number, is it not?
Yes.
By drawing the shells, isn't it?
Yes, sir.
Now, for non-metals, we say that metals are cation, whereas non-metals are what? Anions, isn't it? Chlorine, the valency of chlorine is 1. So chloride ion has the oxidation number of what? -1. Tetraoxosulfate 4 has that of 2, whereas hydroxide ion has what? 1 and -1. Is that clear?
Yes.
So if somebody asks you, what is the oxidation state of potassium? Can you get it? You draw that atomic number something, isn't it?
Yes.
The last shell, the number of electrons on the last shell, you just put positive in front of it. That's the answer, isn't it?
Yes.
And that's how we got plus what? 1. Is that clear?
Yes.
So we're going to be using this in subsequent. Have you finished the write-up?
Yes.
So we're going to be using it when we learn about the IUPAC nomenclature and the oxidation number. Is that clear? Yes, welcome. We are going to be learning about the IUPAC nomenclature of inorganic compounds and the concept of oxidation number or state. Oxidation number or what? State. Whenever elements react, they do so with respect to their oxidation what? Number. Whenever they combine. Is that clear?
Yes, sir.
And when you have the knowledge of this combination, you can easily deduce the chemical formula. You can easily deduce the word chemical formula of a compound, which is what we call the IUPAC nomenclature. How you name the chemical. You understand?
Yes, sir.
When oxygen combines with nitrogen, do you call it nitrogen oxide or dinitrogen 4 oxide or nitrogen 2 oxide or nitrogen 4 oxide? How do you call it? You know you have carbon monoxide.
Yes.
You have carbon dioxide, isn't it? So how do you know the one that is carbon monoxide and carbon dioxide? You have to know the oxidation states and how they combine together, isn't it? And that is what is called IUPAC nomenclature. Is that clear?
Yes, sir.
Now we say that oxidation number is the charge on the word valency. I told us that valency has very close relationship with oxidation number. If the valency of an element, say sodium, is 1, the oxidation number of sodium is also what? +1. If the valency of an element, say calcium, is 2, the oxidation number of calcium is what? +2. Is that clear?
Yes, sir.
So they relate. So that's why we say oxidation number is the charge on the word valency of the element. In other words, oxidation state is the valency word charge. So it's actually the valency, but now with a charge, isn't it?
Yes.
Instead of saying 1, you say +1. Instead of saying 2, you say what? Instead of saying 1 for fluorine, we say what? Minus what? 1. It is always minus for non-metals and always what? Plus for what? Metals. Is that clear?
Yes, sir.
Now, it is very important to know that the total oxidation number of every chemical compound is 0. The total oxidation number of every chemical compound is what? 0. Is that clear?
Yes.
Is that clear? Very, very important. Any chemical compound you are given, know that the oxidation number is what? 0. How do you come about that? Let's take an instance, calcium chloride. This is calcium chloride, written as what? CaCl2. Is that clear? The oxidation number of calcium, as we all know, is what? What is the oxidation number of calcium? What is the oxidation number of calcium? What is the valency of calcium? Calcium. You can draw the shells. What is the atomic number of calcium? Isn't it 20?
Yes.
Calcium is 20 back. So draw the shells and tell me the oxidation, the valency of calcium. I say you should draw the shell and count it properly. What's the valency? 2. You see, from the diagram is very easy. Is it 2 that you got?
Yes, sir.
Good. So the valency is 2. So if the valency is 2, what's the oxidation number? What is the oxidation number if the valency is 2? Plus 2. Oxidation number is always the same thing as the valency, isn't it?
Yes, sir.
Except that you add a charge, isn't it?
Yes, sir.
Plus 2. So the oxidation state of calcium is what? Plus 2. What is the oxidation state of chlorine? You can draw it. Check for chlorine, draw it and tell me the valency of chlorine. What is the oxidation number of chlorine? 1, isn't it?
Yes.
Minus what?
1.
Minus what?
1.
So from there now, how many chlorine do we have here? 2, isn't it?
Yes.
So it will be calcium chloride will be, for calcium you have 2, then for chlorine you have what? Minus 1 times 2, minus 2. Plus 2 minus 2, 0. Can you see that? So that's how you arrive at the fact that the oxidation stage for all compounds are what?
0.
For all compounds are what?
0.
So who can solve the oxidation state for water? So water is what? H2O, isn't it?
Yes.
So how can we do that for water? Hydrogen is what? What is the oxidation state for hydrogen? 1, isn't it?
Yes.
And it's 2 here, but
Yes.
so we have plus 1 times how many? 2. What is the oxidation state for oxygen? What is the oxidation state for oxygen?
8.
No. 8 is the atomic number. What is the valency of oxygen? 2, but so we have minus 2, isn't it? Because it's a non-metal. Minus 2. So what is that for? Hydrogen will be plus 1 times 2 is 2. Minus 2 is minus 2. So H2O now will be what? 2 minus what? 2, which is what? 0. So every chemical compound, the total oxidation number is what? 0. Is that clear?
Yes.
And that's why the chemical is stable. For it to be stable, it has to have oxidation number of what? 0. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
You see that? Now we are going to look at some elements have variable oxidation state. Is that clear? Now when you talk about potassium, you always say that potassium has the oxidation state of +1 because the valency is 1. Calcium has the oxidation state of what? +2 because the valency is what? 2. Chlorine has the oxidation state of what? -1 because the valency is what? 1. Fluorine has the oxidation state of what? -1 because the valency is always what? 1. But there are some elements that have, you cannot say that their valency or their oxidation state is 2 because they change. Is that clear?
Yes, sir.
Such elements are atoms of nitrogen. Is that clear?
Yes.
Nitrogen always has variable oxidation state. So now we're going to look at oxidation number of an element in a compound. Topic: oxidation number of an element in a what? Compound. How do you calculate the oxidation number of an element in a compound? How can you calculate it? So elements exhibit variable oxidation states. Like I told you, some elements exhibit variable oxidation states. You cannot just pin to one oxidation state and say this is always the oxidation state of such element. And what are these elements? E.g., we have copper. Copper can have oxidation state of 1, it can have 2, it can have 3. Another one is what? Lead. Another one is nitrogen. And another one is iron. These 4 elements, they can have different oxidation states. They can have different what? Oxidation numbers. Now let us consider the oxidation state of nitrogen in the following compound. Consider the oxidation state of nitrogen in the following compounds. So let's look at these following compounds and determine the oxidation state of nitrogen. Number 1 is N2O. Number 1 is N2O. Number 2 is NO. Number 2 is what? NO. Number 3 is NH3. Number 3 is NH3, which is ammonia. Number 4 is NO2. Number 4 is what? NO2. So, in these different compounds, nitrogen is having different oxidation states. Nitrogen is having what? Different oxidation. You cannot say that the oxidation state of nitrogen is 1 or 2. It could be 1 here, it could be 4 here. So how do you know the oxidation state? And with that knowledge of knowing the oxidation states of nitrogen, you can easily name these compounds. You can give it the right name that it should be in. Is that clear?
Yes, sir.
Now, what is the total oxidation state of this compound? 0, ba?
Yeah.
The total oxidation state of this compound is 0. Hmm?
Yes, sir.
So now, knowing that, how can you find out the oxidation state of nitrogen? Everybody look at the board, don't write anything. The total oxidation state of this compound is 0. What is the oxidation state of nitrogen? You understand? You don't know that of nitrogen. So let's call it what? X. Isn't it?
Yeah.
X. Nitrogen is how many here?
2.
So we call it 2S, isn't it?
Yeah.
Now, plus, what is the oxidation state of oxygen, which is stable? We know it's always what? -2. Always what? -2. -2. Is that clear? Equal to what? What is the total oxidation state of every compound? 0. So what would we have now? 2x. 2x back.
Yeah.
This 2 now, if it goes over to the other side, it will become +2, isn't it?
Yes.
2x equal to 2. Back. So x is equal to what?
-2.
No? 1 now, because it will be 2 over what? 2, which is 1. So what is the oxidation state of nitrogen? 1. And that is why we call this what? Nitrogen 1 oxide. Is that clear? Nitrogen what? 1 oxide. Call it dinitrogen 1 oxide. The name of this is what? Dinitrogen 1 what? Oxide. Dinitrogen because it's 2 nitrogen. 1 oxide is because the oxidation number is what? 1. Look at the board, don't write anything. After solving all of them, you can write 1. What is the total oxidation number here? 0. Now, nitrogen you don't know, you call it what? X. But oxygen you know, you call it what? Oxygen is always what? Minus 2. All of them is equal to what? 0. Now, you carry this one, you write what? X. Making X the subject of the formula. You take this minus 2 to over, it will become what? Plus what? 2. So the oxidation state of nitrogen here is what? 2. So what is the name of this compound? What is the name? Nitrogen what? 2 what? Oxide. That's the nomenclature. Is that clear? For this one, what is the total oxidation state of this compound? 0. Now, oxidation state of nitrogen, we don't know, we call it what? X. Plus, the oxidation state of hydrogen is what? 1, isn't it?
Yes.
And is how many? 3 of it. 3 times what? Plus 1. Isn't it? Equal to what? 0. Making X the subject of the formula, X is equal to 3 times 1 is 3. 3 going over to the other side will be what? Minus 3. So the oxidation state of nitrogen in this is what? Minus 3. So what will be the name of this compound? It's minus. So we have a generic name for this, which is what? Ammonia. Which is what? Ammonia. Now for this last one, the total oxidation state is equal to what? 0. The oxidation state of oxygen, which we don't know, we call it what? X. Plus what? Oxygen. What's the oxidation state of oxygen? Minus 2, isn't it? Times what? How many? 2. Equal to what? 0. Making S the subject of the formula. X is equal to what? 2 times 2, 4. So minus 4. You take it over to the other side because what? 4. Isn't it? So with that, what is the name of this compound? Nitrogen what? Nitrogen 4 oxide. Is that clear?
Yes.
Is that clear?
Yes.
Yeah, you can copy that in it. And Medina has not been in class for so long. I don't know what she's doing. Yes, so we're going to do calculations in oxidation number. We're going to say exercise on what? Oxidation what? Number. This is a normal question that comes in JAMB. You understand? They will ask you, find the oxidation state or find the oxidation number. Find the oxidation number of chromium atom in potassium heptadichromate what? 6. Find the oxidation number of what? Chromium. This is chromium. Understand? So how do you solve it? Solution. The formula says potassium heptadichromate what? 6. This is it. How do you solve it? What is the oxidation number of potassium? Plus 1. I've already shown you how to find oxidation number, is it not? From valency. I told us that the valency is the same thing as the what? Oxidation number, is it not?
Yes.
Only that you put a charge in front of it. But
Yes.
and valency is simply the number, the outermost electron. Is it not?
Yes.
The number of the outermost. For potassium, when you draw the shells like I taught you, you see that the outermost shell has only what? One electron. That's why the valency is 1. And the oxidation number is what? Plus 1. Isn't it?
Yes.
Now, what is the valency of oxygen? Minus 2, is it not?
Yes, sir.
Is it not?
Yes, sir.
Then what's the valency of chromium? That is the one we are looking for. We call it S. Is it not?
Yes, sir.
Now we say that for every compound, the total valency is always equal to what? The total oxidation number of every compound is always equal to what? 0. Total oxidation number is equal to 0, is it not?
Yes, sir.
So break it down. This is K2. So it will be 2 times what?
Plus 1.
2 times what? Plus 1. So we have 2 times what? Plus 1. Is that clear? This is where the 2 comes from, and this is the plus 1 because we are talking about the K. You understand? Then plus, we talk about the Cr. Is it not? The chromium is what? The oxidation number is X. So we call it what? 2 what? S. 2 times X. Isn't it? 2 times X. What is the oxidation number of oxygen? Minus what? 10. Minus 2. So plus, what times minus 2? 7 times what? Minus 2. Equal to what? 0. Is that clear? Yes. So that's what we have. 2 times plus 1 is what? 2 plus 2x minus 2 times 7 minus what? 14 equal to what? 0. Is that clear?
Yes,
2 plus 2x minus 14 equal to 0. 2 minus 14 will give us what? Minus 12 plus 2x equal to what? 0. Is that clear? 2 minus 14 will give us minus 12. This 2s, this 2s. Is that clear? Then take this 12 minus 12 to the other side. You have 2x is equal to what? 12. Because it's minus here, when it goes over to the other side, it becomes plus. Is it not? Then make s the subject of the formula. S is equal to 12 over 2, which is equal to what? 6. Is that clear? So the oxidation state of chromium is what? 6. Is what? 6. And actually plus 6. And that's why we have the name as potassium heptaozo dichromate what? 6. Dichromate what? 6. Dichromate what? 6. Is that clear? Did you write it like that? Is it on your notes? Is it on your notes? You don't understand the explanation?
Yes, sir.
So I'm going to solve the second one. And the second one says what? Second one is calculate the oxidation number of sulfur in SO3 2. This is an ion. This is not a compound, a neutral compound. And even if it's a neutral compound, it would have been SO3 will be equal to the total oxidation number would have been 0. Is it not? But if you, whenever you see ion, so anything that has a charge here, it will be the total oxidation number will be equal to that of the charge. Is that clear? So we have SO2 to be equal to minus what? 2. To be equal to what? Minus 2. To be equal to what? Minus 2. Very important. Now the oxidation number of S. What is the oxidation number of S? Oxidation number of what? Sulfur. That's what we are looking for, huh? So we can say that oxidation number of S is what? X, isn't it? That of oxygen is what? 2, huh?
Yes.
So oxidation number of oxygen is always 2. Is it not? Is it not? It's always what? 2. It's always what? 2. So we can simply say that what will be here? X, huh? Is it not?
Yes.
Oxidation number of S is what? S. Plus oxidation number of this one will be what? 2. Minus 2 times what?
3.
Minus 2 times 3. But
Yes, sir.
equal to what? Minus 2. Is it not?
Yes, sir.
So now x minus 2 times 3 will give us minus 6. Equal to what? Minus 2. But
Yes, sir.
then x now is going over to the other side will give us minus 2 plus what? 6. X will be equal to what? Minus 2 plus 6 is the same thing as saying 6 minus 2, which is what? 4. And that is why this is known as is plus 4. That is why this is known as trisulfate what? 4 ion. 4 ion because of the 4. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
So now I'm gonna allow you to solve this too, just exactly the way I solved it, and I'll look at it in your notes. Quickly. Solve it exactly the way I just solved it, and I will look at it in your what? In your what? In your what? Good. Do it now. Let me see it. Fresh. Yes, leave whatever you're writing and pay attention. You're going to be learning about isotopy. Isotopy. Isotopy is a phenomenon in chemistry that is very basic and important. You need to know about it. Is that clear? Isotopy. What is isotopy? It is expected, and from Dalton's atomic theory, you understand, that atoms of the same element are always the same. Is that clear? That's what Dalton's atomic theory said. That when you come and find the atom of potassium here in Abuja, is that clear? When you go to Kano and see another potassium, when you bring it, the atom is still the same thing. There's no difference. That's the statement of the Dalton's atomic theory, isn't it? Atoms of the same element are always alike. But you find out that due to advancements in chemistry, when we started using mass spectrometer and other equipment, we find out that this is not true. Atoms of the same element, potassium, you understand? But they are not alike. One might be having the atomic number of this, mass number of this. This one is having mass number of another thing. Two of them will have the same atomic number. You understand? If it is potassium that has, calcium has 20, isn't it? 20. If you get it here, it will have atomic number of 20. Get it in Zuleja, it's still atomic number of 20. But the mass number is not the same. And you know that mass number is simply the number of proton plus the number of what? Neutron. Number of proton plus the number of what? Neutron. Now, the concept of isotopy is saying that the number of neutron of the atom of potassium that you find here might not be the same number of neutron in the one you find in Suleja. Number of neutron in the one in Suleja may be 19, and the one you find here will be what? 18. Is that clear? Making the mass number to be what? Different. The atomic number are the same, but the mass number is what? Different. Because the atomic number is the basic identity of the element. So it's the same, it doesn't change. If you say the first 20 elements, hydrogen is 1, is it not? Helium is 2, is it not? It's the same thing everywhere. But their mass number does what? Vary. Their mass number do what? Vary. Their mass numbers do vary. Is that clear? And that is what isotopy is explained. It says that isotopy is the existence of atoms of the same element. Atoms of the same what? Element. Having the same atomic number but what? Different what? Mass numbers. They have the same atomic number. Atomic number doesn't change. Is that clear? But the mass number can be different. Because of what? The difference in the number of what? Neutrons. The difference in the number of what? Neutrons. This is due to the difference in the number of what? Neutrons. The mass spectrometer shows relative abundance of what? Isotope. Then how do we explain this? Now, you know that hydrogen has the atomic number of what? 1. Isn't it? But you find out that you can have hydrogen having the mass number of 1, we can have hydrogen having the mass number of 2, and we can have hydrogen having the mass number of what? 3. But do you see that the atomic number is the same all through? Can you see? Atomic number of hydrogen is always what? 1. So what is the number of neutron here? Number of neutron. Who can tell me the number of neutron here? Who can tell me? What is mass number? mass number. Mass number is equal to what? Number of proton plus number of what? Neutron. Is that clear? And number of proton is always equal to number of what? Electron. Is it not? So if the number of electron here or the atomic number is 1, this one will also be what? Proton. So what is the neutron? 0. Number of this thing is the mass number is 1 proton plus what? 0 neutron. And that's why it is equal to what? 1. What is the number of neutron here? 1, because we have 1 proton plus what? 1 neutron. The electron here is 1, which is the atomic number. So definitely it's always equal to the what? Proton. So proton is 1. So what is the remaining thing that made it 2 is the neutron. Is that clear? This one has how many proton? How many proton? 1. How many neutron? 2 neutron. So can you see that the number of neutrons is changing from 0 to 1, from 1 to what? 2. So that is actually what is causing the isotopy. And even is constant 1, 1, 1, the mass number will always remain 2. And if it is 0, 0, the mass number will always remain 1. Is that clear? So that's why we say this is due to the different number of what? Neutron. Now if you come to this hydrogen is known as tritone, this one is deuterium, this one is what? Protein. Now if you come to oxygen, oxygen has the atomic number of what? Atomic number of what? 8. It doesn't change. But it can have various mass numbers of 16, 18, and 17 and what? 18. What is the most stable and most common isotope of oxygen? Which one? The first one. Oxygen 16 is the most common, isn't it? That's why we use 16 as the mass number, is it not? Then the same thing happens with chlorine, isn't it? It has atomic number of what? 17. But you can see that the mass number varies. Here is 35 and here is what? 37. Now if you say what is the relative atomic mass of chlorine, you see that it's around 35.5, is it not? Do you know why it's 35.5? Because the relative atomic mass is normally the weighted average of the mass numbers of the what? Isotopes. The relative atomic mass would have been only 35 or only 37, but because there are 2, you can calculate the what? The average. That's what gives the relative atomic mass of chlorine to be 35.5. Is that clear? Is that clear? So that's how we come about that. That's how we come about that. Now, the question says, isotopy what? Calculations. Isotopy calculations. How do you do calculations involving isotopy? The normal question is always to calculate the relative atomic mass. Is that clear? The relative abundance of different isotopes determines the relative atomic mass used. Is that clear? So this question says chlorine exists in 2 isotopy forms. Chlorine 35 and chlorine what? 37 respectively. Those are the 2 isotopes of chlorine. Is that clear? Chlorine is either that is existing as mass number 35 or mass number was 37. Now it's saying that the relative abundance, how plenty are they on Earth? Is that clear? The relative abundance of 35 is what? 75%. Whereas the relative abundance of chlorine 37 is what? 25%. Calculate the relative atomic mass. How can you calculate the relative atomic mass? It's very simple. The relative abundance of chlorine 35 is what? Is what?
75%.
75%. So solution is simply say that the relative atomic what? Mass is equal to the ratios. That of chlorine 35 is what? 75%, is it not? This is 75 over 100, isn't it? times what? 35, chlorine 35, plus that of chlorine 37 is what? 25%, 25 over what? 100 times what?
37.
Times what?
37.
37 equal to the answer. Is that clear? What is the divide? What's the percentage? 75% times 35 will give us 26.25. It will give us what? 26.25 plus 25% of 37 is what? 9.25. It will give us what? 9.25. So when you add up together, you get what? 35.5. You get what? 35. And 35.5 is the relative atomic mass of chlorine, is it not? That 5.5 is the what? Relative atomic mass of chlorine. So write it that relative atomic mass is simply the relative abundance of one of the isotopes times the mass number, is it not?
Yes.
Plus the relative abundance of the other isotope times each what? Mass number. You add them together. If it is 3, you make it 3, add up, and that is the relative atomic mass. So with that, you are going to solve this one for me. I can clean the up back. Good. With that, you are quickly going to solve this. It's similar. Second one, example is similar. It was found from determination in a mass spectrometer. Number 2, it was found from a determination in mass spectrometer that the element neon has the isotope of masses that the element neon has the masses of, it has these various masses, 19, 21 and 22. 19, 21 and what? 22 respectively. The relative abundance of these isotopes are 90.92. The relative abundance of these isotopes are 90.92%. That's for the one with mass number of 19. 0.25%. 0.25% for the one of mass number 21. Then 8.83%. 8.83% for the one of mass number what? 22. Calculate the value of the relative atomic mass of neon. Calculate the value of the relative atomic mass of neon. Who can do this? This is very simple, huh? Emmanuel, is it simple? So solve it, please. Solve it quickly. It was found from the determination in mass spectrometer. I told us that whenever you want to study isotopes or relative atomic mass, you must use mass spectrometer. So the various masses of the isotopes are what? 19, 21 and what? 22. And their relative abundance are what? 90.92, 0.25 and 8.83. Calculate the relative atomic mass. Just the same way I solved the other one. 90.92 over 100 times 19 good. 0.25 times 21 over 100 good. 8.83 times 22 over 100. That's the answer. It's as simple as that. So how do you solve this? Very simple. I told us the relative abundance for the first one is what? 90.92 all over what? 100 times what? 19. That's the first one, 19. 90. Then plus the second one is what? 0.25 over what? 100 times what? 21. That's the second one. The third one is what? 8.83 all over what? 100 times what? Times 22. So solve down, you get the answer. It's as simple as that. Solve down, you get the answer. So when you solve down, you find out that it's equal to 19.27. But solve it down, let me see what you have. What will be this, what will be this, what will be that? So we can press the calculator of 90.92 over 100 times 19. So we give us 0.9092 times 19. 0.9092 times 19 is what?
1713.
17 what? What will it give us? 90.92 divided by 100 times 19 will give us what? Times 19. 17 point what? 2748. That's what this one will give us. 17.2748. What will this one give us? 0.25 over 100 times 21. What will it give us? 0.0525. Do it very well. What? 0.0525. 0.0525. What would this one give us? .83 divided by 100 times 22.
1.9426.
1 point what?
9426.
So add them up together and see whether it gives us 19.27 plus 17.2748. .27. So it gives us what? 19.26 what? 2699, which is approximately what? 19.27. Is that clear? So that is it. You see, it's the same method, huh?
Yes, sir.
Is it not the same method?
Yes, sir.
Understanding this. Okay, we are going to look at formula of compounds. Formula of what? Compound. In the previous calculation we did, we solved for potassium heptadichromate 6, isn't it? Instead of writing this as potassium heptadichromate 6, is very long, is it not? We can simply write it as K2Cr2O7, isn't it? This is the chemical formula. This is the chemical formula of potassium heptadichromate 6. So it's a sign for writing chemicals, so that you don't have to write it very long. Is that clear? But you need to understand how these formulas come about, how you can write it. Because somebody might want to write this and say KCrO2. You see, but you're still having potassium, chromium, and oxygen, but it's not writing it very well. So how do you come about writing the right, getting the right sign or the right chemical formula? We say that chemical formula is a sign to represent the molecules of elements and compound, and comprises of combination of symbols. Chemical formula comprises the combination of symbols. Can you see the symbols? This is the symbol for potassium, is it not? This is the symbol for chromium, and this is the symbol for oxygen. So when you combine symbols like this, you have what we call chemical formula. Chemical formula is a sign to represent molecules of elements and compound, and it comprises of combination of symbols. How do you come about the right symbol? Number one, you must have it in mind that you must understand the concept of atomicity. You must understand the concept of atomicity. How do atoms of some elements, how do they exist naturally? You find out that atoms of elements, these are known as the noble gases, is it not? Helium, neon, and argon. All the atoms can exist as a monoatom. Is that clear? They are monoatomic. They can exist as one, and that's why you can write it as this He without adding 2 or 3, Ne without adding 2, 3, 4. You understand? Argon. So you find out that most of the noble gases exist as monoatom. They are monoatomic. They exist with the atomicity of 1. In their molecule, it's only one atom that is in their molecule. Is that clear? But you find out that most of the halogens and non-metals, most of the halogens and non-metal exist as diatoms. The atomicity is 2. They exist as 2 atoms in one of their molecules. Is that clear? Have you ever seen oxygen written like this in chemical formula? You normally see oxygen written as O2. Is it not? O2, because there are 2 atoms of oxygen inside one molecule. Is that clear? O2 simply means what? O2 means one molecule of oxygen, but it's having how many atoms? 2 atoms. Is that clear? And that's how nitrogen, fluorine, chlorine, bromine, and iodine, most of the non-metals. Is that clear? Now you find out that we also have triatomic molecules like ozonized oxygen. They will have polyatomic like this form of sulfur and potassium. Is that clear? So you must have this at the back of your mind for you to understand how to write formula of chemical compounds. How to write what? Formula of chemical compound. You need to understand the atomicity. And atomicity simply means the number of atoms in each molecule of an element. Atomicity is what?
Number of atoms.
Number of atoms in each molecule. So these are molecules of these various elements. What is the number of atoms in helium molecule? What is the number of atoms in nitrogen molecule? What is the number of atoms in ozone molecule? Is that clear? And that is also the atomicity. Is that clear? Now we're going to look at another concept that is very similar to atomicity, and that is relative atomic mass. That is what? Relative atomic mass. Relative atomic mass. Please write along. Relative atomic mass is defined as the number of times one atom of an element is as heavy as. Is the number of times one atom of an element is as heavy as one atom of hydrogen. One atom of hydrogen. Is that clear? We use mass spectrometer to determine relative atomic mass. It is determined using a mass spectrometer. So how do we get this relative atomic mass? So we're going to look at some elements and their relative atomic masses. Elements, relative atomic mass. So let's look at some elements and their relative atomic mass. Hydrogen has the relative atomic mass of 1.1. Helium has that of 4.0. Helium has that of 4.0. Is that clear? Lithium has that of 6.0. Lithium has that of 6.0. Beryllium has that of 9.0. Beryllium has 9.0. And boron has 11. Carbon has 12. Is that clear? And nitrogen has 14. Nitrogen has 14. Oxygen has 16, fluorine 19, neon 20, and sodium 23. Is that clear? Please, what do you understand? What is the relationship between this relative atomic mass and which of the numbers that we said that is very close to relative atomic mass? Mass number, isn't it? So you see, it's the same thing as saying the mass number. Relative atomic mass is close to. It's approximately the mass number. It's approximately the what? Mass number. So if somebody asks you what is the relative atomic mass of a given element, how do you get it? Since you know the atomic number, do you know the atomic number of the first 20 elements? So you simply say how many, what times what? 2 times the number, is it not? Because 2 times the number is the mass number, is it not? And mass number is almost approximately the same thing as relative atomic mass. But the definition says that was relative atomic mass is the number of times one atom of an element is as heavy as one atom of what? Hydrogen. You understand? It's a relative mass that we use in quantifying elements in chemistry. Is that clear? In relation to hydrogen. Yes, the mole. You're going to be studying the mole in chemistry. It's a quantity. How do you know the quantity? Called mole. When you say, I'm using 1 mole of sodium in this experiment, measure out 1 mole. You understand? Or prepare a solution of 1 mole of sodium chloride in water. You understand? 1 mole. How do you know the quantity? Called 1 mole. How do you know the quantity? Called 1 mole. You say that the mole is the amount of substance which contains as many elementary particles as the number of atoms contained in 12 grams of carbon 12 isotope. That's the definition. The mole is the amount of substance which contains as many elementary particles as there are in what? 12 grams of what? Carbon 12 isotope. Now you can say that the number of atoms of carbon contained in 12 grams. What is the actual number? it is 6.02 times 10 to the power what? 23. And this very number is known as the what? Avogadro's what? Constant, or Avogadro's number, n. 6.02 times 10 to the power 23. You're supposed to have this number in your head, the Avogadro's number. Is that clear? Now, when you say 1 mole of sodium, you understand? 1 mole of sodium contains, how many atoms does 1 mole of sodium contain? 6.02 times 2 to the power 23 atoms of sodium. Is that clear? When you say 1 mole of H2SO4, it contains how many molecules? 6.02 times 10 to the power 23 molecules of the acid. Is that clear? Is that clear? Is that clear? So we're going to do some worked examples. Side. Yes, so we look at chemical equations. In chemistry, you see chemical equations on a daily basis, isn't it? Everything you want to show in chemistry, you use the chemical equation to represent it. Chemical equation tells us what is happening. You understand? In shorthand form. If two things are reacting, do you see them? Mostly you don't see the reaction. You understand? Even though you can see color change or change in state or stuff like that. You understand? But you don't know what is actually happening. You don't know whether it's carbon or it's magnesium, how it is moving. But with chemical equation representation, you can easily notice what is happening, isn't it? You can easily say that these are the reactants that came together in order to form the following products. Is that clear? And that's why we say that chemical equation is a shorthand form of expressing what happens in a chemical reaction. Is that clear? It shows us what actually happens in a chemical reaction in a shorthand form. In essence, it shows us the reactants, how the reactants react to form the what? Products. Now, this is a sample chemical reaction. You have two reactants, A and B, reacting to form two products, C and what? D. Is that clear? So in every chemical equation, you have the reactants on this side, whereas the product on the other side. Is that clear? So first of all, you have to write the reactants, then you write the what? Product on the other side. Now, balancing chemical equation. How do you balance a chemical equation? Now, the law of conservation of mass says that matter or mass cannot be created or what? Nor destroyed. It can neither be created nor what? Destroyed. This ensures that the total number of a particular atom on the reactant side is always the same as the number of that particular atom on the what? Product side. If you have carbon here and you have only one carbon here, you are also expected to have only one carbon on the other side. Is that clear? We are going to demonstrate this with the following examples. I can clean up. So we are going to demonstrate this equation balancing with the following examples. Example 1. Hydrogen gas combines with oxygen gas to form steam. Example 1. Hydrogen gas combines with oxygen gas to form what? Steam. When hydrogen and water combine, hydrogen and oxygen, you know you have H2O, isn't it? So how do you write the equation? How do you write a balanced equation for this? You have the H2 combine with O2 to give H2O. H2 combining with what? O2 to give what? Steam is water in gaseous form. This is in gaseous form, this is in gaseous form, and this is in what? Gaseous form. So that is the equation of reaction. But is it balanced? Is that equation balanced? Is it balanced? Why is it not balanced? There is 2 oxygen here, whereas here there is only what? 1 oxygen. So it's not balanced. You understand? But basically, you have to know one thing. For you to have H, you must write it as H2. You understand? Because it's a diatomic molecule. Is that clear? Most gaseous elements are diatomic molecules. Is that clear? So this one must also be written as O2. But this one can only be written as what? H2O. So how do you balance it? How do you balance it? If you put 2 here, will you be having oxygen, 2 oxygen? You are now having 2 oxygen back, and you're also having 2 oxygen here. But then hydrogen is now how many? 4. So you have to put what? 2 here. So this is a what? Balanced equation. Is that clear? Did you see the way I balanced it? What does this G stand for? Gaseous state. So write that equation, it is balanced. Now we look at the second example. Copper metal reacts with concentrated triosonitrate 5 acids to form a greenish blue solution of copper triosonitrate 5, copper 2 triosonitrate 5. Water with the evolution of blank gas, nitrogen 4 oxide. Copper metal reacts with concentrated triosonitrate 5. Example 2. Copper metal reacts with concentrated trioxo nitrate 5 acid. To form a greenish blue solution of greenish blue solution of copper 2 triosonitrate 5. Copper 2 triosonitrate 5. Water with the evolution of brown gas, nitrogen 4 oxide, with the evolution of a brown gas known as what? Nitrogen 4 oxide. Write a balanced equation for this. I can clean the up, isn't it? So this equation is telling us that copper, metallic copper, if it is metallic copper, it will be CuS, isn't it? S stands for what? Solid state, plus HNO3 plus HNO3. This is the what? Concentrated triazole nitrate 5 acid, and its acids are always in what? Aqueous state. To give what? CuNO32. CuN. Let me start from beginning to write it so that one line can contain it. I have copper plus HNO3 in aqueous state to give CuNO32, which is copper 2 triosonitrate 5, NO2, which is what? Nitrogen 4 oxide, which is a gas. Copper 2 nitrate is a is in aqueous state, then plus what? H2O, which is water, and is in what? Liquid state. That is the equation. Is that clear? That is the equation. So how can we balance this equation? Can we balance this equation? Copper, this S stands for what? Solid, isn't it? AQ stands for what? Aqueous. So this is gas, this is liquid. How do we balance this? Is it balanced? Copper is 1 here, is 1 here, so it's okay, isn't it? Hydrogen is 1 here, is 2 here, which is wrong, isn't it? N is 1 here, and is how many here? N is how many here? 3 back? No. N is 2 here. And N is here, how many? 1 back? So can we make N 4? Since it's 2 here already, we put 2 here. So N is now how many? 4 back? So we put 4 here, so that this one will be what? N will be 4 here too. Isn't it? Hydrogen is how many here? 4. How many is here? 2. So we can put 2 here to make it 4. Isn't it? Oxygen is 4 times 3, 12. Huh? Oxygen here is what? 6. Plus how many here? 4. 6 plus 4, 10. Plus 2 here, 12. So it's balanced. So that's the balanced chemical equation. Yes, welcome. Today we are going to be looking at empirical and molecular formula. Empirical and molecular formula. There are 2 types of formulas that every compound have in chemistry. 2 types of formula that shows the ratio of the elements in the compound. So those 2 types of formulas are empirical or what? Molecular. Whenever the formula of a compound is written, whenever you have the formula of a compound written, let's say sodium chloride. You understand? Sodium chloride. This is known as the molecular formula of a compound. Any compound you see written, the formula you see is normally the word molecular formula. Then you can break down the molecular formula to get the word empirical formula, because the empirical formula is the simplest relationship, the simplest formula. Is that clear? But in most cases you find out that the empirical formula could be the same as the word molecular formula. It's possible. Is that clear? The empirical formula could be the same as the word molecular formula, but in some cases they are different. So now, what is empirical formula? Empirical formula is the simplest formula which shows the simplest ratio of the number of atoms of element present in the word compound. You know what a compound is? This is the example of a compound. Whenever 2 elements are chemically joined together, we have a word compound. Which are the elements here? Sodium and what? Chlorine. You understand? So when they come together, we have what we call sodium chloride. We have what we call what? Sodium chloride. And that's why this is the formula. But you are going to find out that this is also the empirical formula. Is that clear? So empirical formula simply shows the what? The ratio of the element. So what's the ratio of sodium to chlorine here? 1:1. You understand? Because it's only 1:1. Then we'll talk about the second example of formula, which is molecular formula. And molecular formula is the formula which shows the actual, which shows the what? Actual number of atoms of different elements present in one word molecule of the compound. So this one shows the actual number, and that's why this is the formula that we normally use. Is that clear? This one shows the simplest ratio, whereas this one shows the what? Actual formula. Now, you're going to find out that there are 2 different compounds that can have the same empirical formula. Is that clear? But two different compounds can never have the same molecular formula. Is that clear? They don't have the same molecular formula. So example is ethyne. You can see ethyne. The empirical formula for ethyne is what? CH. And the empirical formula for benzene is what? CH. Both of them are having the same what? Empirical formulas. But their molecular formula are not the same. The molecular formula for ethyne is C2H2, whereas that for benzene is what? C6H6. So who can tell me why both of them are having the same empirical formula? Given that you can get the empirical formula from the molecular formula, you can tell me why? Just look at this. You see that if you divide through by 2, what will you have? CH, isn't it? This one you divide through by 6, what will you have? That's why. You understand? This one is telling you the simplest ratio, because here there are 2C and 2H. So the simplest ratio is 1C and what? 1H. Here there are 6C and 6H. They are the same equal number. So if you divide by the number there, you still get this. Is that clear? So this is the empirical formula for this, whereas this is the molecular formula for this. Are we together on that? Are we together on that? That is very, very important. Now, how do we determine empirical formula and the molecular formula? How can we determine the empirical formula and the molecular formula? How do we determine it? What is the way? How do we solve out to get the empirical formula? So we do this right around determination of empirical and molecular formula. Determination of empirical and molecular formula. The following steps are taken. Number 1, make a table of the elements present. That's the first thing you do. You make a table of the elements present. That's the first thing you do. Indicate under each element the percentage composition by mass of the atoms of the element. That's number 2. Indicate under each element the percentage composition by mass of the atoms of the element present in the compound or their masses. That's the number 2 step. Or the mass of each element, the mass of each element. That's the next thing you do. You are going to demonstrate this. Number 3, divide the percentage composition by mass or mass of the element by the molar mass of the elements to obtain the number of atoms or mole atoms present. Divide the percentage composition by mass of the elements. Divide the percentage composition by mass of the elements or the masses or the mass of each element by the molar mass of the element to obtain the number of atoms or mole atoms present, to obtain the number of atoms or mole atoms present. That's the number 3 step. That's the number 3 step. Number 4, obtain the ratio by dividing through by the smallest value obtained. Number 4, obtain the ratio by dividing with the lowest value by dividing through with the lowest value obtained. By dividing through with the lowest value obtained. So that is the number 4 rule. That is the number 4 rule. Then the 5th step is use the ratio to write the empirical formula. 5th step is that you can use the ratio to write the empirical formula. So that is how you get the empirical formula. Now you can obtain the molecular formula from the empirical formula. So how do you do that? And that you see in the 6th step. The molecular formula is equal to the empirical formula placed in brackets with a subscript n. So the molecular formula is equal to the empirical formula placed in a bracket with subscript n. That's the 6th. The molecular formula is equal to the empirical formula placed in brackets with the subscript n. So that is the value of the molecular formula with the subscript n. That is, it is actually equal to empirical formula n. Empirical formula n. Now, number 7, equate the molecular formula to the molar mass to find the value of the subscript. That's step 7. Equate the molecular formula with the empirical. I can clean the number 3 down back. With the empirical formula, weight it with this. So obtain the subscript n. Equate the molecular formula to the molar mass to find the subscript n. Sorry. Equate the molecular formula with the, it should be molar mass, sorry. With the molar mass to find n. Then lastly, write the molecular formula using the value obtained. Write the molecular formula using the value obtained. Write the molecular formula using the value obtained. So that is the rule. That is the rule, and we are going to practice through this. Those are the steps, and we are going to practice with those steps now. We're going to practice with those steps now. Are you done writing the steps? Yeah. Equate the molecular formula with the molar mass to find n. What they mean by the molecular formula is equate empirical formula n with molar mass. You understand? So that later you can now find the real value of that molecular formula. Is that clear? So in order for you to find n, that's why, which we are going to practice. Can I clean up? So let's practice it with an example. And it comes out in JAMB and in other chemistry exams. That is why we took our time to write the steps. Example, analyze a sample of an organic compound. Okay, example, analysis of a sample of an organic compound showed it contains. So we're going to take this example 1 and analysis of a sample compound showed. An analysis of a sample compound showed that it contained, or it contains 39.9% carbon, 39.9% carbon, that's the first, 6.9% hydrogen, 6.9% hydrogen, 53.2% oxygen, and 53.2% oxygen. So a sample compound was analyzed in the lab, and it was found out that it contained 39.9% carbon, 6.9% hydrogen, and 53.2% oxygen. Now it's telling us to, number 1, calculate the empirical formula. So A, calculates the empirical formula. B, if the relative molecular mass is 60, what is the molecular formula of the compound? If the relative molecular mass is 60, what is the molecular formula of the compound? The relative molecular mass is what is the molecular formula of the compound? Given C equal to 12, H 12, and O 16. Then you're given C is equal to 12, H is equal to 1, O is equal to 16. I hope you know what these values are for. What are they for? What are they for? What are these values for? What are they for? The atomic masses, is it not? The mass numbers of the elements. So this is the question. An analysis of a sample compound showed that it contained 39.9% carbon, 6.9% hydrogen, and 53.2% oxygen. Calculate the empirical formula. If the relative molecular mass is 60, what is the molecular formula of the compound? C is equal to 12, that's the atomic mass number of carbon, mass number of hydrogen is 1, and mass number of oxygen is 16. So what is the first step in the formula? What is the first step in solving for empirical formula? Who can tell me? Make a what? Table of elements present. That's the first thing. So step 1 says elements present. Is it not?
Yes, sir.
What are the elements that are present?
Carbon, hydrogen.
CHO, back, carbon, hydrogen, and what? Oxygen. What's the number 2 step?
Indicate under each element the percentage compound by mass of the atom.
Percentage was composition by what? Mass. That you should indicate it under what? Each element. What is the percentage composition by mass of carbon? 39.9. What is that of hydrogen? 6.9. What is that of oxygen? 50 what? 3.2. What is the next step?
Divide the percentage composition by mass of the element of the mass of each element by the molar mass.
Okay, divided by the molar mass of each element, right?
Yes.
So number of mole atoms present of each. So to get the what? Number of what? Mole atoms of each present, right? We should divide this by what? We should divide the percentage composition by mass by what? By the molar mass. So what is the molar mass of carbon? 12. What is the molar mass of?
1.
What is the molar mass of this?
16.
Isn't it? So if you divide it, what will you get? Which is the number of mole atoms? 39.9 divided by 12. Press calculator. 3.33. We get 3.33 here. This one divided by this will give us 6.9. This one divided by this will give us what? 53.2 divided by 16. 3.33 approximately. So what's the next step? Divide by the smallest number, isn't it? What's the smallest number? Divide by smallest what? Number. What's the smallest number? 3.33, right?
Yes.
So if you divide 3.33, 3.33, what will you get here? 3.33 divided by 3.33? 1. 6.9 divided by 3.33? 2, right?
Yes.
3.33 divided by 3.33? 1. So we get 1 is to 2 is to 1, isn't it?
Yes, sir.
Isn't it?
Yes, sir.
So what's the next thing? What is the next thing to do? After dividing by the smallest, check your steps. What's the next thing?
Use the ratio to write the empirical formula.
So use the ratio to write a what? New formula. So what is the ratio?
1:2 ratio.
1:2 is to what? 1. So use it to write the molecular formula. So what would be the formula? We have C what?
1.
C what? CH what? 2 what?
1.
O. Is it not?
Yes.
Is it not?
Yes, sir.
CH2O. Back?
Yes, sir.
Because C is only what? 1. H is what? 2. O is what? 1. So this is the what? This is the what? This is the empirical formula. So how do we get the molecular formula? Take this step.
The formula, the molecular is equal to the empirical formula.
Okay. The molecular what? Formula is equal to what? Empirical formula. What? Put in brackets subscript what? N. That's the meaning, isn't it?
Yes, sir.
Molecular formula is equal to this. Now, what else is the next thing?
The formula of the molecular mass.
Equate this molecular formula back,
Yes.
which is CH2O with the what? Molar mass. What's the molar mass? What's the molar mass? 60. Isn't it?
Yes.
So find the value of what? N. Back.
Yes, sir.
Now, what is the value of C? 12 back. 12 plus. What's the value of H? 1. So it will be 1 times 2 back. Isn't it? What's the value of O? 16 back.
Yes.
16. Our bracket what? N equal to what? 60. 2 times 1 is what? 2. 2 plus 12, 14. 14 plus 16. 30 back.
Yes, sir.
30 N equal to what? 60. N is equal to what? 60 over what? 30, which is equal to what? 2. Isn't it? So what is now the value of the molecular formula? It will now be what? CH2O, all bracket what? 2. Back? So if you open this bracket, MF, if you open this bracket, MF will be equal to what? C2H4O2. That is the answer. So write this thing exactly the way I wrote it. This is where I started. This is the first step. Element present. By this, 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 then this. This is the final answer. Write it very clearly so that you know it once and for all. Laws of chemical combination. Laws of chemical combination. What are the laws? What are the laws that are governing chemical combinations? How do you know how elements or reactants react to form products? How do they do it? They do it under specified law. Number 1 law is the law of conservation of mass, which states that matter can neither be created nor destroyed in the course of what? Chemical reaction. Just like we said before, if you're having a reaction, if the total number of carbon here is 2, the total number of carbon on the product side should also be what? 2. The second law states that the second law is the law of definite proportion or constant composition, which states that all pure samples of the same chemical compound contain the same element combined in the same proportion by mass. If you have sodium chloride in Nigeria, is that clear? And sodium chloride in Nigeria is made up of sodium and chlorine. If you go to America and still see sodium chloride, it will still be made up of what? Sodium and what? Chlorine, provided it's sodium chloride. All pure samples of the same chemical compound contain the same what? Elements combined in the same proportion by mass. Is that clear? It's the same. Water in Nigeria contains hydrogen and oxygen, is it not? In the ratio of 2:1. If you go to America, it will also contain the same element by mass in the same ratio, 2:1. Is that clear? Then the third law states that the third law is the law of multiple proportion, and this law states that if 2 elements A and B combine to form more than one compound, the several masses of A which combine with a fixed mass of B in simple word ratio. That's the law of multiple proportion. There are two elements that can combine together to form more than one compound. I hope you know. If carbon and hydrogen combines, what can they form? They can form ethyl, and they can also form benzene. Is it not what we checked when we are learning empirical formula?
Yes, sir.
So they can form those things, but they're always in what simple ratio. Their ratios are always in simple ratio. So please take note of all that. Yes, welcome. Today we're going to be looking at organic chemistry. We are going to be looking at organic chemistry. In the olden days, organic chemistry is believed to be the chemistry of plants and animals. It's believed to be the chemistry of what? Plants and animals. Whenever you hear that word organic simply means living things, is it not? And the living things that we know are what? Plants and what? Animals. Plants and what? These plants and animals, most of them are consisting of a particular chemical element. And that particular chemical element is known as what? Carbon. It's known as what? Carbon. So in modern times now, we have another definition of organic chemistry. We have another definition of what? Organic chemistry. And it is simply that organic chemistry is the chemistry of carbon. Is the chemistry of what? Carbon. Together with some other elements such as hydrogen, nitrogen, oxygen, sulfur. You understand? So whenever you have carbon connected using bond to hydrogen or sulfur, or with both of them, or nitrogen, or what? Oxygen, you call it what? Organic chemistry. You call it what? Can you see this? This is carbon and which other element? Carbon and hydrogen. So whenever you see such structure, even if there is nitrogen here, you still call it organic what? You still call it what? Organic what? So to be more specific, organic chemistry is the chemistry of carbon together with a few other elements like what? Hydrogen, nitrogen, oxygen, and what? Sulfur. There are over 3,000 organic compounds. There are over what? In the world. That's why organic chemistry is very, very important. Most of the compounds that you have in chemistry, some of them are what? Organic what? Compounds. Do you know the material that supplies the most money for Nigeria? Who can tell me the raw material that we have in Nigeria that gives us much of our GDP and much of our revenue? What is it that Nigeria exports to get money that we use in running the government? Crude oil. You understand? Crude oil is an organic what? Compound. And we are going to learn about crude oil under this organic chemistry. And you see why organic chemistry is very, very important. The main engine of Nigeria's economy is under what? Organic chemistry, and that is crude oil, hydrocarbons. You understand? So hydrocarbon is a component of organic chemistry because hydrocarbon is made up of carbon and what? Carbon and what? Hydrogen, and that's why you call it hydrocarbon. Fuel. You understand? So in subsequent classes, we are going to be learning about fuel. Now, why is it that carbon is so unique that is able to bond together with all these elements to form stable compound known as hydrocarbon? Why? Organic compounds. Why? Because carbon has some unique features, and one of those unique features that we are going to study is the valency of what? Carbon. Valency of what? Carbon has the following configuration. This is the configuration of carbon: 1s2, 2x2, 2px1, 2py1, and 2pz. Very, very important. You need to know this configuration of carbon. Is that clear? It forms mainly covalent bonds. Do you know the types of bonds we have in chemistry? Covalent, electrovalent. You understand? Yes, welcome. I told us that we have up to how many thousand carbon compounds? How many thousand? 3,000. You can see that there are plenty carbon compounds in the world. What are the unique features of carbon that allows it to have as many compounds as possible? I told us that due to the covalency, I've already explained that one to you. Carbon has how many external electrons? You understand? With those external electrons, you can only form the type of bonding known as covalent bonding. Carbon is tetravalent. Tetravalent means that it has how many? 4. Tetra means 4, you understand? So there are other features of carbon that enables it to have numerous stable compounds. Is that clear? One of the other features is that there are 3 types of orbital hybridization open to what? Carbon. And they are what? sp3, sp2, and what? sp hybridizations. This gives rise to a variety of what? Neutral compounds having single, double, or what? Triple bond. You understand? So depending on the type of hybridization, it determines whether it's going to have a single, double, or what? Triple bond. How many bonds is here? Carbon having here? Single. Single. How many here? Triple. How many here? Double. You see, man? So carbon can exist having single bond, having double bond, or having what? You understand? And you see that this carbon, this one and this one, how many carbon atoms do we have here? 1, 2, 3, 4, 5. How many do we have here? 1, 2, 3, 4, 5. You understand? So you see that this carbon compound here and this one are similar, but the arrangements are different. You understand? And that is because of the fact that carbon has unique features that makes it to have such thing. So if you can have 2 similar compounds having different structures, you understand? It's making carbon to have plenty types of compounds. You understand? So the arrangement alone can change so that you have an entirely different chemical compound. This chemical compound is different from this. It has different physical properties and chemical properties. Is that clear? So this is known as what? Pentane. Pentane means 5. Pen, but this one is what? 2-methyl what? Butane. Butane is 4. 1, 2, 3, 4. But it's having a methyl on the second carbon atom. That's why it says 2-methyl butane. You understand? So you should know all this. This one is what? Pent2-ine. Pent because it's having how many atoms? Carbon? 1, 2, 3, 4, 5. I told you that 5 is what? Pent. Then 2-ine. What does that mean? Ine. Whenever you see ine, it simply means that there are what? 3 bonds. You understand? This one is ane. A-N-E. Single bond. Butane. A-N-E. What? No. Single bond. Are you seeing any double bond here? No. But when you have E-N-E, in, double bond. Can you see that? Can you see that? It's still having how many carbon atoms? 1, 2, 3, 4, 5. Just like this one. But the difference is just in the number of bonds. And this different number of bonds, this one is single, this one is double. This one is what? Triple. And it's also 5 carbon atoms. You see, 5 carbon atoms, all of them are 5 carbon atoms, but they are arranged differently. You understand? Because of what? Hybridization. That's why this one is having double, this one is triple, this one is single. Because carbon can exist as what? sp3 hybridization, sp2 or sp hybridization. And that's why we have numerous carbon compounds in nature. And we say we have up to 3,000, is it not? Now another thing is that there is another style of compound that you can have, and this one is caused by what? The localization of what? Continuous pi bonding, which assures that 6-membered ring. This is a ring, but how many members? 1, 2, 3, 4, 5, 6. 6-membered ring carbon compound with the localized orbitals are particularly what? Stable. So this one is known as benzene. This is known as what? This is a benzene ring. You're supposed to ask a chemistry student to know how to draw these various types of compounds. So that's the assignment for you. Learning so that next time when I say draw pentane, you can off your head draw pentane. When I say draw hexane, hexane is 6. So you just add up 1 more C and put your hydrogen around it. Is it not? Thank you. That's all. Yes, welcome. Today we're going to be looking at hydrocarbons. Hydrocarbons are very, very important for us here in Nigeria because much of our revenue, our national revenue, is coming from oil, crude oil. You understand? So hydrocarbons are gotten from crude oil or from other sources like coal, you understand, or natural gas. But natural gas and crude oil are the major sources of our income here in Nigeria. So hydrocarbons is very, very important because from there you can get the fuel that cars use and everything. You understand? So we're going to be looking at these hydrocarbons. Hydrocarbons are organic compounds that are composed of carbon and hydrogen. Is that clear? Hydrocarbons are what? Organic compounds that are composed of what? Carbon and what? Hydrogen. That's why we call it hydrocarbons. Hydro stands for what? Hydrogen. Carbon stands for carbon. You understand? So any organic compound that is composed of hydrogen and carbon, hydrogen and carbon is known as what? Hydrocarbon. It has the molecular formula of CXHY. The molecular formula is what? CXHY, where X and Y's are what? Whole numbers. Is that clear? Example of hydrocarbons are methane. Can you see this? Methane, CH4. Another example is propane, C3H8. Another example is what? Benzene, C6H6. All these are examples of what? Hydrocarbons. Why are they examples of hydrocarbons? Because they are composed of what? Carbon and what? Hydrogen. Carbon and hydrogen. Carbon and hydrogen. Is that clear? Hydrocarbons are classified into aliphatic and what? Aromatic hydrocarbons. Aliphatic hydrocarbons are the ones that have straight chains or black chains, branch chains, or cyclic chains. Whereas aromatic hydrocarbons are the ones that are based on the structure of what? Benzene. Is that clear? What are the sources of hydrocarbons? If you want to make hydrocarbons, if you want to get hydrocarbons, what are those things that you use in getting them? Number one, the natural sources of hydrocarbons are what? Coal, natural gas, and what? Petroleum. Coal, natural gas, and what? Petroleum are the sources of hydrocarbons. And these natural sources of hydrocarbons are known as fossil fuel. They are called what? Fossil fuel. Why are they called fossil fuel? They are called fossil fuel because they are remains of plants and animals that have died over millions of years ago. You understand? And because you can burn them as fuels to produce what? Heat energy and other forms of energy. That's why you call them fossil fuel. Fossil fuels are just fuels that are gotten from remains of plants and animals that have died millions of years ago that you can burn to produce heat energy and other forms of energy. In these three types of sources, coal is a solid form of fuel. Petrol is a liquid viscous form of fuel, whereas natural gas is in gaseous form. So we have the gaseous form, the liquid form, and the what? Solid form. The solid form is coal. You understand? The liquid form is petroleum. The gaseous form of fossil fuel is what? Natural gas. Now we look at petroleum, which I told you is the major source of income for Nigeria in form of crude oil. Actually, the source. You understand? But this petroleum or crude oil can be used to produce fuel that our cars can use. You understand? Our generators in the house can use the fuel as well. You understand? So what is petroleum or crude oil? Crude oil is actually one of the major sources of fuel today. Is that clear? You can do what we call fractional distillation. You can do what we call what? Fractional distillation. To divide the crude oil into its various what? Mixtures, components. Is that clear? When we are learning separating techniques, we have various separating techniques. We have distillation, we have fractional distillation, we have sieving, we have evaporation, we have all of them, you understand? But the one that you use in separating petroleum mixtures is the one called fractional what? Distillation. So with fractional distillation, you can get the components of petrol or crude oil, such as PMS that you can use for driving car and other things, you understand? After getting the volatile components, the less volatile components that can be broken down more to get other components using what is equation known as what? Cracking. You can use cracking to break down the less volatile components of petroleum to produce various other components of petroleum that are useful in poly products and in other spheres of life. Is that clear? So first of all, what you do to the crude oil is that you do what we call what? Fractional what? Distillation. To get some of the volatile components. You get some of the what? Volatile components like what? PMS and other ones. You understand? PMS, premium, this one is used for in driving cars. To get to other further products, you do what we call cracking. You understand? So I'll be explaining these processes of fractional distillation of crude oil as well as cracking in subsequent classes. Is that clear? Thank you. Yes, welcome. Today we are going to be looking at a very important measurements of the quality of fuel. Of the quality of what? Fuel. Fuel. You use fuel to drive your car, is it not? You use fuel to do many things. To run the generator, to supply electricity, isn't it? You use fuel for many things. But most importantly, the fuel that we use in driving our cars. You understand? That fuel, the quality has to be high in order to prevent the knocking of our engine. In order to prevent the what? Knocking our engine. And how do you measure the quality of fuel that enables your engine to work effectively and smoothly? You do it using a parameter known as octane number. Known as what? Octane number. Octane number. You understand? If your car has the octane number of, if the fuel in your car has the octane number of 0, that means that the fuel has very strong quality. It means that it has very what? Strong quality. That means it can burn very well in the engine and it will not knock the engine. Your engine will be working effectively. You understand? So it's very, very important that you check the octane number of the fuel that we use, either in the lab before the fuel is being shipped out for people to use. Is that clear? So how you know that a fuel is of good quality is by measuring the what? Measuring the what? Octane number. So what is this octane number? Octane number is the rating of the performance of a petrol in the internal combustion what? Engine. Internal combustion engine simply means the engine of a car. Is that clear? Or any automobile. Now you say that 2,2,4-trimethylpentane. 2,2,4 what? Trimethylpentane, or you also can call it isooctane. You can call it what? Isooctane is a good fuel. Is a what? Good fuel. Because why is it a good fuel? Because it burns smoothly without causing what? Knocking. Any fuel that causes knocking is not a good fuel. But the one that burns smoothly without causing knocking is a what? Good fuel. And a very good example is what? 2,2,4-trimethyl what? Pentane, or you call it what? Isooctane. This isooctane is assigned the arbitrary octane number of what? 0. It has the octane number of what? 0. It is assigned the octane number of what? 0, because it's the most perfect fuel for engines. Is that clear? Now, octane number of any fuel is the percentage of what? Isooctane blended with heptanes, which has the same knocking characteristics as the fuel when compared in a standard what? Engine. That is the definition. You understand? So the more isooctane that your fuel has, the better the performance of the fuel. You understand? So you need it to have octane number of very low octane number, 0 or around that side. You understand? But if you have octane number of 100, is the fuel good for your car? It's not good. So you need octane number of around 0 or very small octane number. Now you talk about it can be raised by the presence of what? Branch chain hydrocarbons and aromatics. There are 2 types of hydrocarbon in terms of aliphatic. You have branch chain and we have the what? Straight chain. We have the normal. You understand? When you say isooctane is the octane that is branch chain. But the normal octane is what? N-octane. Normal octane, the one that is straight chain. We are going to be learning about straight chain and branch chain hydrocarbon very soon. So if you want to raise the octane number, you can do it by adding what? Branch chain hydrocarbons and what? Aromatic hydrocarbon. Other compounds that can improve octane number are what? Ethanol, methanol, and what? Tetraethyl what? Lead 4. Tetraethyl lead 4. Though the last, which one is the last? Tetraethyl what? Lead 4. The last causes lead oxides exhaust from pollution. So that's why it's not good you use this one to improve your octane number, because it can cause pollution, lead pollution. Organic chemistry is the chemistry of carbon compounds. You understand? These compounds are, what are some of the characteristics of features of organic compounds? They are very numerous in number. They are plenty. I told us that we have up to how many? 3,000. And they have common features. They have what? Most of the hydrocarbons, they have common features. And another thing is that they have great medical, biomedical, and economic what importance and value. And that's why we are studying we are studying organic chemistry, because they are of great economic importance. Like, you know that much of the revenue that Nigeria has is coming from an organic compound, the crude oil, you understand, that has plenty of organic compounds like pentane and all of them that you use in manufacturing fuel. And that is why we are learning about octane number, because your octane number of your fuel determines how efficient the fuel can burn in the internal combustion engines of cars, enabling you to have effective burning, and you can drive your car without knocking. Is that clear? So in order for you to avoid knocking, make sure you use fuel that has good octane number, like what 2,2,4 trimethyl what pentane, also called what isooctane. You understand? And that is the arbitrary measure of the octane numbers of fuels. Exactly. Thank you. Hello, welcome. Today we are going to be looking at variety of organic compounds. I told us that we have up to 3,000 different types of organic compounds. So we're going to be looking at why is it that carbon is able to have so many compounds to be able to be called organic chemistry. Organic chemistry is just the chemistry of only carbon and its compound. Why is it that carbon has so many compounds? So we're going to look at the presence of numerous organic compounds. What is the reason for having numerous organic compounds? First of all, organic compounds are compounds that are composed of, number one thing is what? Carbon. Number two is oxygen and what? Hydrogen. Number three is nitrogen, sulfur, halogens, and in some rare cases we have something like metals on carbon. So we look at organic compounds are composed of, number one, carbon, number two, hydrogen and oxygen, number three, elements such as nitrogen, sulfur, halogens, phosphorus, and sometimes metals. You understand? So that's how you identify an organic compound when you see them. First of all, is that it must contain carbon. Then in most cases it can contain hydrogen and what? Or oxygen. Then in some cases, few times it can contain nitrogen, sulfur, halogen, and phosphorus. And in few cases it can have what? Metal. So why is it that carbon is able to form many organic compounds? What nature of carbon that enables that? Number one, carbon's ability to form single, double, and triple what? Covalent bonds. I told us that carbon can easily form single, double, and what? Triple covalent bonds. Using the same number of carbon atoms, like 5, you can have a structure that has a single bond, pentane. You can have the one that have a double bond, 2-methyl and butane. You can have the one that has ring, like benzene and other ones. You understand? So carbon can be in all this nature. And I told you that the reason for this is because of the hybridization of the N orbital. Now we have ability of carbon atoms to catenate. Carbon has the ability to do what? Catenate. Catenation simply means to combine with one another in order to form straight chain, branch chain, and what? Ring chain compound containing many carbon atoms. Carbon has the ability to do what? Catenate. Catenation. Ability to bond with other carbon atoms to form straight chain hydrocarbons, branch chain hydrocarbons, and ring hydrocarbons. Now, the other character is because of the ease with which carbon combine with hydrogen, oxygen, nitrogen, and what? Halogen. Carbon combine easily with nitrogen, oxygen, halogen, and other these things. Then another thing is that the bond energy per carbon-carbon single bond is high, 346. So it makes carbon-carbon bond to be very stable. Then we look at characteristic features of organic compounds. How do you know organic compounds when you see them? Number one, organic compounds are flammable. They are highly what? Flammable. They can burn, they can explode. That's why you can use fuel to burn things. You can use it to drive car, because when fuel burns in the engine, it just develops energy that the car can use to move. Reactivity. Reactions of organic compounds are slow. You understand? Organic compounds have low melting and what? Boiling point, because of the weak intermolecular forces between them. They are covalent in nature. You know that carbon has 4 outer electrons, so they form covalent bonds. Organic compounds are not soluble in polar solvent, but they are soluble in non-polar solvent. Example of non-polar solvent is benzene and ether. Benzene and what? ether. Both of them are non-polar. So that's why you can, if you want to dissolve any organic compound like fuel and all those things, you cannot dissolve them in water. You understand? Fuel is not soluble in water. All those things, they are not soluble in water, but they are soluble in non-polar what? Solvents like benzene and what? Ether. So these are the characteristics of organic compounds. They have low melting and boiling points. They are covalent in nature. Their polarity, they are non-polar. They are non-polar, and their solubility, they are only soluble in non-polar compounds. They are flammable, highly flammable. If you see where they are keeping hydrocarbons, they will write, please don't. They are highly flammable. You don't have to use matchbox or anything around that area. Reactivity, they are very, very slow in reaction. Is that clear? So we've been able to cover the reason for the availability of numerous organic compounds and the characteristics of organic compounds. Thank you. Yes, welcome. Today we're going to be looking at homologous series. We're going to be looking at what? Homologous series. Homologous series. I told us that there are numerous numbers of organic compounds. We have up to 3,000 organic compounds. You understand? So in chemistry, these organic compounds are divided into, they are classified into families, into groups that share similar physical and chemical properties. You understand? And these groups, you have a group called alkanes, we have alkenes, we have alkynes, we have alkanols, we have alkanoic acid, we have aromatic hydrocarbons too. You understand? So we have different groups. In order for us to understand the behavior of these these organic compounds very well, we divided them into groups. And these groups are known as what? Homologous series. So what is homologous series? Homologous series is a family of organic compounds which follows a regular structural pattern in which each successive member differs in its molecular formula by a CS2 group. So when we look at a group like alkanes, when we look at a group like what? Alkanes. These are the different homologous series we have. We have alkanes, alkenes, alkynes, alkanols, carboxylic acids, and so on. You understand? So the first member of the alkane is known as methane. It's known as what? Methane. You just use METH. You understand? And end it with what? End it with the rest of the numbers. So the first member of this is what? Give me another marker. The first member is what? Methane. That's the first member. You understand? So you can see this name is coming here, is it not? Yes. So the second member is what? Ethane. You can see this same thing is also here. But methane is for what? One carbon atom. Is that clear? Ethane is for how many carbon atoms? 2. Propane is for how many? Butane is for how many? Pentane is for how many? The same way, the first member of alkane is also what? It will be 1. The second member will be what? Ethene. What? Ethene. So you have this similar to this, only that this is what? 2. Is it not? The third member will be what? Propene. Whereas here, the third member here will be what? Propane. Can you see that? So, if you look at the structural formula of this, the difference between this one and this one will be just addition of this. Once you add this to this, you get this. You add another this to this, you get this. Is that clear? So that is how they are in their families. So I'm going to clean this up so that we have what we had before. You understand? So the first homologous series, the simplest homologous series is known as the what? Alkenes. And it has this what? Formula. Can you see the formula? So now, ethene, we have this. How did we come about ethene having this? If you have this formula and you say you're taking the first one, methane, but methane is 1, but so it will be C, N will be represent 1, H will still be H. You have what? 2 times 1, is it not? Plus what? 2. So what will you get? You will get C. 2 times 1 is what? Plus 2, 4. CH what? 4. So this one will be what? Methane. Can you see that? Methane. How do we get ethane to be this? The same thing. See, instead of 1, what will ethane be? 2. H in bracket, you have 2 times what? 2 plus what? 2. So we will now have the formula to be what? C2, 2 times 2, 4 plus 2, 6, H6. Can you see it? C2H6. That's why we have ethane to be this. Is that clear? So we actually use the what? Formula. We actually use the what? Formula. And this is the formula that we are using. We are just replacing, for methane, we put 1 in place of N. For ethane, we put 2 in place of N. For propane, we put what? 3. So if you look at this methane, this is the formula. Who can tell me the difference between this and this ethane? Is it not just the addition of this? Because when you carry this 1C and add to this one, you have C2, is it not? When you carry 2H and add to this 4H, you have what? H6. You understand? So if you add another one here, another of this to here, like now, you will now have C3, H what? 8. And that will be what? That will be what? Propane, the third one. If you want to add butane, just add another of this to this. Is that clear? Is that clear? So we simply get subsequent one by just the addition of what? By the addition of what? CH2 what? Group. The same thing happens to this one. If you also add this one to this, if you put 1 here, you add to this, you get ethane. Add another one, you get propane. Add another one, you get what? Butane. You understand? So the most important thing is that you take note of the what? Formulas. You take note of the what? Of the different homologous what? Series. So you have alkenes, you have alkynes, you have alkanols. Example of alkanol is what? Ethanol. Example of alkyne is what? Ethyne. Example of alkene is what? Ethene. Example of carboxylic or alkanoic acid. You can also call this either carboxylic acid or you call it what? Alkanoic acid. Example of alkanoic acid is what? Ethanoic acid. And these are their formulas. All these their formulas are derived from here. Only that if it is ethene, if it is it that is starting it, you know that you are replacing N with what? 2. If it is prop that you want to start, you will replace what? N with what? 3. Then you derive the formulas. All these their individual formulas are derived from these general formulas. Is that clear? But note what you want to start with. If it is meth, it's 1, eth 2, prop 3, boot 4, pent 5, hex what? 6. So that's how you come about the formulas. Knowing these very formulas, very, very important. The individual formulas of the homologous series. So the different homologous series that we have are what? Yes, welcome. Today we are going to be looking at the common characteristics of homologous series. Common what? Characteristics of homologous series. We said that homologous series are families of organic compounds. You understand? That increase structurally by the group known as CH2. So that each member, when you want to get another member of the same homologous series, you just add CH2. Like if you have methane, you add CH2 to methane, you get what? Ethane. Add another CH2 to ethane, you get propane. Add another CH2 to propane, you get what? Butane. Add another CH2 to butane, you get what? Pentane. Add another CH2 to pentane, you get what? Hexane. You understand? So you just have addition by what? CH2. Another homologous series that we have is the alkenes. We have also the alkynes. We have the alkanols, and we have the what? Alkanoic acid and so on. So what is the common characteristics that each homologous series have within its members? Number 1, they have the same general molecular formula. All members share the same general what? Molecular formula. Like the alkenes, all of them have this formula. So if you put 1 here, if you use 1 to replace N, you're finding for methane. If you use 2, you're finding for what? Ethane. If you use 3, you're finding for what? Propane. If you use 4, you're finding for what? Butane. If you use 5, pentane. The same way here, alkenes, this is their formula. If you replace with 2, you have ethane. With 3, you have propane. With 4, you have butane. The same thing with this one. If you replace N with 1, you have what? With 2, you have ethine. With 3, you have propine. With 4, you have what? Butane. With 5, you have what? Pentine. With you understand? So that's how it works. Now you have Difference between successive homologous series is just by the addition of what? CS2 group. I told you this before, you understand? So if you want to move from methane to ethane, you just add CS group. Now the physical properties, their boiling point increases down the series so that the first four members of alkanes are gases. What are the first four members of alkanes? Methane, ethane, propane, methane, ethane, propane, and what? Butane. All of them are gases. You understand? But the other ones from 5 to 17, they are what? Liquids. Then from 17 down, they are what? Solid. Wax-like solid. You understand? Why? Because their boiling point is increasing down the series. You understand? So the one with the smallest boiling point in the alkane group is the what? Methane. Followed by what? Ethane. Now, chemical properties. Members show similar chemical properties. Example, alkanes are fairly unreactive under ordinary what? Conditions. All alkanes are fairly unreactive under ordinary conditions. You understand? So the chemical properties of alkanes, all of them, whether it is methane, ethane, or butane, they are similar. The chemical properties for all alkynes are also similar. That of all alkanols are also similar. You understand? So they share similar what? Chemical properties. Like what? Alkanes are fairly unreactive under ordinary conditions. They burn in air, forming carbon 4 oxide and what? Water, and undergo substitution reaction with other substances such as what? Halogen. So when we start learning about the chemical properties of alkanes, you see that they undergo a reaction known as substitution reaction with halogens. Then fifthly, we have that the general methods of preparation of all of them are similar. You understand? The same way you prepare methane is similar to the way you prepare what? Ethane. Is similar to the way you prepare what? Butane, because they are in the same homologous series. So if you want to prepare like alkanes now, you have all members usually prepared using the same general method. E.g., alkanes are prepared by the action of hot soda lime on sodium salts of specific acid. You understand? So what you now check is that you want to know the particular alkane you want to find. So get the specific soda, get the specific sodium salt and add it to soda lime. You get the alkane, whether it is methane or ethane or propane or butane or what? Pentane. You understand? So you use similar way to prepare for the homologous, similar method to prepare each homologous series. And we say that the homologous series that we have are what? Alkanes, alkenes, alkynes, alkanols, alkanoic acids, you understand? And so on and so forth. So note that why we group them into the same homologous series is because they have these similar properties. Number one, most of them have the same general molecular formula. Most of them, the members have difference between successive homologous series to be what? CS2 group, and also increase of 14 in the molecular mass. Most of the members of each homologous series have physical properties in which the boiling point increase down the what? Series. Most of them share similar chemical properties. Most of the members of each homologous series share the same chemical properties. Most of them are also prepared using the same method of preparation. Most of the members of each homologous series are also prepared using the what? Good. So if you are preparing alkanes by using by the action of soda lime on respective sodium salts, how are you going to prepare the alkenes? It's going to be a different method. You understand? But no matter the member, it's going to be the same for alkenes, for all of them, whether it is ethene, propene, butene, or what? Pentane. The same way you use similar method to prepare members of the alkynes, whether it is ethine, propine, butane, pentine, or what? Exactly. You understand? So you better study that. Most of them have these similarities. Homologous series have these various similarities. So after this, we are going to be looking at archive groups and functional groups. Very, very important thing. Yes, welcome. Today we are going to be looking at archive groups. Sit down, sit down, sit down, sit down. Make yourself comfortable. we're going to be looking at alkyl groups. In most of the organic compounds that we'll be looking at, they are going to be making up of two groups. Two what? One is the alkyl group and one is the functional group. One is the what? Alkyl group and one is the what? Functional group. So we are going to be looking at these two groups, alkyl groups and functional groups. Now, if you look at this compound, can you see this compound? The name of this compound is chloromethane. Chloro what? Methane. Chloro what? Methane. This chloromethane is simply formed from chlorine and methane. From chlorine and what? Methane. What is the formula for methane? The formula for methane is CH4, is it not? CH4. What is the formula for chlorine? Cl2. You understand? Can you see that this is how many hydrogen is there? 4. If you replace this hydrogen, that is 4, with 1 chlorine, it will remain only what? 3. Can you understand this? Yeah. This is methane, the parent compound. You understand? You react methane with chlorine. You understand? Can you see this chlorine atom? Yes. This chlorine atom is replacing one of the hydrogen here. Making the hydrogen, instead of to be 4 now, it will be what? 3. And the remaining hydrogen will be replaced by what? Chlorine. In order to form what? Chloromethane. Can you see that? So this kind of reaction, they call it substitution reaction. They call it what? Substitution reaction. When one of the hydrogen atom of an alkane is replaced by a halogen in order to form such compounds as this. Is that clear? So this compound that is formed, the first part of it is known as the methyl group. It's known as the what? Methyl group. If it is from methane. If it's from ethane, it is known as what? Ethyl group. So all of them are classified as what? Alkyl group. So alkyl groups are those groups that are formed. You can see these groups derive from the alkanes by loss of a hydrogen what? Atom under what? Substitution reaction. So that reaction, whereby one hydrogen atom from an alkane group is lost in order to be replaced by halogen or any subsequent element, is known as substitution reaction. It's known as what? They form compounds composed of the alkyl group and the substituent group. Who can tell me the substituent group? Who can tell me the substituent group in this compound, chloromethane? The substituent group is the what? Chlorine, whereas the alkyl group is the what? Methyl. Is that clear? So they are formed from alkyl group and substituent group. E.g., chloromethane is composed of methyl group obtained from methane by the loss of one hydrogen atom linked to a substituent chlorine atom. Alkyl groups have a general formula of this. This is the general molecular formula of alkyl groups, CnH2n+1, and are named after the parent alkane by replacing what? The ending A by what? Al. They are given the symbol what? R. So this is the parent alkane, methane. The alkyl group will be called what? Methyl. Methyl. And this is the formula. If it is ethane that you are getting it from, it will be called what? Ethyl. You understand? You understand? Just like here where we have what? Methyl. Can you see that? Methyl. Ethyl, propyl, butyl, pentyl, and hexyl, with their respective what? Formulas. So what happens actually is that in their formula you just remove one what? Hydrogen. Can you see that? Methane should have been CH4, is it not? Yes. But now it's CH3 because it's methyl. Loss of one hydrogen what? Atom. This one is ethyl. It should be C2H6. But here it is what? C2H5 because of the loss of one hydrogen atom from ethane to form what? Ethyl. You understand? So this is what we call alkyl groups. Very, very important. We are going to be looking at functional groups. You understand? Immediately after alkyl group, you have the functional group. Is that clear? Okay. Yes, welcome. We are going to be looking at functional groups. We are going to be looking at what? Functional groups. Every organic compound normally has two groups. the alkyl group and the functional group. The alkyl group and the what? Functional group. And I told us that the functional group determines the chemical properties of the organic compound, whereas the alkyl group determines the physical properties like solubility and melting point. Is that clear? So in most of the organic compounds that you'll be seeing, note that it is making up of alkyl group and what? Functional groups. Alkyl group and what? Functional groups. The alkyl groups determine the physical property, whereas the what? The functional group determine the what? Chemical properties. So what is a functional group? A functional group is an atom, a radical, which are a group of atoms, or a bond common to a homologous series, and which determines the main chemical properties of the series. So you see, the functional group is the group that determines the what? The main chemical properties of the series. An alkyl group is a fairly inert chemical, the alkyl group is fairly inert chemically because of the stability of the carbon-hydrogen what? Bond. You understand? So chemically, the alkyl groups are stable, so they don't engage in chemical reactions. So it is actually the functional groups that do what? Engage in chemical reactions. So examples of functional groups are, if you come to the alkanes, they don't have any functional group. You understand? They don't have any functional group. The alkyl groups, the alkyl group is the functional group. The haloalkanes is they are a combination of halogens and alkanes. You understand? So the halogen part of it is the functional group. Alkanols has something to do with the hydroxy group. Can you see the hydroxy group? The hydroxy group is the functional group. For ethers, this line is the functional group. For carboxylic acids, the COOH is the functional group. You understand? For alkanones, the CO is the functional group. For alkanals, the HCO is the functional group. For ethers, OR is the functional. So you need to be able to pick out the functional groups. So whenever you look at the formula, you should be able to tell the functional group. What is the functional group for this? This place is the functional. This is the functional group. This is the functional group. Immediately you remove the R. The other part of the formula is the what? Functional group. And that is what determines the chemical property of the homologous series. Very, very important. If you are asked what are the effects of alkyl groups and functional groups on the chemical properties, what are the effects? If somebody asks you what are the effects of the alkyl groups and the functional groups on organic compounds, the effect is that the alkyl groups determine the physical properties like boiling point and solubility and melting point. Is that clear? Whereas the functional group determines the what? Chemical properties. Is that clear? Yeah, you want to ask me a question?
Those are, they are not.
Which ones?
R.
This R represents the alkyl group. If you check your note, you see where I said alkyl groups are represented by R. So all these R's are the what? Alkyl groups. Whereas the other thing apart from the R is the functional group. And I told you that every chemical compound is composed of an alkyl group and what? Functional group. Alkyl group, functional, alkyl, functional, alkyl group, functional. The R here is the alkyl group, whereas the other things here are the functional group. And that's why I brought out the functional groups here separately. You understand? The X in this place is the functional group. The OH here is the functional group, whereas the R is the what? Alkyl group. So these alkyl groups determine the physical properties, whereas the functional groups, which are these, determine the what? Chemical properties. You understand? So if you have compounds where the alkyl group, the R's, are very big compound, you understand? They are going to dominate the functional group. So that's why we have homologous series or compounds that have very large R. They are insoluble in water. You understand? Whereas the ones that have very small amounts of R, they will be soluble in water. Thank you. Yes, welcome. Today we are going to be looking at saturated and unsaturated organic compounds. there are two major classes of organic compounds. The ones that have single carbon to carbon bond. Is that clear? The ones that have only single carbon to carbon bonds or only single bonds inside them. Those compounds are known as saturated compounds. The ones that have double or triple bonds are known as unsaturated. Is that clear? So those are the two classes. Can you see this ethane? What kind of bonds does ethane have? Single or double? Single. Can you see propane? What kind of bonds does propane have? Single bonds. So these ones that have single bonds, they are known as saturated. Whereas, can you look at this one? How many bonds? Double. This is ethene. This is ethyne. How many bonds? Triple. These ones that have double bonds, or these ones that have double bonds connected to other atoms like oxygen and nitrogen, they are regarded as what? Unsaturated organic compounds. Is that clear? JAMB is going to ask you, which of the following is an unsaturated hydrocarbon? Then they will put options like methane, ethane, propane, ethyne. Which one is the answer? Ethyne. Because ethyne has triple bonds. Is that clear? This is ethyne. How many bonds? Triple. You understand? So anyone that has more than one bond, it is known as unsaturated. But the ones that have only single bonds, they are known as what? Saturated. A good example of saturated hydrocarbons are alkanes. They are what? All the alkanes, they have single bonds. Whereas the ethyne, the alkanes and the alkynes have double and what? Triple bonds respectively. So they are regarded as what? Unsaturated. Also, these other compounds like ethanol that is connected to oxygen in double bond, they are also regarded as what? Unsaturated. Even ethanonitrate that has triple bond connected to nitrogen, they are also regarded as what? Unsaturated. Now, how do you get unsaturated compounds? Are you looking at this ethane? How many carbon atoms does it have? 2. This ethyne, how many carbon atoms? You see that? For the nitrogen, how many nitrogen do we have here? 1, 2, 3, 4, 5, 6. How many nitrogen here? 1, 2, 3, 4. That means this one has lost some hydrogen atoms. You understand? And replaced it with what? Double bond. So you get unsaturated organic compounds from the saturated ones by losing some hydrogen what? Atoms and replacing it with double bonds. Is that clear? So that's what I say there. Unsaturated, on. This is not used saturated. This is a mistake. This is on. Is that clear? Unsaturated compounds are gotten from the saturated ones by the removal of what? Hydrogen atoms and introduction of what? Double or what? Triple bonds, which are the functional groups, making them more what? Reactive. All these unsaturated compounds, they are more reactive than the saturated ones. These ones are stable. So this double bond of alkenes is their what? Functional group. The triple bond of alkynes is their what? Functional group. And you know that functional groups makes organic compounds to be more what? Reactive chemically. While the alkyl group makes them to determine their physical properties. Is it not what we learned yesterday? So take note of all these. You understand? So if somebody asks you, why is it that the alkanes and the alkynes are more reactive than alkanes? You say because they have double bonds, which are what? Which makes them unsaturated, and which are their functional group that helps them in reaction. Is that clear? Thank you. Yes, welcome. Today we are going to be looking at the formulas of organic compounds. Formulas are very, very important in chemistry. Is it not? You use formulas to indicate or to show compounds. Is it not? So organic chemical compounds, they also have their formulas, just like the inorganic ones have. They have empirical formulas, which are the smallest formula representation. They also have molecular formula, which are the actual indication of the atoms that are combined to form a particular compound. Those are the two kinds of formulas that we have in inorganic chemistry: empirical formula and what? Molecular formula. But for organic chemistry or organic chemical compounds, we have an additional formula known as what? Structural formula, known as what? Do you know why we have structural formulas in organic chemistry? It is because one single molecular formula can be representing two different types of compounds when you represent them structurally. Do you know what they call isomerism? Yes. You are going to be learning it so that you see that a compound with one chemical formula might represent two different types of substances, but the structure that are the same. You understand? The way this one is bonding this direction, this other one might be bonding in this direction, or might be having different atom constituents. So that brings us to today's lecture: formula of organic compounds. How do you represent organic compounds in equations using formulas? How do you do that? So you can do by number one using what we call empirical formula, which is also possible for inorganic chemical compounds. Empirical formula. What is empirical formula? It is the simplest formula of a compound. It indicates the relative number of each kind of atom in a molecule of a substance. Relative number. Do you know the compound that has C6H6? Which compound has this? Do you know that this, you can represent the empirical formula for this is CH. What is the ratio of carbon to hydrogen? 1 is to what? 1. And it is here also what? 1 is to 1. You understand? Because 6, if you divide through by 6, you get 1. You understand? So this is the empirical formula for this. Do you know this compound C2H4? This is ethane, but the empirical formula for ethane is CH4. CH what? 2. CH2. Do you know why? What is the ratio of this to this? 1 is to what? 2. And this one is also what? 1 is to what? 2. Because if you use 2 and divide through, you get 1 and 2. You know? That is what is here. You understand? So this formula shows you the what? The relative number. It's telling us that the relation to this, that is 1 is 1. So the more you add this, the more you add this. You understand? But for you to get the molecular formula, you need to indicate the actual number. So the empirical formula for ethane is this, whereas the molecular formula for ethane is this, which is what? 2C2H4. This is the actual. And that's why we say that molecular formula indicates the actual numbers of each kind of what? Atoms in a molecule of a substance. It is got from the what? Relative molecular mass of the substance and is what? Empirical formula. So you can use this empirical formula to get the what? Molecular formula. Once you have the what? Relative molecular mass of the substance. It is more useful than the empirical formula. The molecular formula is more what? Useful than the empirical formula. So we look at the third kind of formula known as structural formula, which is possible for organic chemical compounds. Like I told you, if you're using only the molecular formula to represent organic compounds, you will be lacking some information, because one molecular formula may be represented to two different types of substances in organic chemistry. So it's better you use their structural formula so that you can get better understanding. So structural formula indicates how the atoms are what? Arranged within the molecule of a substance. It is determined through various what? Spectroscopic methods. You understand? For you to see the structural formula, you need to use your eye with microscope and other things. You understand? So you use a special machine known as spectroscope. You understand? So you use special spectroscopic methods in order to determine the structural formula of an organic compound. It is more used for organic what? Compounds. I think this it is more useful for organic compounds than what? Molecular formula. It is more useful than molecular formula. Since a molecular formula may represent what? More than one what? Substance in organic chemistry. So these are examples of molecular formulas. This is ethanoic acid. Can you see the way it is arranged? It's telling us that ethanoic, ET, yes, N is for 2, is it not? Meaning 2 carbon what? Compounds. Oic acid, the carboxylic acid is what? COOH. So this is the functional group being shown. So you can easily see the functional group. This formula is the same as this. This one is the condensed form. So this is the alkyl group, and this is the what? Functional group. Is that clear? So this is the what? Alkyl group, and this is the what? Functional group. This is ethanoic acid. This is the structural representation of methane. You know that methane is what? CH what? 4. Is it not? This CH4. So the molecular formula for methane is what? Molecular formula for methane is what? CH4. Also, the empirical formula for methane is also CH4. But the structural formula representation is this, and it's showing us that this is carbon. Is it not? Bonded to what? 4 hydrogen what? Atoms. It's telling us now that this bond is not a right angle triangle bond. You understand? This bond is at an angle, and this angle is what? 109 degrees 28 seconds. You understand? So actually these bonds are made at an angle. They are not at right angle. These bonds are made at what? They are made at what? So it's making us to understand the structure of methane very well. So this is what we call spatial representation or three-dimensional representation of what? Of compounds, methane. You understand? So this is the same as this, but this is telling us how exactly it is done. So you have what we call tetrahedral arrangement of the bonds around the carbon atom at an angle of 109.28. You understand? 109 degrees at an angle of about 109 degrees. So you need to understand this. Structural formulas are very, very important for organic compound because they help you to understand more how the atoms are arranged. Unlike for inorganic chemistry or chemical compound, where the empirical formula, the simplest formula, and the molecular formula, which indicates the actual number of atoms, are important. Is that clear? So the additional thing for organic chemistry is that the structural formula is very, very important because it makes you understand the arrangement very well. Is that clear? Yes, welcome. There is a system of naming in chemistry. There is a system of what? Naming in chemistry. Just like if they want to name you, normally they name you have first name and second name, is it not? Happiness, Doma, is it not? Aisha or Isa. Aisha or Isa. That's Kogi State. Igala or Ibira. Yeah. So you have system of naming, first name, second name, you understand? In chemistry, there is a system of naming known as IUPAC nomenclature. Known as what? IUPAC nomenclature. IUPAC. Can you see it? IU, is it not? IUPAC nomenclature. Known as what? IUPAC nomenclature. You understand? It's a system of naming. That's the way they name things. They name chemical compounds. You understand? In that same way, you use IUPAC nomenclature for aliphatic compounds in chemistry, in organic chemistry. Is that clear? What is this IUPAC system of nomenclature? This is the International what? Union of Pure and Applied what? Chemistry. I stands for what? International. U stands for what? Union. P stands for what? Pure. A stands for what? Applied. C stands for what? Chemistry. IUPAC. International Union of Pure and Applied what? Chemistry. IUPAC. So it's a system of naming compounds where the name consists of what? A root, a suffix, and as many prefixes as necessary. Is that clear? So in IUPAC nomenclature for organic chemical compounds, we have a name consisting of a word, a root. You understand? A suffix and as many prefixes as what possible or necessary. So how do you get the root? The root is derived from what? By replacing hydrogen atoms with alkyl functional group or what? Multiple bonds, which we are going to illustrate here. This is a functional group, is it not? What functional group is this? This is a carboxylic acid functional group. This one is the Arachidonic acid, is it not? Similar, two of them are similar. This one is what? Alkyl or carboxylate. This one is what? Bromate or bromine as a functional group, and this is iodine as a functional group. So when this carboxyl group is coming as a suffix, it's starting the name. Suffix is when it starts. Prefix is suffix is when it comes last. Prefix is when it starts. Beginning, prefix, beginning, suffix coming at the end. Is that clear? So when this one is coming as a suffix, you end it with what? Carboxylic acid. But when it's coming as the prefix, you start it with what? You start with carboxy. The same thing with this. This ends with arachidonic acid. Like when you have arachidonic acid, that's the ending. This one doesn't come in suffix form. This is alkyl or what? Carboxylate. Now these ones, they cannot come in the end. You understand? They can only come in the beginning. You say bromo, you understand? Or iodo. Is that clear? You start it with them. You are going to demonstrate it with examples. Now, basic rules of naming organic compounds. What are the basic rules that you use in naming organic compounds? Number one is that you have to do what? Take the longest continuous carbon chain as the root hydrocarbon and name it according to the number of carbon atoms it contains. You understand? Adding the appropriate suffix and prefixes. Number two, number the carbon atoms in the root hydrocarbon from the end, which will give the lowest number to the suffix, and then the what? Prefixes. Number three, indicate the other constituents by prefixes preceded by numbers to show their positions on the carbon chain. And finally, number four, when two different alkyl groups are substituted to one organic compound, you have to name them with the one alphabetically, with the one with, you understand? Like if you have the one starting with E and M, the one with E will come first when they are more than one. So we are going to demonstrate these rules now. We are going to do what? Demonstrate these rules in naming an organic compound. We are going to name an organic compound. So I'm going to structurally indicate an organic compound, and you will name it for me. Please now. Let's indicate an organic compound and let's name it. So we have C. This is not right. We have CH3 bonded. Are you looking at that? Bonded to CH2 bonded to CH. Are we looking at that? Bonded to another CH3 and bonded down to CH3. Can you look at that structure? Can you look at that? So how do you name this? Are you going to start naming from here? Are you going to name this as 1, 2, 3, and what? 4. The first rule says take the longest chain, longest continuous chain as the root hydrocarbon and name it according to the number of what? Carbon atoms. And these are the carbon atoms. So take the longest. Don't take this. This one is the longest. It's short. It's composed of only 2. Is it not? So the rule says take the longest. This is the longest. So name this longest according to the carbon atom. So you have carbon atom 1, carbon atom 1, 2, carbon atom 1, 3, carbon atom 1, 4. Is that clear? Name only the what? Longest chain. You understand? This other one is an attachment. It's a methyl group attached. Is that clear? It's a methyl group attached. So with this naming, what can you call this? It's possible that you call it 3-methylbutane. It's possible that you call it what? It's possible that you call it 3-methylbutane. This is methyl, is it not? On which one is it? Is it on the 1 or 2 or 3 or 4? On the 3. So you can call it 3 what? Methyl. 3-methyl what? butane. Why do you call it butane? Because it's 4. Is it not? 1, 2, 3, 4. Can you see that? 3-methyl what? Butane. But you can also name it in another form. This is what? CH3, CH2, CH, CH3, and what? CH3. Tell me another way you can name this. Obeying this first rule, you can also name the longest chain as saying this is what? 1, this is what? 2, this is what? 3, this is what? 4. So if you name it like this, what is going to be the name? Is it 3 or 2? Where is the methyl group here? 2. So you can now say what? 2 what? Methyl. 2 methyl what? 1, 2, 3, 4. Butane. Huh? So who can tell me from the remaining rules which one it should be the correct one? Is it this 2-methyl butane or 3-methyl butane? Both of them have the same. So who can tell me the one? If you look at the second rule says number the carbon atoms in the root hydrocarbon from the end, which will give the lowest number to the suffix and then the word prefix. So which number? Is this the lower number or this one? 2 is lower. So the rule says number is in such a way that you will give the lower number to this suffix or prefix. So which one should be the right name for this chemical compound? 2-methyl what? Butane. 2-methyl what? Butane. So whenever you're given a chemical compound, look at the 2 chemical compounds. Is that clear? Check out the longest chain. Check out the what? That's what the first rule says. You understand? If you've identified the longest chain, start numbering. You understand? You can number from here to here or number from here to here. But how do you know the right one to be? The one that will give the suffix or the prefix the lowest what? Lowest number. Number 3 say indicate the other constituent. You've already indicated the other constituent is the methyl group, is it not? Indicate the other what? Constituent by prefix preceded by what? Number to show their position. This is the number showing the position of the methyl group. It's telling us that the methyl group is on the second what? Second carbon of the butane. Whereas this one is telling us that it's on the third carbon, and we know this is wrong because we need the one that will give the lowest number. Is that clear? And the 4th rule says when 2 different alkyl groups are involved, that you should start this thing. You understand? So if you have another alkyl group, this is only one alkyl group, methyl, added. Or maybe you have something like 2-methyl butyl, 1, 2, 3 pentane. You understand? 2-methyl butyl. So if you have another butyl added, let's say the form is a different compound, you're having something like 2-methyl butyl. Which one is supposed to come first, methyl or butyl? Butyl, it can only be 2 butyl before methyl because but is what? Alphabetically, but is more than this one. So you put the one that is up in alphabetically. You understand? So always check this. Always check this. Always check this. Is that clear? Is that clear? Yes, we talked about the formulas of a chemical compound that is organic. We said that every chemical compound has every organic chemical compound has 3 formulas. Number 1 is the empirical formula. Number 2 is the molecular formula. And number 3 is the what? Structural formula. We said for inorganic chemical compounds that the 2 formulas, empirical and molecular, are enough for you to identify that particular inorganic compound. But for an organic compound, you need the 3 formulas: empirical, molecular, and structural. And of importance for an organic compound is the structural formula, very, very important. And we said that the structural formula is very, very important because a compound may have one molecular formula but have 2 different structural formulas. And this can be explained through a phenomenon known as isomerism, which is what we are going to study today. The existence of compound with one molecular formula in two different structural forms or three different structural forms, depending on the number of carbon atoms in that very compound. And that brings us to this topic known as isomerism. But before then, stereochemistry is the study of the structure in 3 dimensions. So there is an aspect of chemistry known as stereochemistry, which simply involves the study of the structure of compounds in 3 dimensions, not 2-dimensional, not 1, but in 3 dimensions. If you're able to look at every compound in 3 dimensions, you discover that a particular compound can exist in various isomers. So what is this isomerism? Isomerism is the existence of 2 or more compounds, known as isomers, with the same molecular formula but different molecular structures. They have the same molecular formula, but they exist in different structures. You understand? A very good example is butane and 2-methylpropane. Butane and 2-methylpropane, 2 of them have the same molecular formula. But when you look at their structures, you see that their structures are different. This one contains how many carbon atoms? 1, 2, 3, 4. This one contains how many carbon atoms? 1, 2, 3, 4. So both of them contain 4 carbon atoms. You understand? They have the same molecular formula. But when you look at their structures, you see that the 2 of them are not the same. This is a simple straight chain butane, known as normal butane. Whereas this is what we call 2-methylpropane, which is isobutane. Can you see? Do you know why it is called 2-methylpropane? This is a methyl group. CH3 is a methyl group. And when you look at the long chain hydrocarbon, on which carbon atom is it the first, the second, or the third that the methyl group is on? The second. That's why it is called 2-methylpropane. 1, 2, 3. You understand? But if you look at them, they have the same molecular formula. They also have the same mass number, but the structures are different. You understand? So butane can exist in this form, normal butane, or in form of 2-methylpropane. So the ability of butane or any other organic compound to exist in different structures is what we call isomerism. And the more the carbon atom increases, the more you have isomers. Like here, for butane, we have how many isomers? 2 isomers. For pentane, we have 3 isomers. You understand? For hexane, we have up to 7 isomers. So the more the carbon atom increases, the more the number of isomers that we have. Exactly. So what do we call this different structural arrangement that we have? What do we call these different structural arrangements? What do we call them? Yes, Emmanuel. Yes, good one. Isomers. That's the name. Isomers. Really, this is it already. These different arrangements are known as isomers. All of them are isomers of one compound, known as what? Known as butane. So whenever you have this arrangement, we call it isomers. You look at them, they are having almost the same thing. Count the number of carbon atoms here. 1, 2, 3, 4. How many here? 1, 2, 3, 4. Count the number of hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Count the number of hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You understand? But then, the arrangements are not the same. You understand? And because the arrangements are not the same, that's what we will explain as what? Explain it as what? Isomerism. And JAMB is going to ask you the existence of 2 or more compounds with the same molecular formula but different molecular structure is known as what? Isomerism. It's known as what? Isomerism. The phenomenon is known as isomerism, or the different chemical compounds that are formed are known as what? Isomers. Is that clear? And this concept is explained under a branch of chemistry known as what? Known as what? Stereochemistry. The study of chemical compounds existing in 3 dimensions. The study of chemical compounds existing in what? 3 dimensions. Get down your notes. Continue from here. Yes, welcome. Today we are going to be looking at the different types of isomerism that we have. In the previous class, we said that the existence of 2 or more organic compounds having the same molecular formula is known as isomerism. It's known as what? They have the same molecular formula, but their structural formulas are different. And we say that it increases with increased number of carbon atoms. We say that butane has how many isomers? 2. Isn't it? Pentane has how many isomers? 5. Hexane has how many isomers? 7. Check your notes. Check your notes. You're writing notes. Make sure you're reading them. Now, there are 2 types of these. 2 further types of isomerism, known as geometric isomerism and what? Optical isomerism. Whenever you have an arrangement like this, are you looking here? Can you see this? If you have the substituent of the hydrogen, you know they're supposed to be hydrogen. You understand, for hydrocarbons. But when it is replaced by some other thing, that thing is known as substituent. And this time around, it is being replaced by what? Chlorine. If the chlorine are on the either side, can you see them on the either side? We call it trans. This one is on one side of the double bond. This one is on the other side of the double bond. Can you see that? We call it what? We call it what? But when they are on the same side like this, we call it what? Cis. We call it what? We call it what? Cis. 2 types of geometric isomerism. Trans or what? Trans or what? This one they are on this side, this one they are either on the up or either on the down together. They are known as what? Cis. The ones are on the other side, they are known as what? Trans. It is mostly common among alkenes due to what? Double bond. Due to what? Will this thing be possible for alkenes? Because alkenes has how many bond? Have how many bond? Alkenes. Alkenes have how many bond? Alkenes. We have alkanes, we have alkenes, we have alkynes. Alkanes have how many bonds? Alkenes have 1 single bond. Alkenes have double bond. Alkynes have what? Triple bond. Make sure you people are not fooling yourselves. Make sure you're reading your books. Make sure you're reading your books, because I've noticed that most of you are starting to fool yourselves instead of reading your books. If you're learning organic chemistry and you don't know how many bonds that alkanes and alkenes have, you know that you're deceiving yourself. Don't deceive yourself. When you come inside this place, read your book, make consultations that will help your life. Don't start looking around and doing things that are not important. You spend time on Facebook and other things instead of getting to read your book and you'll be writing in JAMB. You know that JAMB, they are writing very early this time around. They are supposed to start JAMB registration on Monday, 22nd. But because the book you're supposed to read is not yet available, that's why they postpone it. So any moment they will start registration. And once they start registration, the tension starts. And in 3 months' time, you write. So if you're not reading your book, you are simply deceiving yourself. And the question I just asked you now is very basic. Make sure you're reading your book. Geometric isomerism is common to alkenes because of the presence of what? Double bonds. Alkenes have double bond. Alkenes have single bond. Alkynes have triple bond. I was very explicit when I explained it. Now we look at optical isomerism. But before I go there, the definition, geometric isomerism is the existence of compounds with the same molecular formula but are not identical because of different spatial arrangement of the compound atoms. Different spatial arrangement. Here we are having them on the same side. Here we are having them on different sides of the double bond. The one you are having on different sides, we call them trans. Trans 1, 2, like chronomethane. The one we have on the same up, or down, down. We call it what? Cs. Is that clear? Now we look at optical isomerism, which is the existence of two or more compounds with the same molecular formula but with different configuration. And because of the molecular asymmetry, they rotate plane polarized light. So when you get light across to them, you see them rotate in a plane polarized light. Can you see this? This COO edge is now starting from where edge OO1C, as if you are putting a mirror, isn't it? So you put a mirror here, this is what you see. C here, C S3, S3C, edge, edge, O edge, edge O. You understand? Anyone that is rotated to the right, you call it dextro-rotatory, or you call it plus, or D slash. You understand? The one that is rotated to the left, we call it what? Level rotatory. Minus, or you say L hyphen. You understand? So those are the two possible types of what? Optical isomerism. It's either is what? Dextro-rotatory or what? Level rotatory. For geometric isomerism, it's either that is what? Trans or what? Cs. Trans or what? Trans or what? And it's mostly common with what? Because of the presence of what? Is that clear? Please get this note down. Read it very well. Read the organic chemistry we've done so far. Next class, we are entering into the actual classification of organic chemistry. We are going to be learning alkanes, how they are produced, their chemical and physical properties. Is that clear? We'll go to alkenes, how they are produced, their chemical and physical properties. We'll go to alkynes, how they are produced, their chemical and what? Physical properties, and also uses. We go to alkanoic acid, alkanols, and all of them one by one. You understand? But what we've done so far is the basis of organic chemistry. You're supposed to master them. Is that clear? Read them and master them. So once I get out of this class, I want to see your note pass so that I can cross-check it. Thank you. Yes, welcome. Today we're going to be looking at classification of organic compounds. Organic compounds are classified into two major classes. Number one is aliphatic compounds, and number two is aromatic compounds. Aliphatic compounds and what? Aromatic compounds. Those are the two major classifications of organic compounds. It's either that the organic compounds are arranged in chains. Are arranged in what? Chains. Just like what we are seeing here. It's either straight chain, branch chain, cyclic chains. You understand? So any organic compound that has this sort of arrangement is known as what? Aliphatic compound. So in subsequent classes, we are going to be looking at aromatic compounds. Aromatic compounds are the ones that have this sort of shape. Anyone that has benzene-like shape like this is known as what? Aromatic compound. You understand? Benzene and all its derivatives are known as what? Aromatic compounds. Whereas the ones that have straight chain, branch chain, or cyclic chain are known as what? Aliphatic what? Compounds. So those are the two broad classes of organic chemistry. So we said that organic compounds are classified according to the what? Molecular structure. That's the arrangement. Can you see the arrangement here? Straight. This is what? Branch chain. This is cyclic chain. So organic compounds are classified according to their what? Molecular structure. The arrangement of atoms in the molecules into what? Aliphatic or what? Aromatic compounds. So whenever it's coming in these forms, it is known as aliphatic. But when it's coming in form of benzene, it is known as what? Aromatic. Is that clear? Aliphatic compounds. These are compounds with chains. They are compounds with what? Chains of carbon atoms. Can you see chains of carbon atoms? With one or more branches. It can have branches as well. You understand? It could be straight chain and branch chain. When it is straight chain and branch chain, it is known as what? Acyclic compound. But it can also have ends joined to form a closed system or ring. When it is forming a closed system, can you see a closed system of carbon atoms? Can you see it? Whenever it's forming a closed system of carbon atoms, we call it what? Cyclic compound. Is that clear? So acyclic are the ones that have straight chain and what? Branch chain. Example of acyclic compound is pentane. This is pentane. The organic compound with 5 atoms. This is what? 2-methylbutane. 1,2 methyl. 2-methyl what? Butane. 1, 2, 3, 4. These two are examples of what? Acyclic compounds. They are acyclic aliphatic compound. But these ones that form closed ring, can you see the closed ring? They are known as what? Cyclic compound. Example is what? Cyclopropane and what? Cyclohexane. Is that clear? So organic compounds are majorly classified into 2 broad categories. We have the what? Aliphatic compound and the what? Aromatic compound. Aliphatic compounds are things like pentane and branched chain organic chemistry, as well as the cyclopropane, the acyclic compounds. Whereas aromatic compounds are derivatives of benzene. Derivatives of what? Benzene, which we are going to look at in subsequent classes. Is that clear? Yes, we said that we can classify organic compounds into 2. Aliphatic and what? Aromatic compounds. Aliphatic compounds are those organic compounds that have straight chains, branch chains, and cyclic what? Chains. Now we have another type of compounds known as aromatic compounds. And I told us that aromatic compounds are basically based on what? Benzene. They have benzene structure. Benzene is a 6 carbon atom. This is benzene. This is a benzene atom. You understand? It has how many carbon atoms? 1, 2, 3, 4, 5, 6. 6. You understand? With double bonds intermediate at intermediate. After every double bond, you have single, double, single, double, single. In a ring form. You understand? That is benzene. Is that clear? So any compound whose structures are based on the structure of benzene, they are all classified as what? Aromatic compound. And benzene is simply benzene has the formula C6H6, and it's simply a carbon ring what? Atom. Some of these aromatic compounds are derived from benzene. You understand? Some of them are derived from benzene. Can you see these ones? These are the 3 forms of structures of benzene. You can draw benzene to be this. You can also draw it to be like this. You can also draw it to be like this. You understand? So when you have benzene attached to some other thing, like here you have what? Ethylbenzene. This is a derivative of what? Benzene. All these ones are derivative of benzene. But there are also other forms that are not derived from benzene, but they have the same structure as benzene. So how do you know aromatic compounds? Any compound that has these 3 things, they must be what? Cyclic, in ring form. Can you see that all these ones are in ring form? Can you see? That's one thing you must look at before you can say that the compound is an aromatic compound. They must be planar. You understand? They must be contained inside one plane. Unlike the other aliphatic that would be tetrahedral. You understand? They must be planar. And number 3, they must have a system of what? 2n plus 6 n electrons. 2n plus 6 pi electrons. You understand? Or 6, 10, 14 electrons. That's their configuration must be in that range. So aromatic compounds can be benzene. Can you see benzene? This is benzene. These are the 3 forms of representation of what? Benzene. They can be derivatives of benzene. And examples of derivatives of benzene are what? Aniline, or you call it phenylamine, and what? Phenol. Phenylamine or aniline and phenol are all derived from what? Benzene. Is that clear? They are all derived from benzene. But they can also not be derivative of benzene. Others are not derivative of benzene. Example of the ones that are not derivative of benzene are these ones. Pyro. Can you see pyro? When it has nitrogen. You can also have what? Thiophane. Can you see thiophane? When it has sulfur. Or what? Furan. Can you see furan? When it has what? Oxygen. Can you see that? So these 3 structures are similar. Can you see? Always having two electrons. Can you see them? But when it is connected to nitrogen, it's called it pyro. When it is connected to oxygen, you call it furan. When it is connected to sulfur, you call it what? Thiophane. You understand? So these ones are not derivatives of benzene. They are not derivatives of benzene. But these ones are derivatives of benzene. Other examples of derivatives of benzene are what? Phenylamine or aniline and what? Phenol. Is that clear? So aromatic compounds can be derivative of benzene or non-derivatives of benzene, but they must have the same structure as benzene. And though their structure must be what? Ring form. You can see all of them are ring. They can be what? Planar in one plane, and they must have a system of configuration known as 2m plus what? 4. Is that clear? So if JAMB asks you which of the following is a derivative of benzene, or is not a derivative of benzene, or is a, if the JAMB asks you which of the following is a derivative of benzene, and they will put pyro, furanthiophane, and phenol, what will be the answer? Phenol, because phenol is a derivative of benzene. But these ones are having the shape of benzene, but they are not actually derivatives of benzene. But all of them are what? Aromatic compounds, because they are having what? Ring form, and they are what? In one plane, and they are having a system of electronic configuration 2m plus 4. Is that clear? So this is what we call aromatic what? Compound. Compounds that have the same structure as what? Benzene. And benzene is a 6-carbon atom with the formula C6H what? 6. Having this structure, we can represent it as this, or as this. So if somebody asks you to draw benzene, very simple. 1, 2, 3, 4, 5, what? 6. Is it not? The carbon atoms. Connect them together. Is that clear? And just put what? Circle inside this benzene. You understand? If you don't want to draw benzene that way, also say 1, 2, 3, 4, 5, 6. Understand? Connect all of them together and put double bonds at intermediate. This is also what? Benzene. If you don't want to draw it this way, also do 1, 2, 3, 4, 5, 6. Connect them together. Why are you using 6? Because benzene is a what? 6-carbon atom. You understand? Then connect each one to what? Edge, 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 edge. Then put double bonds at intermediates. Exactly. Which is this one. So you can draw benzene this way, you can draw it easily or this way. You understand? These ones are derivatives of benzene because this is a benzene added to an ethyl group. This benzene added to what? I can only count this group and chlorine group. That's why we have what? 2,4-dichloro, 2-chloro, dichloro, benzoic what? Acid. Is that clear? So take note of all these structures, make sure you master them. No derivatives of benzene like phenol and what? Aniline, know them. Also know other aromatic compounds that are not derivative of benzene like pyro, furan, and what? Thiophane. Is that clear? Is that clear? Thank you. Yes, welcome. Today we're going to be looking at hydrocarbons. Hydrocarbons are very, very important for us here in Nigeria because much of our revenue, our national revenue, is coming from oil, crude oil. You understand? So hydrocarbons are gotten from crude oil or from other sources like coal, you understand, or natural gas. But natural gas and crude oil are the major sources of our income here in Nigeria. You understand? So hydrocarbons is very, very important because from there you can get the fuel that cars use and everything. You understand? So we're going to be looking at these hydrocarbons. Hydrocarbons are organic compounds that are composed of carbon and hydrogen. Is that clear? Hydrocarbons are what? Organic compounds that are composed of what? Carbon and what? Hydrogen. That's why we call it hydrocarbons. Hydro stands for what? Hydrogen. Carbon stands for carbon. You understand? So any organic compound that is composed of hydrogen and carbon, hydrogen and carbon is known as what? Hydrocarbon. It has the molecular formula of CXHY. The molecular formula is what? CXHY, where X and Y's are what? Whole numbers. Is that clear? Example of hydrocarbons are methane. Can you see this? Methane, CH4. Another example is propane, C3H8. Another example is what? Benzene, C6H6. All these are examples of what? Hydrocarbons. Why are they examples of hydrocarbons? Because they are composed of what? Carbon and what? Hydrogen. Carbon and hydrogen. Carbon and hydrogen. Is that clear? Hydrocarbons are classified into aliphatic and what? Aromatic hydrocarbons. Aliphatic hydrocarbons are the ones that have straight chains or black chains, branch chains, or cyclic chains. Whereas aromatic hydrocarbons are the ones that are based on the structure of what? Benzene. Is that clear? What are the sources of hydrocarbons? If you want to make hydrocarbons, if you want to get hydrocarbons, what are those things that you use in getting them? Number one, the natural sources of hydrocarbons are what? Coal, natural gas, and what? Petroleum. Coal, natural gas, and what? Petroleum are the sources of hydrocarbons. And these natural sources of hydrocarbons are known as fossil fuel. They are called what? Fossil fuel. Why are they called fossil fuel? They are called fossil fuel because they are remains of plants and animals that have died over millions of years ago. You understand? And because you can burn them as fuels to produce what? Heat energy and other forms of energy. That's why you call them fossil fuel. Fossil fuels are just fuels that are gotten from remains of plants and animals that have died millions of years ago that you can burn to produce heat energy and other forms of energy. In these three types of sources, coal is a solid form of fuel, petrol is a liquid viscous form of fuel, whereas natural gas is in gaseous form. So we have the gaseous form, the liquid form, and the what? Solid form. The solid form is coal, you understand? The liquid form is petroleum. The gaseous form of fossil fuel is what? Natural gas. Now we look at petroleum, which I told you is the major source of income for Nigeria in form of crude oil, actually, the source, you understand? But this petroleum or crude oil can be used to produce fuel that our cars can use, you understand? Our generators in the house can use the fuel as well, you understand? So what is petroleum or crude oil? Crude oil is actually one of the major sources of fuel today. Is that clear? You can do what we call fractional distillation. You can do what we call what? Fractional distillation. To divide the crude oil into its various what? Mixtures, components. Is that clear? When we are learning separating techniques, we have various separating techniques. We have distillation, we have fractional distillation, we have sieving, we have evaporation, we have all of them, you understand? But the one that you use in separating petroleum mixtures is the one called fractional what? Distillation. So with fractional distillation, you can get the components of petrol or crude oil, such as PMS that you can use for the driving car and other things, you understand? After getting the volatile components, the less volatile components that can be broken down more to get other components using what is equation known as what? Cracking. You can use cracking to break down the less volatile components of petroleum to produce various other components of petroleum that are useful in poly products and in other spheres of life. Is that clear? So first of all, what you do to the crude oil is that you do what we call what? Fractional what? Distillation to get some of the volatile components. You get some of the what? Volatile components like what? PMS and other ones. You understand? PMS, premium. This one is used for in driving cars. To get other further products, you do what we call cracking. You understand? So I'll be explaining these processes of fractional distillation of crude oil as well as cracking in subsequent classes. Is that clear? Thank you. Yes, welcome. Petroleum, crude oil. After distillation, after fractional distillation. I told you that to separate crude oil into its various components to get fuel, kerosene, and other things, it needs to undergo a separating technique known as what? Fractional what? Distillation. After fractional distillation, there are some distillates that will not be good enough for petrol. You understand? Because they contain molecules of very high molecular weight. And you need to get them down, you need to cut them down to form smaller ones, to form alkenes, which have a high octane number, which can be used for petrol or fuel. You understand? What process can you use to bring down large molecular hydrocarbons to smaller molecular hydrocarbons? That process is known as cracking. That process is known as what? That process is known as what? Cracking is the breakdown of or the composition of larger molecules into what? Smaller molecules. By the action of what? Heat. By the action of what? You must apply heat to break the what? Larger molecular hydrocarbons to smaller molecular hydrocarbons. This heat you are applying is to the tune of temperature of what? 1000 degrees Celsius and what? High pressure. And what? To produce desirable petrol fuels for what? Motor engines. You understand? The essence is for you to produce desirable fuels for what? Motor engines. You can also have what we call catalytic cracking. If you don't want to take it to a high temperature as big as 1000, you understand? And if you want to produce mostly alkanes of high octane number, you use what we call catalytic cracking, which is done in the presence of what? Silica alumina catalyst at temperatures of about what? 450 to 550 under slight what? Pressure to yield mostly what? Alkenes, good for what? Motor fuels, petrol, and of what? High quality. So if you want the quality to be very high, you use the method known as what? Catalytic cracking. So when you are doing cracking in the presence of catalysts like silica aluminum, call it catalytic cracking. But if you are doing cracking in the presence of only what? Heat alone, you call it what? Thermal cracking. You call it what? So there are two types of cracking: thermal cracking, the one done by heat, and catalytic cracking, the one done using catalyst, silica aluminum catalyst. Is that clear? Now there is another method of producing very good fuel. We call it reforming. We call it what? If you want to produce fuel of high quality with very good octane number, you use what we call what? Reforming. We call it catalytic reforming. And this is the conversion done by increasing the proportion of what? Branch chain hydrocarbons, which yield high octane petrol. It is an isomerization process that takes place in the presence of what? Oxides of silicon and aluminium as catalysts to improve petrol's anti-knocking activities. The feedstock is naphtha. So if you want to produce fuel of very high quality that will not be knocking your engines when you use them in motor cars, you use what we call catalytic reforming. And this catalytic reforming simply means rearrangement from straight chain hydrocarbons to branch chain hydrocarbons. From what? Straight chain hydrocarbons to what? Branch chain hydrocarbons. There are two types of reforming. You can have aromatization and isomerization. Aromatization simply means converting cyclic alkanes through dehydrogenation to aromatic hydrocarbons. You understand? Cyclic alkanes, converting them to what? Aromatic hydrocarbons like benzene and its derivatives. You understand? That is called aromatization. Whereas isomerization is conversion of straight chain alkanes into isomeric what? Branch chain. From straight chain to what? Branch chain. That is what? Isomerization, which is also a form of what? Catalytic cracking. Is that clear? So if they ask you what are the two ways you can produce better fuels, you can use what we call what? And what? Cracking and what? Reforming. Those are the two ways. And cracking is of two types. Thermal cracking, the one with heat, and catalytic cracking, the one with catalysts like silica aluminum. Is that clear? Reforming is of two types. Conversion of cyclic alkanes to what? Aromatics, known as aromatization. Or conversion of straight chain alkanes to what? Branch chain alkanes, known as what? Isomerization. Very important, take note. Yes, we are going to be looking at octane number system. If you want to know the quality of your petrol that you want to use for your car, or the petrol that you produce in the refinery, if you want to get the quality, its ability to work very well in car engine without causing knocking, if you want to check that ability, you need to check the what? Octane number. You need to check the what? You use octane number to check the quality of your petroleum, the quality of your petrol. You understand? And what is this octane number? This is a measure of the grade or quality of petrol according to the percentage of heptane. The percentage of what? Heptane. Heptane has the octane number of 0. So when you check the percentage of heptane to that of 2,2,4-trimethylpentane, which has the octane number of 0 in a mixture, when you check this percentage, you use it to calculate the what? Octane number. This is tested in a calibrated standard engine. So you check it in a calibrated standard engine. You understand? So octane number is simply checking the percentage of heptane to what? 2,3,4-trimethylpentane. Why? Because heptane has the octane number of 0. And 2,2,4-trimethylpentane has the octane number of what? 100. You understand? So when you test this in a standard calibrated engine, you check the what we call the octane number. Now this is heptane. This is the structure of heptane with octane number 0, and this is the structure of 2,2,4-trimethylpentane, also known as isooctane, with the octane number what? 100. You understand? So when you have a petrol having octane number of around 100 or 92 or 89, it has very strong quality. But when you have the one having octane number of 0, 1, 2, minus 20, it has very what? Low quality. Now, if you look at all these hydrocarbons, can you see propane? The octane number of propane is also what? 100. That of butane is 92. That of pentane is what? 61. So you can see propane, butane, and pentane can function as a very good petrol. Is that clear? Whereas hexane, heptane, and nonane with octane numbers 25, 0, and 40, minus 45 will work as a very bad fuel for your cars, isn't it? Because they are going to be causing what? What will they cause? What will this low quality fuel cause? What will they cause in your engine? They will cause knocking. They will cause what? They will cause your engine to knock. So you don't need fuels that have low octane number. Use the one that have what? High octane number. So much of your fuel should contain propane, butane, and what? Pentane, and not hexane, heptane, and what? Nonane. Is that clear? So as the molecular mass of the hydrocarbon is increasing, the octane number drops. You understand? That's why you need more of branch chain. You need more of what? Branch chain hydrocarbons. If you want to produce anti-knocking fuel, if you want to produce what? Anti-knocking fuel or petrol, you need more branch chain than what? Straight chain. You need more branch chain than what? Straight chain. Why do you need more branch chain than straight chain? Because straight chain hydrocarbons, they have very low octane number, so they will cause knocking in your engine. But branch chain, can you see the branches? They have very high octane number, so they are very high quality fuel. See that? So the one that has high octane number, which is around 100 or thereabouts, is very good for the engine. Whereas the one that has low octane number is bad for your engine. Is that clear? So octane number is simply the measurement of grading, which is calculated by checking the percentage of heptane to 2,2,4-trimethylpentane contained in a mixture of fuel. Is that clear? And it is tested in a what? Calibrated standard engine, so that you know the octane number. Whether it's measured from 100 to what? 0. So the fuel having octane number of 92 and the one having octane number of 3, which one is better? 92. So 92 is better. So you can also have octane number less than 0. Can you see that? Because this one is having minus 45, so it's not actually to 0, but actually you start from 100 down to minus. Is that clear? Is that clear? So the fuel that has the highest octane number is what? Can you see it? 2,2,4-trimethylpentane. Also, propane has octane number of what? 100. Whereas heptane has 0. Can you see that? Heptane has octane number of what? 0. That means heptane is not good for your car engine. Is that clear? Is that clear? So know this, very, very important. And check this. The higher the molecular mass of the hydrocarbon, the lesser the what? Octane number. Is that clear? Is that clear? So 2,2,4-trimethylpentane can also be called what? Isooctane. And it has the what? Octane number of what? 100. And also branch chain hydrocarbons, they always have better octane number than straight chain. You understand? The straight chain, they have very less octane number. That's the Yes, we said that there are two types of organic compounds, the aliphatic and the aromatic compound. We said that the aliphatic are the ones that are straight chain, branch chain, or even cyclic. And the aromatic is the ones that look like benzene. So this very aliphatic, there are different types. You have the single bonded ones, which have carbon atoms that are bonded singly to other carbon atoms and hydrogen. Those ones are known as alkanes. They are known as what? alkanes. They have single bond. Because they have single bond, they are said to be saturated. Please close that window for me so that the noise will not. They are said to be what? Saturated. Once they are having only single bond in the molecule, they are said to be what? Saturated. So alkanes are aliphatic hydrocarbons that contain only what? Single bond. That contain only what? Single bond, and therefore are saturated. In subsequent classes, when we'll be learning about alkanes or alkynes, those ones have double bond and triple bond respectively. Those ones are said to be unsaturated. They are said to be what? Unsaturated. So alkanes, these are saturated aliphatic hydrocarbons with molecular formula CnH2n+2. Very, very important molecular formula you need to know. JAMB will ask you, which of the following has this molecular formula? They will put it CnH2n+2. Then they will give you options: alkenes, alkynes, alkanoic acid, alkanes. You should be able to know their molecular formula. You understand? Alkanes, they have their own molecular formula. Alkynes have, alkanoic acid have, esters have, ethers have. So this is the molecular formula of alkanes, CnH2n+2. Here, all the carbon atoms are tetrahedrally bonded to the hydrogen and other carbon atoms. You understand? Using single bonds. They are very stable compounds, since all the 4 valence electrons of each carbon atom in the alkaline molecule are used up. There is no free electron. You understand? All the electrons are used up. That makes them to be saturated and to be stable. That makes them to be what? Saturated and to be stable. And these are the first 3 members of the alkane group. Is that clear? We learned about homologous series, isn't it? Which are a series of members having similar properties. So alkane is one of those homologous series. We have alkenes, we have alkynes, we have the rest of them. So these are the members of alkanes. Alkanes. The first 5 members. The first member is having 1 carbon atom, and the name is what? Methane. The name is what? With this formula, CH4. Who can tell me how we came about this formula? Who can tell me how we came about this formula? Look at the general formula and tell me how this formula is stated. Are you looking at the general formula? If we have in methane, what number of C do we have? 1, 2, or 3? 1. So if you have 1 for methane, this formula would be C1H2 times 1 plus 2. C1 is the same thing as saying what? C. Then H. 2 times 1 is what? 2 plus 2. Can you see? That's how we got methane. For ethane, what is the carbon atom? How many carbon atoms? 2. So we are going to have, using this formula, C2H2 times 2 plus 2. So we now have what? C2. 2 times 2 is what? 4 plus 2. We have H6. Can you see that? If we are doing for propane, propane is how many carbon atoms? 3. So using the same formula, C3H2 times 3 plus 2. I will now have C3, 3 times 2, 6 plus 2. See that? So all of them are following the same formula. That's why we call it homologous series. Homologous series is simply a series that has the same formula and have CH to being added. You understand? That's how we came about butane, even pentane. Is that clear? So I'm going to give you assignments now. You write 2 molecules, 2 molecular formula of this methane group, So you're going to write, you have methane, ethane, propane, butane, and pentane. What's the next one? Hexane. So you like the molecular formula for hexane and heptane. Heptane is this heptane or heptane? 7 is heptane. No, it's not heptane. So you do for the 2, then you do for the 9th and 10th, then him you will do for the 11th and 12th. So quickly come and write it now. Let me see them. Yes, we are going to look at the first member of the alkane group. The first member of the alkane homologous series. The name is methane. The name is what? Methane. Methane is the simplest alkane. Why? Because it has only one carbon atom. You understand? One carbon atom. And that carbon atom is surrounded by how many hydrogen atoms? How many hydrogen atoms? 4. You understand? So if the middle is the carbon, hydrogen, 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 4. You understand? All connected in a single bond. All connected in a what? Single bond. So methane is the simplest member of the alkane series. The molecular formula of methane is what? CH4. You know how we came about CH4? By using the formula CnH2n plus 2, isn't it? Where n stands for how many? 1, because it's methane. It is the component of petroleum gas, you understand, and natural gas. Natural gas and petroleum gas, I told you, is one of the things Nigeria used to get their revenue, isn't it? So natural gas and petroleum gas, one of their major components is what? Methane. It is produced during the decomposition of plant matter in the absence of what? Air. When plant matter is decomposed in the absence of air, we get methane. It is also called marsh gas because it is given off in swamps. If you go to those swampy areas, swamps, that gas coming out is methane. It is also called fire down when it is found in poorly ventilated coal mines. Do you know where they call coal mines? Do you know Enugu State? They have coal deposits. So the mine that gets out this coal, if it is poorly ventilated, you will have what we call methane. You will have what? Methane, and it's very bad. And it causes explosion. This damn fire dam methane causes what? Explosion. It is the main cause of explosion in coal mines. How do we prepare coal? How do we prepare methane in the lab? Methane is prepared by heating anhydrous sodium ethanoate with alkali, usually soda lime. Is that clear? So this is anhydrous sodium ethanoate. Can you see it? Sodium ethanoate. Sodium ethanoate. Anhydrous simply means it doesn't contain water. When it reacts with this sodium hydroxide from soda lime, it will give what? Sodium carbonate and what? Methane. Sodium carbonate and what? This is methane. This is how methane is produced in the lab. By heating, you must apply what? Heat. Heating what? Anhydrous what? Sodium ethanoate with what? An alkali. Say soda lime. This is from soda lime. So when you react the two of them, you get sodium carbonate and what? Methane. Now, the other alkanes are also prepared in similar way by heating the appropriate what? Sodium salt. This must be a sodium salt. If this was not this, we would have gotten another type of organic aliphatic alkane here. It could be butane or anyone, depending on the sodium salt that you use. Is that clear? What are the physical properties of methane? How do you know methane whenever you see it? How? Physically, how can you identify methane? Number one, it is a colorless and odorless gas. So if you are looking for it to have color or have odor, it doesn't have color, it doesn't have odor. You understand? Methane gas does not have color and odor. It is slightly soluble in water. It is only slightly soluble in water. That means it does not dissolve in water easily. Is that clear? It is less dense than air. So if you have air here, you most likely get methane on top because the density of air is bigger than that of methane. It has no action on litmus paper. It has no action on what? Litmus paper. That means it's a neutral substance. Is that clear? So these are the physical properties. Number one, methane is a colorless, odorless gas. Number two, methane is only slightly soluble in water. Number three, it is less dense than air. Number four, it has no action on litmus paper. Is that clear? Is that clear? Yes, welcome. We're going to be looking at the chemical properties of methane. Methane, as a member of alkane, has two major chemical properties. Number one is combustion reaction or combustion, and number two is chlorination, or you call it substitution reaction with chlorine. Is that clear? So two major types of reaction that occurs in every methane. Combustion, and this combustion simply means the burning in air or oxygen of methane to produce steam, carbon dioxide, and a lot of heat. Is that clear? So combustion, methane burns in air or oxygen with a paired non-luminous flame to produce steam, carbon dioxide, and a lot of heat. The general combustion formula for all alkane is not only methane that undergoes combustion. Every other alkane do the same thing. So this is the general molecular form, general equation of combustion: CXHY plus X plus Y over 4 O2 to give Y over 2 H2O plus HCO2. You understand? The value for X for methane is 1. You can see it here. And the value for H for Y here is what? 4. So if you replace X and Y with 1 and 4 in this equation, you get this simple equation of combustion of methane. Methane plus oxygen to give steam and carbon dioxide. A mixture of methane and air or oxygen may explode violently when ignited. It is the main cause of explosion in coal mines. So if JAMB asks you which of the following is the main cause of explosion in coal mines, you should be able to say that it is the what? Reaction between methane and air or oxygen. When it is ignited, it will cause a very violent explosion. Now we look at the second chemical property of methane, which is chlorination reaction. Chlorination reaction is a sort of substitution reaction whereby the hydrogen atom in the methane is replaced by chlorine. So chlorination, methane reacts with chlorine in the presence of ultraviolet light. The ultraviolet light acts as catalyst to yield a mixture of products. It is a substitution reaction. A substitution reaction is the direct displacement of an atom or group by another atom or group. And in this case, which atom displaces which the other? In this case, chlorine will displace what? Hydrogen. So what happens is that the chlorine molecule is broken into two. You understand? So one of the chlorine will now go and displace one of the hydrogen here. Instead of being CH4, it's now CH3. You understand? Meaning that one of the hydrogen here has gone here to form HCl. Is that clear? And so on and so forth. What are the uses of methane? What can you use methane to do? Why is this so important that we are studying methane? Because it is useful. Methane is mainly used as fuel, either by itself or mixed with what? Other gases. So it can be used as fuel. Number two, it is used in making hydrogen, carbon black, carbon 4 sulfide, alkynes, hydrocyanic acid, trichloromethane, also known as chloroform. You can see that there are a range of products that you can use methane to produce. Can you see that? That's why it is very important. This chloroform is an anesthetic that is used in hospital and for health. You understand? So you can use methane to produce some of these things, and that makes methane very, very important. You see that methane is mainly used as what? Fuel. So one of the major components of your petrol gas or natural gas is what? Methane. So methane is very, very important. So when you are handling methane, you have to be careful because it can explode violently. You understand? That's the caution you should take. But methane is very, very useful because you can use it to produce a range of products like what? Hydrogen, carbon black, carbon 4 sulfur, many things. And you can also use it as fuel. Is that clear? Hello, welcome. We said we have in the homologous series, you understand, we have the alkanes that have only single bonds, isn't it? We have the alkenes that have double bond. We have the alkynes that have triple bond. Then we have the alkanoic acid, the alkanos and the alkanals and the rest of them, isn't it? And we've already treated the alkanes that have single bond. Today we're going to be treating the alkenes that have what? Double bond. You understand? They are said to be unsaturated. They are said to be what? Unsaturated because of the presence of electrons caused by the double bond. and because of that, they are more reactive than the alkanes. We say that the alkanes are very stable because they are saturated, but these ones, they are not saturated. So they try to be saturated like the alkanes, thereby causing them to be more reactive than the alkanes. So alkanes, these are homologous series of hydrocarbons with the general molecular formula of what? CnH2n. Cn what? H2n. So if n is equal to 2, 2 is if ethane, but so if n is equal to 2, this thing will be what? C2H 2 times 2, 4, but so we have what? C2H what? 4. That is ethane. That's how we got this ethane. Can you see it? C2H4. Ethane. That's the impact name. Whereas the common name is what? Ethylene. Common name is the name used by chemical engineers or chemistry people. People that are dealing in chemical. People that are dealing in chemicals. You understand? Now, if n is 2, is 3. If n is 3, this one is 2 bar. If it is 3, it will be C3H 2 times what? 3. Giving us what? C3H what? 6. C3H6. And the name is what? Propene. And the common name is what? Propylene. Is that clear? If n is 4, you will have what? C4H2 times 4. Giving us what? C4H8. And the C4H8, the name is what? But1N or what? 1-butylene. Is that clear? Which is also the formula for this second one. It's just that the structure are different. But2N or 2-butylene. Is that clear? If it is 5 here, we have C5H2 times 5, which will give us C5 what? H what? 10. C5H10. The name is what? Pent1N or what? Pentylene. Is that clear? So that's how you get the subsequent members of the alkane group, because their general molecular formula is what? CnH2n. They contain 2 hydrogen less than the what? Alkanes. Why do they contain 2 hydrogen less? Because of the double bond. And they are what? Unsaturated, since they contain carbon-carbon what? Double bond. Now, the first 3, can you see the first 3? Ethane, propene, but1N, and what? Butene. No, but1N and butene, they have the same molecular formula, you know that. So these first 3 are colorless. They are what? They are colorless gases. These first 4 again, they are colorless gases at ordinary what? Temperature and pressure. But the next 13, after these 3, the next 13 from pentylene down to C17 are what? Liquids. While the higher members are what? Solids. Is that clear? Alkenes, sorry. Alkenes tend to bond with a more luminous and smoky what? Flame. We said that one of the physical properties of alkanes is that they bond with non-luminous flame. But this one bond with a more what? Luminous and smoky flame than the corresponding what? Alkanes, since they contain greater percentage of carbon. Why is it that they bond in a smoky flame or luminous flame? Because they contain greater percentage of what? Carbon. The electrons in the double bonds makes them chemically more what? Reactive. They are more reactive than the alkanes because of the presence of electrons in the double bonds. Is that clear? And this is the first 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The first 5 what? Members of the what? Alkanes. You understand? The other one started with methane. Alkane started with methane, with C1, isn't it? But this one is not starting from C1. It's starting from C1 to 2. So this is the first 5. We have the ethane, propene, but1N, but2N, and pent1N. And their common names are what? Ethylene, propylene, 1-butylene, 2-butylene, and what? Pentylene. You understand? So basically what I want you to understand about alkenes is that they have the general formula CnH2n. They have the general formula what? CnH2n. They are unsaturated. They are what? Unsaturated. Because they have how many bonds? Double bond. Double carbon to carbon bond. You understand? And whenever there is double bond, there is presence of valence electrons, which makes them to be more reactive than the corresponding alkanes. Is that clear? They bond with more luminous and smoky flame, unlike the alkanes that bond with non-luminous flames. They are more reactive than the alkanes. Is that clear? Is that clear? Yes, welcome. We'll take a look at the most important alkene. You understand? Ethene is the most important alkene, and it is the constituent of many of the cracking products that we use for fuel. Is that clear? Ethene is very, very important. So we'll take a look at the ethene and see how we can produce it. Ethene is the most important alkene and one of the main products of cracking of gas oil fraction of petroleum. We learned about cracking, isn't it? We said that cracking is the breakdown of larger molecular formula organic compound into smaller ones through the use of heat or catalyst. You understand? So when these larger molecules are broken down, what you produce mostly is ethene. Is what? Ethene. I will give an example. This is C17. Can you see 17? It's very high. So when you break it down, you get this one, C8. You get ethene. Can you see ethene? This one is how many? 1. This one is how many? 1. But ethene is how many? 3. Meaning that you produce more molecules of ethene after cracking. Is that clear? Now, how do we produce this ethene in laboratory? How do we produce ethene? First of all, we know that ethene is C2 what? H4. That's the molecular formula of ethene, C2H4. How do we get it in the lab? We get ethene by heating ethanol with excess concentrated what? Tetraisosulfate 6 acid at a temperature of what? 170 degrees. And this ethanol and tetraisosulfate 6 has to be mixed in the ratio of what? 1:2. So you have 1 mole of ethanol mixed with 2 moles of what? Tetraisosulfate 6 acid. It is a two-stage reaction, you understand? First of all, you form something that later decompose to form the ethane. Is that clear? Is this in 4 or 5? 4. Or is it a mistake? Is it 5? It's ethane. Ethane should be 4. So it's a mistake, please. You understand? This is the formula for ethane. This is ethane 4. You understand? And this reaction is simply dehydration. Can you see that oxygen, water is taken out? You understand? In this ethanol, when you dehydrate it by taking out water, you see the OH goes out with this so that you have only what? C and H. You understand? And the reaction has to be done in the presence of concentrated what? H2SO4, concentrated tetraisosulfate 6 acid. What are the physical properties of ethene? How do you recognize ethene when you see one? Number 1, it is a colorless gas with a what? Faint, sweety smell. So when you come across a gas that has a faint, sweety smell, but it is still colorless, you suspect that the gas should be what? Ethene. It is slightly less dense than what? Air. So if you keep air and keep ethene, ethene will be on top because it's less denser. It has no action of what? Litmus paper, showing that it is neutral, isn't it? It is sparingly soluble in what? Water. That means it doesn't dissolve in water so easily. It is only slightly or sparingly soluble in water. Caution, in the process of producing ethane, you understand, you need to put the reaction mixture inside a flask. The flask will contain ethanol and what? Concentrated what? H2SO4. You understand? In order to produce what? Ethene. If ethene is produced, you need to insert what we call, you need to insert an empty flask before you connect it to sodium hydroxide, and then where the product comes. You understand? When concentrated H2SO4 and ethanol reacts, when ethanol and concentrated H2SO4 react, what will produce? Ethene. You understand? This ethene that you produce, you need to pass it through sodium hydroxide to remove any impurity. You understand? But you don't need to connect it directly to this one. You need to insert an empty flask first. Because if you connect it, this thing will suck the sodium hydroxide and it will not give you the product you want. You understand? So you need to connect an empty flask first before you now connect the sodium hydroxide. So when the gas passes through here, all the impurities will be taken out before the pure ethene will enter here. That's why we say caution. In the preparation of ethene, an empty conical flask is inserted between the what? Sodium hydroxide. Between the sodium hydroxide and the reaction mixture. This is the reaction mixture. You understand? In order to prevent sucking back of the what? Sodium hydroxide. And what is the function of sodium hydroxide in this place? To remove what? Gaseous impurities. Is that clear? So this is the structure of the production plant. You understand? First of all, you have your what? Reaction mixture. You understand? Connected to what? Empty what? Conical flask. Then connected to what? Sodium hydroxide. Then connected to the what? Where you get your output. So in this reaction flask, you have what? Corn, S2SO4 and what? Ethanol. When they react together, they produce ethene. That ethene will pass through here, then pass through sodium what? Hydroxide to remove any impurity before it will not enter here, so that you get your pure what? Ethane. You understand? So you connect this empty flask in order that this sodium hydroxide will not be sucked back into the system. Is that clear? So you study this very well. Ethane is the most important alkene because it is one of the major products of what? Cracking of gas oil fraction. You can use it as fuel. Is that clear? So it is prepared by heating ethanol with excess what? Concentrated tetraoxosulfate 6 acid at a temperature of 170 degrees Celsius in the ratio of what? 1 is to what? 2. So there will be more tetraoxosulfate 6 acid than ethanol. And this is the general reaction. And this general reaction simply shows us that this reaction is actually a dehydration reaction that takes out the water molecule part of the ethanol in order to produce the what? Ethane in the presence of concentrated H2O. And physical properties of ethane is that it is a colorless gas with faint sweety smell. It is slightly less dense than air. It has no action on litmus paper, and it is sparingly soluble in water. Yes, let's look at the chemical properties of ethane. We say that the two major chemical properties of ethane is combustion and substitution or chlorination, isn't it? But for ethane, the three major chemical properties are: number one, combustion; number two, addition reaction; and number three, polymerization. You understand? So let's look at these three characteristics. Combustion. Ethane burns more than ethane. You know why? Because it has greater percentage of carbon. So this combustion is simply reaction with air or what? Oxygen. Combustion of ethane. Ethane burns readily with what? Oxygen or air with a what? Luminous or smoky flame to be oxidized. Okay, please. The right word is to be oxidized to what? Water and what? Carbon dioxide. When ethane burns in air or oxygen, it is oxidized to what? Water and what? Carbon dioxide, as shown in this equation. This is ethane reacting with oxygen to give what? Water and what? Carbon dioxide. It forms explosive mixture when mixed with oxygen and what? Air. You understand? It burns with a more luminous flame because it has more carbon percentage, unlike ethane. Number two, addition reaction. What is addition reaction? Addition reaction is simply the direct addition of an attacking reagent across the double bond or triple bond of an unsaturated compound to yield a saturated product, or at least one in which the degree of saturation is increased. You understand? And this attacking reagent that causes addition can be hydrogen, halogens, hydrogen halides, chlorine or bromine water, oxygen or air, tetraoxosulfate 6 acid, or tetraoxomanganate what? 7. Any of them can be the attacking reagent. And what do? Whenever an attacking reagent like chlorine water or bromine water or tetraoxosulfate 6 acid or hydrogen or halogen, whenever it attacks ethane, it turns it from an unsaturated compound of double bond to a single bond saturated compound of maybe ethane. Or at least if you attack something like alkyne. You understand? When this attacking reagent attacks alkyne, it might produce an alkene which is unsaturated, but at least it has greater percentage of saturation. Is that clear? So whenever an unsaturated compound reacts with an attacking reagent, it will produce a saturated product or a product of higher degree of what? Saturation. Is that clear? So this is an example. What compound is this? This is ethane. You understand? When you add something like hydrogen or any of these reagents, it will form ethane. This is ethane. You understand? The double bond has gone. No more, it's now a single bond. You understand? So it moves from unsaturation to saturation. Polymerization. Polymerization is a process whereby two or more simple molecules are linked together to form a much larger molecule. Who can tell me the opposite of polymerization? The opposite of polymerization. Polymerization is linking of simple ones to form bigger ones. What of the breakdown? Cracking, thank you. Cracking is the breakdown of bigger ones to form simple ones. You understand? So it's the opposite of this one. You understand? To form larger molecules. Ethane and its derivative undergo polymerization to form important compounds like what? Polyethene. When you combine plenty ethene, you form what? Polyethene. Or what? Polychloroethene. When you combine plenty chloroethane, you form polychloroethane. You understand? And this polyethene and poly, all those things, they are used in making plastic bags. You know these plastic bags you use in carrying things. They are made from there. So that's why it's very, very important. Uses of ethene. What can we use ethene for? Ethene is the main source or raw material for plenty important organic compounds like ethane. You can use ethene to produce ethane, to produce ethanol, to produce ethanoic acid, to produce epoxy ethane, to produce ethane 1,2-diol, to produce tetraethylene. This is very important additive. To produce polyethylene, as we've already mentioned. To produce synthetic rubber known as what? Styrene butadiene rubber. To produce polystyrene, also known as polyphenylethane. You understand? Also, in small quantities or small concentration, ethane can be used in agriculture to help hasten ripening of what? Fruit. See all those fruits that you buy. Some of them, they say this one was not naturally, this one did not ripe naturally. You understand? You can go and buy plenty mango, or you just spray small quantity of less concentration of ethene on it. It will ripe faster. You understand? You can use it in agriculture. So ethene is very, very important. It can be used as a source of raw material for plenty important organic compounds like ethane, ethanol, ethanoic acid. You understand? SBR, which is synthetic rubber. Thiocol, many of the things you use in producing all these plastic bags, most of them are gotten from ethene. That's why ethene is very, very important. That's why we have to learn about it. So the major properties of ethene are what? Major chemical properties: combustion, addition reaction, and what? Polymerization. Combustion is burning in air to produce water and carbon dioxide. Addition is coming together to turn from unsaturation to saturation. Whereas polymerization is coming together to form longer chain of higher molecular something in order to produce polyethylene, which are very, very useful in polyproducts company. Is that clear? Thank you. Yes, welcome. We are continuing our studies on the homologous series of organic compounds, isn't it? First of all, we did the alkanes. We did the what? I would say that the alkanes have single bond and they are saturated, is it not? Then we did the what? Alkenes. And we say that they are unsaturated because they have what? Double bond. Today we are going to look at the alkynes, the ones that have how many bonds? Triple bond. You understand? And they are even more unsaturated than the alkenes. You understand? Because of the triple bonds. So alkynes, these are homologous series of unsaturated hydrocarbons with the general molecular formula of what? CN H2N minus 2. Take note. Cn H2N minus what? So let's say we are calling n to be 2. You know, n represents positive whole numbers. So for if the n is what? 2, isn't it? So we'll now say C2 H 2 times what? 2 minus what? 2. What will that give us? It will give us C2 H 2 times 2, 4. 4 minus 2, 2. C2 H2. And that is what we have here, C2 H2, is it not? And it is called what? A time. And you can see the way it is drawn. CH, triple bond CH. Why is it CH, CH? Because there are how many C's? 1, 2. How many H? 1, 2. And the common name is what? Acetylene. Is that clear? I told us that the common name is the name. The common name is the names that people that are in the chemical industry normally call it. You understand? So if you go to a big chemical factory, you may ask for ethyne. They might not actually know what ethyne is. You understand? Because the name they use is acetylene. Is that clear? But as somebody that is studying chemistry, you're supposed to know this. Now we look at the second one. The second one is what? Propyne. And we say that for prop, how many carbon atoms in prop? 3. So now we replace this with 3. We now say C3 H2 times what? 3 minus what? 2. So what will this give us? It will give us C3 2 times 3 6 minus 2 4. C3H4. Can you see it? C3H4. And the name is what? Propyne. And the common name is what? Methyl acetylene. Is that clear? So the next one is C4. The name is what? But1I. And the common name is what? Ethyl acetylene. The next one is an isomer of the upper one. You understand? So still C4. But2I. And the common name is what? Dimethyl acetylene. The next one is C5. And it's what? Bent1I. And the common name is what? Propyl acetylene. Is that clear? So you can always get the rest of them by substituting N with 1, 2, 3 and the rest of it. Is that clear? Now we look at this, we say that they contain carbon to carbon triple what? Bond, 3 bonds. Is that clear? Can you see that all of them have 3 bonds? Can you see? So they contain carbon to carbon what? Triple bond. Thus, they show higher degree of what? Unsaturation. If they ask you, alkenes and alkynes, which one is more unsaturated? You say that it is alkyne. Both of them are unsaturated because they don't have single bond. But this one is more unsaturated because it has 3. Unlike alkenes that have 2 bonds. So they are more, they show higher degree of unsaturation than the alkenes. Hence, they are chemically more reactive than the corresponding alkanes and alkenes. Their electron-rich triple bonds make them very prone to what? Addition reaction. We said that alkenes undergo addition reaction, is it not? With hydrogen, halogens, and some other chemicals. These people too, alkynes, they also undergo addition reaction. Exactly. So in subsequent classes, we look at a particular alkyne known as ethyne. Just the way we did for the other ones. Are we together? Thank you. Yes, we look at the most important alkene. The most important alkyne. We look at the most important alkyne. Ethyne. Ethyne is the first member. It is the what? First member of the alkyne homologous series. Ethyne. Ethyne. You understand? And it has the molecular formula of what? C2H2. And the structural formula of CH, triple bond CH. How can you get ethyne in the laboratory? How do you prepare ethyne? If you want to have ethyne, how do you get it? How do you prepare it? It is prepared by the action of cold water. By the action of what? Cold water on calcium carbide. On what? Calcium carbide. The gas evolved its first pass through an acidified copper 2 tetrahydrosulfate 6 solution. Why? In order to remove any phosphine what? Impurity. Is that clear? So when you pass, when there is an action of cold water on calcium carbide, you produce ethyne. but the ethyne that you produce is impure because of some impurity, and the name of that impurity is phosphine. And to remove this phosphine, you need to pass it through what? Acidified copper 2 tetraoxosulfate 6 solution. Is that clear? Then collected over water. It is collected over water to cleanse it up. The process involves large amount of what? Heat, and is performed on a heap of what? Sand inside a flask to prevent the letter, to prevent your ethyne from what? Cracking. You have to do it in a flask that contains heap of sand because the heat is so much. You understand? If the heat is so much, the flask might just crack. The flask that you're using to prepare it, you understand? So make sure that you put a heap of sand in contact to prevent the flask from what? Cracking. This is the equation of reaction. Carbon carbide reacting with what? Cold water to give this calcium carbide reacting with cold water to give what? Calcium hydroxide and what? Ethyne, which is what you need. What are the physical properties of ethyne? Number one, it is a colorless gas with a characteristic what? Sweet smell. Sweet smell whenever it is pure. You understand? When it's pure, it has sweet smell. That's how you identify it. You understand? We say that methane is colorless and odorless. This one has a sweet smell. It is slightly less dense than air. It is sparingly soluble in water. It is unstable and may explode on compression to liquid. If you want to compress it into liquid, it may just do what? Explode. So how do you store it? If you cannot compress it to liquid, how do you store it? For storage purposes, ethyne is usually dissolved in what? Propanone. Another word for propanone is what? Acetone. And kept in steel cylinders at about 12 atmospheres pressure. That's how you store it, you understand? So you can store ethyne by what? Dissolving it in propanone, also called acetone, and kept in a steel cylinder at about 12 atmosphere pressure. Exactly. So that's the little we know about ethyne, its preparation and physical properties. So we are going to look at the chemical properties and uses.
Hello, welcome. Let's look at some nonmetals and their compounds, starting with hydrogen. Hydrogen is an element with the simplest atomic structure. Hydrogen is usually placed in group 1 of the periodic table because it has one electron in its only shell. It is the lightest of all elements. Preparation of hydrogen from water gas, also known as Bosch process. Water gas is a mixture of hydrogen and carbon 2 oxide in the ratio of 1:1. It is prepared by passing steam through a tower of white hot coke at about 1200 degrees Celsius, producing a mixture of carbon 2 oxide and hydrogen known as water gas. This water gas obtained is then mixed with excess steam and passed over a catalyst of iron 3 oxide or chromium 2 oxide at 400 degrees Celsius or 500 degrees Celsius. More hydrogen gas is produced and the carbon 2 oxide in the water gas is converted to or oxidized to carbon 4 oxide. This is an exothermic reaction. The carbon 4 oxide is removed from the mixture by dissolving it in water under a pressure of 30 atmosphere. This is known as scrubbing. Other solvents like potassium hydroxide can be used to remove carbon 4 oxide from the mixture. If there is any unreacted carbon 2 oxide, this is absorbed in an ammoniacal solution of carbon 1 metanoate. This method is cheap because cheap materials are used. Laboratory preparation of hydrogen. Action of dilute acid on zinc. This is a method to prepare hydrogen in the lab by the action of dilute acid on zinc. This is a displacement action because zinc will displace hydrogen from hydrochloric acid because it is above hydrogen in the activity series. Method: put some piece of zinc into a flat bottom flask or bottle and add dilute hydrochloric acid by means of a testo funnel. If the zinc is pure, add a few drops of copper 2 tetraoxysulfate 6 solution to act as a catalyst. There is effervescence and hydrogen gas is given off. Allow the first gas evolve to escape to ensure that the air originally inside the flask is swept away. This is very important as hydrogen forms an explosive mixture with air. Physical properties of hydrogen. Hydrogen is the lightest element known. It is 14.4 times less dense than air. It is neutral to moist litmus paper. It has no action on either red or blue litmus paper. Hydrogen is a colorless and odorless gas when pure. it is slightly soluble in water, 2 parts dissolving in 100 parts of water by volume. Chemical properties of hydrogen. Hydrogen reacts with metals to form ionic hydrides. Hydrogen gives a pop sound when a flame is applied to it. This is even the characteristic text for hydrogen. It also burns with a blue flame to produce water. Hydrogen reacts with an explosion with chlorine gas or bromine to produce hydrogen chloride or hydrogen bromide. Hydrogen is a good reducing agent. It reduces copper 2 oxide to copper. Uses of hydrogen. Hydrogen is used in filling balloons and airships because it has a low density. Hydrogen is used in hardening fats and oil in the manufacture of margarine and other solid fats. Hydrogen gives out a lot of heat when it burns, and as a result of it, used in oxyhydrogen flame to produce a high temperature for welding metals. Hydrogen is used in the manufacture of ammonia by Haber process. In the conversion of coal to petrol, a paste of coal dust and oil containing iron oxide and alkali as catalyst is spread into hydrogen at 200 atmosphere pressure and 450 degrees Celsius temperature. The products are hydrocarbon gases and liquid oil. Test for hydrogen. Hydrogen gives a pop sound when a flame is applied to it. It also burns with a blue flame to produce water. Hydrogen reacts with an explosion with chlorine gas or bromine to produce hydrogen chloride and hydrogen bromide. Please, if you like this video, hit the subscribe button. If you have any question, drop it on the comment section. Like and share our videos. Thanks and God bless you. Hello, welcome. Today we're going to be looking at sulfur and its compound. Sulfur is the second member of the group 6 in the periodic table of elements. Unlike the first member, oxygen, which is a gas, sulfur is a solid. It is a yellow non-metallic, naturally occurring element, found mainly in the upper surface of the earth, in Sicily, and in deep in the earth in the USA. It has a relatively low melting point of 387 Kelvin or 114 degrees Celsius and is practically insoluble in water. This would suggest that sulfur is a covalent element. Now let's look at the allotropes of sulfur. Allotropes are just different forms in which sulfur can exist due to its structure. Solid sulfur can exist in 3 allotropic states, and those are rhombic sulfur, monoclinic sulfur, and amorphous sulfur. So let's look at the first one, rhombic sulfur. This is the most stable allotrope at temperature below 96 degrees Celsius. It can be prepared by dissolving powdered raw sulfur in carbon 4 sulfide and allowing the solvent to evaporate slowly. The preparation should be done in a fume cupboard because carbon 4 sulfide is poisonous and highly flammable. It should be highly flammable. Now, monoclinic sulfur. This is the stable form of sulfur above 96 degrees Celsius and produced if sulfur crystallizes above 96 degrees Celsius. It is prepared by cooling molten sulfur. Heat some powdered sulfur in a crucible till it melts. Add more sulfur and continue heating and stirring at the same time. Repeat this process until the crucible is almost filled with molten sulfur. Now let's look at amorphous sulfur. These ones are crystals, but this is amorphous. Amorphous sulfur can be prepared in several ways. One method is by saturating hydrogen sulfide with distilled water and then exposing the sulfur to air. Sulfur will be deposited as an almost white powder known as amorphous sulfur. It is also prepared by the action of dilute hydrochloric acid on triazonitrate and triazothiolsulfate 6 solution. Now let's look at the properties of sulfur, the physical properties. Sulfur has a melting point of 115 degrees Celsius and a boiling point of 444 degrees Celsius. Sulfur is soluble in organic solvents such as benzene, toluene. It is also soluble in carbon 4 sulfide, but insoluble in water. Sulfur is a bad conductor of heat and electricity. Sulfur is brittle. Let's look at the chemical properties of sulfur. Reaction with air or oxygen. Sulfur burns in air or oxygen with a blue flame to produce sulfur 4 oxide gas, which is acidic to litmus. With metals, sulfur reacts with most metals to form sulfides, and some of these reactions are vigorous. Reactive metals like sodium and potassium may even react with sulfur without heating. Sulfur combines directly with metals. Iron and sulfur mixture, when heated, produces iron 2 sulfide. The same thing applies to a heated mixture of copper and sulfur, which produces copper 1 sulfide. Reaction with oxidizing agents. Sulfur is readily oxidized on warming with concentrated tetraoxosulfate 6 acid to form sulfur 4 oxide. The acid is reduced to sulfur 4 oxide. If warmed with triazonitrate 5 acid using bromine as catalyst, sulfur is oxidized to tetraoxosulfate 6 acid. Now let's look at the uses of sulfur. Sulfur is used in the manufacture of tetraoxosulfate 6 acid. It is also used in the production of chemicals such as carbon 4 sulfide and calcium hydrogen triazosulfate 4. Sulfur is used to manufacture the bleaching agents used in pulp and paper industry. It is used as sulfide in the manufacture of matches, fireworks, and gunpowder. Sulfur acts both as an insecticide and as a fungicide. It is used for the manufacture of drugs. Many modern drugs contain sulfur, such as M&B, which prevents pneumonia, antibiotics, e.g. sulfathioxole, and sulfur ointment for curing skin diseases. For the vulcanization of rubber, a process which converts the soft pliable rubber into hard tough substance from which motor tires and similar products are made. So sulfur is that element that is used for vulcanization, an application used in repairing our motor car tires. Now let's look at the preparation of some of the compounds of sulfur, like sulfur 4 oxide. The steps are: hold a moist potassium heptaoxodichromate 6 pepper. A solution of sodium chloride is left in the flask and the pepper changes from orange to green, showing the reducing property. Laboratory preparation of sulfur 4 oxide. Another laboratory method of preparing sulfur 4 oxide gas is by heating concentrated tetraoxosulfate 6 acid with copper. This is more hazardous as the gas is evolved with effervescence. Reaction with alkalis. As an acid, the gas sulfur 4 oxide reacts with aqueous sodium hydroxide to form an acid salt called sodium hydrogen trioxosulfate 4, or the normal salt sodium trioxosulfate 4. The acid salt is formed when excess sulfur 4 oxide is used. Trioxosulfate 4 acid. Trioxosulfate 4 acid is a diabasic acid which forms 2 sodium salts with sodium hydroxide. When a limited amount of sodium hydroxide is used, the acid salt sodium hydrogen trioxosulfate 4 is produced. Commercial preparation by contact process. Tetraoxosulfate 6 acid is prepared commercially by the contact process. Sulfur is first burnt in air to produce sulfur 4 oxide. This sulfur 4 oxide can also be produced by roasting iron pyrites, that is FeS2. If the sulfur 4 oxide is prepared from pyrites, it is purified. Purification is by removing any substances such as arsenic, which would poison the catalyst in the next stage. Sulfur 4 oxide is mixed with air, dried, and passed over heated vanadium 5 oxide. This is 2. As catalyst to a temperature of 450 degrees Celsius. Vanadium 5 oxide is used instead of platinized asbestos as catalyst because it is not easily poisoned. The sulfur 4 oxide reacts with oxygen from the air to produce sulfur 6 oxide. As a typical strong diabasic acid, dilute tetraoxosulfate 6 acid is strong and diabasic. The properties are: it turns blue litmus red, it reacts with alkalis and bases to form salts and water, it reacts with more electropositive metals to liberate hydrogen, it reacts with triazocarbonate 4 to liberate carbon 4 oxide. As an oxidizing agent, hot concentrated tetraoxosulfate 6 acid is a strong oxidizing agent. It oxidizes many elements, both metals and nonmetals, to their oxides, and is itself reduced to sulfur 4 oxide. Uses of concentrated tetraoxosulfate 6 acid. Tetraoxosulfate 6 acid is used in the manufacture of paints and pigments. It is used in making cellulose film, natural and artificial fabrics, as well as plastics. It is used as an electrolyte in car batteries and accumulators. It is also used in the manufacture of fertilizer. It is used to clean or pickle metals before electroplating or enameling. It is also used in the production of tetraoxosulfate 4 salts. The acid is used to manufacture rayon, which is an artificial silk, detergents, and car batteries. It is used in removing impurities from crude oil. Test for tetraoxosulfate 4 acid or tetraoxosulfate 6 in solution yield a white precipitate of barium tetraoxosulfate 6, which is insoluble in hydrochloric acid on addition of barium chloride. The purpose of hydrochloric acid is to dissolve any barium trioxosulfate 4 or barium trioxocarbonate 4, which might also form but which reacts with the acid and is dissolved by it. Hydrogen sulfide is a naturally occurring gas produced by decaying animal and vegetable substances, especially those of high protein content. Hydrogen sulfide is also released into the atmosphere during the combustion of coal. Laboratory preparation of hydrogen sulfide. Hydrogen sulfide is prepared in the laboratory by the action of dilute acid on iron 2 sulfide. The preparation should be carried out in fume cupboard because hydrogen sulfide is poisonous. Method: put some iron 2 sulfide chips in a flat bottom flask and cover with water and set the apparatus. Add some concentrated hydrochloric acid through a Thistle funnel. The gas is collected over warm water in order to dissolve traces of hydrogen chloride gas. Collect the pure dry gas by first passing it through water and then through a U-tube containing fused calcium chloride to dry the gas. Collect by downward delivery as the gas is denser than air. Physical properties of hydrogen sulfide. Hydrogen sulfide is a colorless gas with characteristic offensive odor of rotten egg. It is denser than air. It is fairly soluble in water at room temperature. It is very poisonous. It burns with a pale blue flame. Chemical properties. Hydrogen sulfide as a reducing agent. Hydrogen sulfide is a powerful reducing agent. During the redox reaction, hydrogen sulfide is usually oxidized to sulfur, while the electrons released in the process are accepted by the oxidizing agent. Test for hydrogen sulfide. A gas with a repulsive smell like that of rotten eggs is probably hydrogen sulfide. Confirm this by doing the following test. With lead 2 triosonitrate 5, musting a piece of filter paper with lead 2 triosonitrate 5 solution and drop it in a gas jar of the unknown gas. If the gas is hydrogen sulfide, the pepper turns black due to the formation of black lead-2 sulfide. Lead-2 ethanoate 2 gives the same reaction. So that's where we're going to end for a very detailed straight to curriculum course outline for JAMB and WAEC for sulfur and its compounds. Please, if you like this, hit the subscribe button by this side of the screen. If you have any question, drop it on the comment section. Like and share our videos so that your friends can see them. Thank you and God bless you.